Welcome to an Introduction to Calculus. This course is intended to bring you up to speed quickly with ideas and techniques in calculus which are commonly used throughout science and engineering, and also in many applications in business and economics. The course is organised into 5 modules, supported by videos, accompanying notes, formative practice exercises that develop mastery of the concepts, and graded exercises that verify your level of achievement. The first 2 modules discuss pre-calculus, setting the stage and helping you develop a repertoire of important and useful functions. A function is a process or rule that finds connections or relationships between different physical quantities or measurements, represented in this course always by real numbers. The pre-calculus provides all the necessary background and foundations for the rest of the course. Pre-calculus can be difficult and challenging, especially if you're not used to the ideas, notation or terminology. It might seem sometimes that I'm speaking in a foreign language. Nevertheless, I hope you'll be able to engage with the exercises, find them interesting and useful in developing familiarity and fluency with the key ideas, as this will set you up for a smooth transition into the remaining modules. In learning mathematics, there's no substitute for practice. The best way to develop focus and practice is to attempt the exercises, and they've been carefully designed to support your learning. The 3rd and 4th modules introduce limits and derivatives. Limits are a precise mathematical tool for connecting finite objects, which we typically think of as represented by real numbers, with intriguing processes that play with notions of infinity going on forever. Have you ever stood in the middle of a road, gazed into the distance, and seen the sides of the road converge to a point on the horizon? How can that be? The sides of the road remain the same distance apart always, yet they seem to meet at infinity. The image on your retina, a single dot where they appear to meet, is an example of a limit point. When limits are combined with ratios or rates of changes, particular types of fractions, then we obtain derivatives and the theory of differential calculus. Techniques of differential calculus lead to some of the most profound applications and insights. These techniques led to an explosion of progress and activity in science from their discovery in the 17th century. Are you intrigued by space travel? By the possibility of travelling to the stars and beyond? In the 17th century, Isaac Newton imagined just that. In a feat of imagination and creative thinking unmatched until Einstein in the 20th century, Newton worked out the escape velocity of a rocket. By pure reasoning, he figured out that in order for a rocket to escape the gravitational field of the Earth, without any further forces acting, it would have to move at 11 kilometres per second. His calculation involved the theory of calculus that he'd only just invented, and estimates about the radius of the Earth from ancient astronomy. By the time you reach the end of this course, you'll be able to reconstruct Newton's thought processes. But you will need the last module. The 5th and final module introduces the integral calculus, which again uses limiting processes, but now applied to areas. The fundamental theorem of calculus, discovered in the 17th century independently by Newton and Leibniz, reveals the most remarkable connection between areas defined by curves and slopes of tangent lines to curves. Why might that be useful? Well, this connection leads naturally and surprisingly into theories of differential equations and their solutions, which are ubiquitous throughout science. We hope you enjoy this course. Calculus is a miracle of invention and one of the great pinnacles of the imagination of the human mind. We hope that you don't get tired from being surprised at every turn, and that you obtain great benefit from the videos and the practice and challenges provided by the many exercises. So let's begin. In this video, we introduce the real line, discuss different kinds of numbers that fall on the real line, and how they can be represented using decimal expansions. We also briefly discuss approximations, significant figures, and scientific notation. All of the numbers you use or meet in this course may be regarded as falling on the real number line, indicated like this, extending infinitely to the left and to the right. Somewhere in the middle is the number 0, and you can see the counting numbers 1, 2, 3 going to the right, and the negative counting numbers going to the left. These points that I've indicated are called integers. And in between there's lots of other numbers. For example, halfway between 0 and 1, is the number 1/2, which has the decimal expansion 0.5. Okay, halfway between 1 and 2 is the number 1.5, or 3 on 2, which has the decimal expansion 1.5. Now if we go, say, 1/3 of the way between 0 and 1, somewhere like here, we have the number 1/3. And if you divide 3 into 1, repeatedly you just get lots and lots of 3s that go on forever. We say 1/3 is 0.3 repeated. If we look close to 1, there's a number here, say 6/7. Okay, and if you divide 7 into 6 repeatedly, what you get is 0.857142, and then the digits repeat, 857142 forever. So we say 6/7 is 0.857142 repeated. Now let's have a closer look at 1/3. 1/3 is 0.3 repeated. So what should 2/3 be? It stands to reason that that should be 0.6 repeated. So what should 3/3 be? It stands to reason that 3/3 should be 0.9 repeated. But notice 3/3 is actually 1. So what we have is that 1 has this decimal expansion 0.9999 going on forever. Okay. So if I take 1 and I look at this decimal expansion and say truncate at, say, the 3rd decimal place, I get 0.999, which is a little bit less than 1. If I go further along and add more 9s and stop, I still get a number which is a little bit less than 1. The further I go along this decimal expansion, the closer I get to 1. And if I imagine going on forever, in the limit, we actually reach 1. Okay? And this idea of looking at an approximation and seeing what happens in the limit is a central core concept in calculus, and you'll see it many times in this course. Now there are lots of other numbers, interesting numbers on this real number line. If I look just below 1.5, there's a number called the square root of 2. Now the square root of 2 has a decimal expansion 1.41421 and so on. Now this differs from the other examples. No matter where you look in the decimal expansion of the square root of 2, you never get a repeated pattern of digits that goes on forever. Okay? The square root of 2 turns out not to be a fraction involving counting numbers. It's said to be irrational, and that's an idea that we explore in the next video on the theorem of Pythagoras. What is the square root of 2? Well, it's a number whose square is 2, literally. So if I take a square, okay, whose side lengths are this number, the square root of 2, when I multiply these two numbers together, I get an area which is exactly 2 square units. Now there's another number, very important number on this line, a little bit more than 3. This number is called pi. And its decimal expansion is 3.14159 and so on. And like the square root of 2, no matter where you look on the decimal expansion for pi, you will never get a sequence of digits that repeats forever. Right? Pi turns out also not to be a fraction. The verification of that, in fact, is quite sophisticated, and to see that you would need all the tools that we develop in calculus in this course. Pi is defined in terms of circles. If I take a circle and I create a diameter, and I look at the perimeter, call that P, pi is in fact defined to be the ratio of the perimeter to the diameter. the fraction formed by dividing p by d. Now this is not a fraction involving counting numbers or integers, it's a fraction involving real numbers. And it's an amazing fact that no matter what circle I choose, no matter how small or how large, this ratio, p divided by d, is the same. It's not obvious, it's a fact that most people take for granted. And the reason it's true, in fact, is because all circles can be approximated arbitrarily well using similar triangles. And it's a fact from geometry that ratios of corresponding sides of similar triangles are equal. And that fact, when you take the limit using a limiting process, that produces this fact that pi is constant for all circles. Now, in real life, we can't use infinite decimal expansions of numbers. When we come to apply numbers, we have to use a finite number of decimal places. For example, on your calculator, you'll read a display with maybe 8 or 9 or 10 digits, depending on how powerful your calculator is. You certainly don't see an infinite decimal expansion of a real number. For example, a third as an abstract real number is 0.3 repeated. But if I decide to truncate, if I just read the first 3 decimal places, I get 0.333. So instead of equals, I've actually got approximately equal. A third is approximately equal to 0.333 to 3 decimal places. Okay. Now 2/3, which is 0.6 repeated, if I truncate at the 3rd decimal place, instead of 0.666, I round up to 0.667. To 3 decimal places, this is closer to 2/3 than 0.666. So in that other example we had, 6/7, remember that's 0.857142 repeated. If I truncate that at the 3rd decimal place, I get 0.857. If I decided to truncate at the 1st decimal place, I'd actually round this up to 0.9. Okay, so there are 2 different approximations to 6/7. One is more accurate than the other, to 3 decimal places, but the most accurate approximation to 1 decimal place of 6/7 is 0.9. Okay. Now the real number line is equipped with an arithmetic. You can do addition, subtraction, multiplication and division. And there are various rules for handling approximations when you apply these arithmetic operations. Okay, the first rule, when adding or subtracting, quote your answer to the least number of decimal places that is used. The second rule, when multiplying or dividing, quote your answer to the least number of significant figures that are used. I'll explain what significant figures are in a moment, but let's just illustrate the first rule. Okay, suppose I have a length which I've measured correct to 1 decimal place, say 9.4 centimetres. Then I want to add to it another length which I've measured carefully, this time to 2 decimal places, which is 2.13 centimetres. Okay, when I combine the 2 lengths, I have to add these 2 numbers together. So the combined length is 9.4 plus 2.13, okay, and that's 11.53. Okay. Now the 3 in the 2nd decimal place can't be relied upon because the coarsest measurement is the 9.4. Right? Because the coarsest measurement is to 1 decimal place, I'm not entitled to quote the answer to 2 decimal places, so I approximate this to the nearest number to 1 decimal place, which is 11.5. Okay, similarly with subtraction, suppose I take this length, 9.4 centimetres, and I remove a segment which I've carefully measured to be 2.13 centimetres. Okay, so what's left is the difference, 9.4 minus 2.13 which is 7.27. Okay. Once again, this 7 in the second decimal place can't be relied upon because of the coarseness of the measurement of the 9.4, which is correct only to one decimal place. So again, you round your answer to the nearest number to one decimal place, which is 7.3. Okay, let's do an example with multiplication. Suppose I take a rectangle which is 9.4 centimetres wide and 2.13 centimetres high. Right, so the area is obtained by multiplying the numbers together. 9.4 times 2.13. Okay, if you type that into your calculator, it's a little bit hard to do in your head, you should get 20.022. But not all these digits are significant. You don't expect to be able to quote this answer to this degree of accuracy. The rule for multiplication is that you quote your answer to the least number of significant figures that appear in each of the numbers that are used in the arithmetic. The number of significant figures is the number of digits, regardless of the decimal point. So the 9.4 uses 2 significant figures. The 2.13 uses 3. So we quote our final answer to 2 significant figures, which gives you an approximation of 20 square centimetres. Now if I just say 20 square centimetres, without reference to the original problem, it's ambiguous. You don't know whether I'm saying this rectangle is 20 centimetres correct to the nearest unit or possibly to the nearest 10 units. Right? Is it 20 to the nearest unit or 20 to the nearest 10 square centimetres? Okay. Now it may look a little bit pedantic, but to be more precise, you could write this as 2.0 times 10 square centimetres. And the fact that you've written 2.0 means that this 0 in the expression is significant. Okay, so this is correct to 2 significant figures. Now if I wrote 2 times 10 square centimetres, because I've deliberately only written one digit, the 2, you know that the answer is correct to the nearest 10 square centimetres. So I'll give a more elaborate example. If you look, say, at the radius of the Earth, I believe that's 6,370,000 metres. Okay. Now if I just quote that number to you, you don't know whether any of those zeros are significant in the accuracy of the radius of the Earth. And in fact, the Earth is not a perfect sphere. Right? The radius changes as you move around the Earth. When I quote this radius, in fact, only 3 digits are significant. It's not obvious in the way the number's represented. So to emphasize that only 3 digits are significant, we express this in what's called scientific notation. I only list 3 digits, and we put the decimal point between the first 2 digits. And to recover the original measurement, we multiply by an appropriate power of 10. So the radius of the Earth in scientific notation is 6.37 times 10 to the 6 metres. And then the person receiving this information knows that you're only quoting the first 3 digits as accurate in this estimation of the radius of the Earth. Now we've covered a lot of ground in just a few minutes, and there are many important ideas. Everything we've touched on is carefully explained and expanded in the notes accompanying this video. If any of these materials require clarification, please make a posting on the online discussion forum. We welcome your input and feedback. In this video, we introduce the theorem of Pythagoras, possibly familiar to many of you from school. We'll look at it in the context of an interesting historical perspective relating to Babylonian mathematics. An application of this theorem is a geometric interpretation of the square root of 2, a very important real number in the history of mathematics. We prove that the square root of 2 is irrational, that is, cannot be expressed as a fraction, a result that was known to the ancient Greeks. We begin the story by considering a unit square with side lengths 1 unit. I'll reproduce the unit square. If you start off at, say, one corner and travel to the opposite corner, you could, for example, move along the sides of the square. But that's not the most direct path. The most direct path from one point to another is a straight line. If we go along the diagonal of the square, that's the shortest path, and it has a certain length. We'll call it x. So what I'm going to do is play around with this square. This is a trick that goes back to Babylonian times. So here we have a unit square, and I've just taken a copy of it, and I've formed a stack with 2 squares. I will just put another stack of 2 squares next to the original 2 squares to create a 2 by 2 square. So I've got 4 unit squares making a larger square with side lengths 2 units. Now I'm going to focus on the midpoints of the sides of this square, and then join up these midpoints by forming diagonals in this way. Okay, now notice something. In the middle of this 2 by 2 square is another square whose side length is x, the length of the diagonal of the unit square. And that inner square has an area which is x squared. Okay, now I can count the area by adding up the areas of certain triangles in this diagram. If I shade that triangle, then that has area which is a half of a unit square. Then I add the area of this triangle, another half, the area of this triangle, and the area of this triangle. So I'm adding a half 4 times, which gives you 2. So the area of the inner square, it's all shaded now in green, is 2 units. So x is a number whose square is 2, so x is the square root of 2. Okay. Now I'm going to do something. I'm going to copy this figure, and I'm just going to rub out everything outside that green inner square. And then I'm going to get some clay. So I've got some soft clay, and I've imprinted on that clay an image of that inner square that we've been discussing. I put it in the oven and bake it, and then a few thousand years later, this is what we get. Okay? This is called the Yale tablet, and it's the oldest recorded proof of the theorem of Pythagoras, and in fact predates Pythagoras by about 1,000 years. Now, what's this got to do with the theorem of Pythagoras? Well, let's go back to the unit square and its diagonal, which is the square root of 2, which we've demonstrated by that method. This is what's called an isosceles triangle, where the shorter side lengths are equal, in this case to 1. I can draw another isosceles triangle, which could be much bigger or much smaller, with common side length A. We scale up the lengths of the smaller triangle, so the hypotenuse of this new isosceles triangle is root 2 times A. Okay, and if we call that C, then C squared is root 2A all squared, which is 2A squared, which is A squared plus A squared. Right. Now perhaps you can see that this starts to resemble a familiar result. The square of the hypotenuse is the sum of the squares of the other 2 sides. This is a special case of a general theorem, the theorem of Pythagoras, which says if you take any right-angled triangle with side lengths A, B, and hypotenuse C, and A and B can be different now, if you form squares on each side of the triangle, then the square of the hypotenuse is the sum of the squares of the other 2 sides. So we get this famous equation, c squared equals a squared plus b squared. And this is the theorem of Pythagoras. And what we discussed earlier was, in fact, a proof of this theorem in the special case where a and b are equal to 1, which clearly scales up to a and b being equal. Now you can modify that proof very easily to get a general proof, and that modification appears in the notes that accompany this video. Now if we have a look, c squared equals a squared plus b squared implies that c is the square root of a squared plus b squared. Now when you have an expression involving a square root sign, it's called a surd expression. Okay, and you don't expect it to simplify. Occasionally it will. For example, if I take a right-angled triangle where the shortest side is 3 units long, the other short side is 4 units long, then the hypotenuse turns out to be 5 units long. Okay, so you have what's called a 3, 4, 5 triangle. The 5 is predicted by this theorem because 3 squared plus 4 squared, which is 9 plus 16, is equal to 25, which is indeed 5 squared. Okay. Now that's very rare that the hypotenuse simplifies so simply. Typically, the surd expression doesn't simplify, and if we go back to the unit square, triangle associated with a unit square, the hypotenuse has length root 2, and it turns out that root 2 cannot be expressed as a fraction. Okay. Now, of course, the distance between 2 points is very important, and ancient mathematicians wanted the mathematics to be sufficiently powerful to model distances between points. Okay. So studying the square root of 2, the diagonal of the unit square, was a very important kind of mathematical entity. And now, when you develop mathematics, you start off, for example, with counting numbers, and then you form fractions of counting numbers. They're called rational numbers. And it was an important question whether the mathematics of fractions was sufficiently powerful to model distances like the square root of 2. And it turned out the answer is no. There is no fraction which can be used to express the square root of 2 exactly. The square root of 2 is not a fraction. Okay, now I'm going to try and explain why this is the case. Now in mathematics, proofs or demonstrations are a little bit like criminal investigations. It's typical to make some kind of supposition and see if it leads to nonsense or a contradiction. Right? If you're investigating a crime and you want to know who was the murderer or who was the thief, if a suspect can produce an alibi that contradicts the possibility of them committing the crime, then you know that they're innocent. And we're going to use that technique in this proof. We're going to suppose, to the contrary, that root 2 is a fraction and see if it produces nonsense. Okay, so I'm going to suppose root 2 is a divided by b, where a and b are counting numbers or integers, and I can assume that we've cancelled off any common divisors in the numerator and the denominator, so that this is in reduced form, and that will turn out to be important. We will square both sides of this equation. On the left-hand side we get 2, on the right-hand side we get a squared divided by b squared. Okay, so if we multiply both sides by b squared, we get 2b squared is equal to a squared. Okay, so a squared is 2 times a counting number, 2b squared, so it's even. Okay, and it follows, you can think about why this is the case, that a itself must be an even counting number. So if it's even, it means it's 2 times something. Say a is equal to 2 times c for some counting number c. So if we go back to the previous line, we've got 2b squared is equal to a squared, but a is 2c, so that's 2c all squared, which is 4c squared. Okay. So now we divide both sides by 2, and we conclude that b squared is 2c squared. So b squared is 2 times something, which is even. And as before, if the square of a number, counting number, is even, the number must be even, so therefore b is even. Okay, now have a look. b is even, and a is even, so they're both divisible by 2. They've both got a common divisor of 2. And that contradicts the assumption that a over b is expressed in reduced form. So this is actually nonsense. It can't be true. So therefore root 2 is not a fraction. Again, we've covered a lot of ground in just a few minutes. Much more detail is provided in the accompanying written notes. Please take some time to read and digest them carefully, and then try the exercises that follow. Thank you for watching, and I look forward to seeing you next time. In this video, I'd like to discuss how mathematical expressions can be built and manipulated algebraically with, I think, some rather remarkable and surprising outcomes. I'll begin by relating a childhood experience that really stayed in my long-term memory and stimulated my interest in mathematics. Some people have bad or unpleasant experiences in early childhood that put them off mathematics. I was lucky and had a very fine teacher. One morning, he came into the classroom and said, "I want you all to think of a number between 1 and 10. It's your own secret number. Don't tell me or your friends. I want you to double it. Add 4. Halve what you see in your head. Remember your secret number. Don't tell anyone. Take it away. You are now thinking of the number 2. We were all indeed thinking of the number 2. This was quite astonishing to a child, and what was even more remarkable was that the teacher was able to explain carefully why we were all thinking of the number 2. Call this secret unknown quantity x, build up an algebraic expression that corresponds to the instructions, and see that it simplifies in every case to the number 2. It was, for me, quite amazing and powerful, my first experience of mathematical proof. I'd like to show you something surprising about some common everyday objects. Sheets of paper, in fact, in the A series. Here's A4. This is A5, half as big. A6, half as big again. And A7, half as big yet again. 2 A5s make an A4. 2 A6s make an A5, and so on. These pages are all rectangles. You can have thin rectangles, thick rectangles, rectangles with perfect symmetry known as squares. But notice that all of those sheets of paper in the A series form similar rectangles, by which we mean they have the same proportions. How can we prove that? Well, we can draw lines along the diagonals of each of them. If the diagonals all line up, then the rectangles are similar. See how all the diagonals line up? We can continue creating smaller and smaller similar rectangles forever just by dividing the sheets in half. Now, the diagonal lines of rectangles have a slope, and slopes are really important in calculus. So what we'll do now is try to understand this particular slope associated with the A series of sheets of paper. The slope is just the ratio of the side lengths. Here we have a diagram of an A4 sheet of paper divided exactly in half, so the two halves represent A5 sheets of paper. Call the longer side length B and the shorter side length A. So the shorter side length of the A5 half is B on 2, and its longer side length is A. Let X denote the ratio of the longer side length to the shorter side length. So for the A4 sheet, this is B on A, and for the A5 sheet, this is A over B on 2. Multiply top and bottom by 2, then divide top and bottom by A, and we get 2 divided by X. Thus, X is equal to 2 over X, so X squared is equal to 2. So X must be the square root of 2. Just using algebraic manipulation, we discover that for the A series of paper, the ratio of the longer side to the shorter side is the square root of 2. Now from your calculator, you'll see that the square root of 2 has this decimal expansion, and it goes on forever. There's no repeating pattern of digits because the square root of 2 is irrational, something we discussed last time. How does the calculator know that this is the correct way to start the decimal expansion? I'll show you a surprising consequence of algebraic manipulation. First, remove the 1 at the front by subtracting 1 from the square root of 2, and we get this mysterious decimal expansion after the decimal point. Now in mathematics, it's very important for all sorts of reasons to be able to reciprocate or invert numbers. Just for fun, let's play around with the reciprocal of root 2 minus 1. Who knows where it may lead? We get this awkward looking fraction. Any mixture of symbols involving the square root sign is called a surd expression. How might we simplify it? There's a technique explained in the notes called rationalizing the denominator. I won't go into the details here, but in this case it involves multiplying the top and the bottom by root 2 plus 1. When we do this, the numerator just becomes 1 times root 2 plus 1, which is root 2 plus 1, and the denominator becomes root 2 minus 1 times root 2 plus 1, which becomes root 2 squared minus 1 squared. This comes from something called the difference of two squares formula. A squared minus b squared is a minus b times a plus b, which we apply here with a equal to root 2 and b equal to 1. And so, because of this neat trick, the fraction simplifies in a couple of steps to root 2 plus 1. Thus we have shown that the reciprocal of root 2 minus 1 is root 2 plus 1. Reciprocating again, that is turning the fraction over, we get root 2 minus 1 is 1 over root 2 plus 1. Now there are more neat tricks. We can subtract 1 and add 1 in the denominator without altering the overall value of the expression. And then this becomes 1 over root 2 minus 1 plus 2. Now in mathematics and computer science, you almost always discover something interesting or useful if you can set up some kind of self-reference or recursion. We have that here. Now what do I mean? Well, put y equal to root 2 minus 1. So y equals 1 over y plus 2. And it's convenient to swap the 2 and the y around. This doesn't alter the value of the expression. And we get y equals 1 over 2 plus y. Now why should we get excited by this? I remember when I was very young having porridge for breakfast, and the oats came out of a packet with a picture of a man holding a packet, with a picture of a man holding a packet, with a picture of a man holding a packet, and so on forever. It was intriguing, mind-boggling that infinity could sneak its way into the kitchen. And we have that here. Y is our packet of oats with this self-referential property. We can feed y into itself, again, and again, and again and again, going on forever, creating what is called a continued fraction expansion. Remember, y equals root 2 minus 1, so here's its continued fraction expansion, going on forever. Of course, we can't compute with infinite expressions, but we can approximate them. What we do is truncate the expression somewhere, say here, and equals becomes approximately equals. And then evaluate this fraction on the right-hand side inside out. We get 5 on 2, which becomes 2 on 5, which unravels in a few steps to become 29 on 70. Thus we have that root 2 minus 1 is approximately equal to 29 on 70, so root 2 is approximately 1 plus 29 on 70, which equals 99 on 70. We've just played with simple numbers and come up with this approximation. So how good is it? If you square 99 on 70, you get 9,801 divided by 4,900, which is almost 9,800 on 4,900, and that's exactly equal to 2. The difference here is 1/4,900th. So close. If you start dividing 70 into 99, you get a recurring decimal expansion after several steps with repeating digits ad infinitum. Here's the decimal expansion of root 2 again. Notice that these decimal expansions agree up to the first 4 digits past the decimal point. Now we just took a few layers of the continued fraction, and just in a couple of minutes we produced a rational number approximation whose expansion gives the first 4 digits of root 2 after the decimal point. Now before mathematicians had calculators, this is how they would get such amazingly accurate approximations of numbers. They'd use some kind of clever algebraic manipulation to get an approximation involving fractions, which in turn involve simple counting numbers. And then it becomes straightforward, though possibly tedious, to write out the decimal expansion, which eventually repeats, being a recurring decimal. Just for fun, you could go back to that truncated continued fraction, add some more terms, and get an even more accurate approximation of the square root of 2. We've covered a lot of ground in a few minutes, including developing some techniques of algebraic manipulation, looking at surd expressions involving square roots, including a rather surprising example of reciprocation leading to a recursive formula, and a novel method of approximation using a continued fraction. There's more detail in the notes, and I'd like you to read and digest them. When you're ready, please have a go at the exercises. We should give you a thorough workout with manipulating fractions in all sorts of combinations, including symbols and numbers, and some practice with the technique of rationalizing the denominator of a fractional surd expression. Thank you very much for watching, and I look forward to seeing you again soon. In this video, we discuss equations or equalities, when things are equal, and inequalities, a complementary notion when things are not equal. Often we're trying to isolate, evaluate, or estimate some unknown quantity, typically denoted by x. It turns out that essentially the same algebraic tools apply for both equalities and inequalities, though a little bit more care is needed for inequalities. Let's begin with a simple equation involving an unknown x. 2x plus 1 is equal to 7, and as usual x is an unknown and we want to find out what it is. And the idea is that you try and isolate x. Okay, so we want to x is embedded in this expression 2x plus 1. We want to somehow separate it out so that we get it standing on its own. Okay, so we just get to x in 2 steps. We'll take 1 away from both sides, and we get 2x is equal to 6. And then we divide by 2, and we end up with x is equal to 3. And of course, when you do a calculation like this, you can always check that your answer works. Right, 2 times 3 plus 1 is equal to 6 plus 1, which is equal to 7. So the left-hand side and the right-hand side of the original equations agree when x is equal to 3. Okay, now let's make things a little bit more elaborate. Again, I'm going to write down an equation, but x will appear more than once. In fact, x appears 3 times and it's sort of mixed up with fractions. And again, the aim is to isolate x. So we'll start off by simplifying the expressions involving fractions on the right-hand side by getting a common denominator of 10. And then the numerator simplifies to 7x minus 9. And then we multiply both sides by 10. We can simplify the left-hand side a little bit. And then multiply both sides by 2. Add 18 to both sides. Subtract 5x from both sides, and we get 18 is equal to 9x. Divide through by 9, and then put x first, and we get x is equal to 2. Now that was a rather long process, but can you see that in principle it was no more difficult than the previous exercise? There's a little bit more rearranging, and x appeared more than once, but it was like sort of gathering apples or oranges. We just collect together everything involving x until we've just got one x, then simplify the expressions until we get x on its own. Of course, you can check that the answer is correct by feeding back into the original equation and checking that the left-hand sides and the right-hand sides are in fact equal. But what I want to do next is something that's qualitatively quite different. It involves a completely new idea to just simply rearranging information. Let's consider the following equation. Again, x appears more than once. It appears twice. Now this equation is very special because 0 appears on the right-hand side. The left-hand side is a product of two numbers, x minus 1 and x minus 2. And whenever you have a factorization of 0, you're able to make progress almost immediately. A consequence of this equation is that at least one of the factors has to be equal to 0. And why is that? Well, it's a property of multiplication of real numbers. If I take a rectangle, side lengths a and b, then the result of multiplying a and b, which we call ab, geometrically is the area of this rectangle. Okay, now let's suppose the product of a and b is equal to 0. Okay, what does that imply about the geometry of the rectangle? It means the area has to be 0. So how can that be the case? It means the rectangle becomes infinitely thin. There's at least two possible ways. The rectangle could become infinitely thin of length b, so a turns out to be 0. Another possibility is that the area could become 0 by becoming an infinitely thin line of length a, and now b has become equal to 0. Okay, there's in fact a third possibility, and that's that the whole thing contracts to a single point with 0 area, in which case both a and b are equal to 0. But the upshot of this is that if AB is equal to 0, if the area of the rectangle is equal to 0, then either A is equal to 0 or B is equal to 0. And it's this fact that was used, if we go back to the equation, to deduce that either x minus 1 is equal to 0 or x minus 2 is equal to 0, where x minus 1 has the role of A and x minus 2 the role of B. So what we have is that our original equation is split up into two equations where in each case x appears only once. So by simple rearrangement of the information in each case, we isolate x as either 1 or 2. I would like to revisit this equation using a technique that I saw a student use years ago. The student had very little mathematical experience and background, so was using his own ingenuity. And he ignored this property of 0 that we've used just now to solve this equation. He just started off by expanding the left-hand side. Okay, so if you multiply out the brackets, you get x squared minus 3x plus 2 is equal to 0. Okay. And his idea was to, again, try to isolate x. And the first step will be perhaps to strip away the 2 from the left-hand side, take it away, and you get x squared minus 3x equals minus 2. And then he did something really, really clever. He added 9 divided by 4 to both sides. Yeah, now, why on earth 9 on 4? Well, let's just see that the right-hand side simplifies to a quarter. I'll just explain why 9 on 4. Notice that 9 on 4 is actually minus 3 on 2 all squared. And the minus 3 on 2 is a half of the coefficient of x. Now, where is all this leading? Well, by choosing minus 3 on 2 squared, the left-hand side can be rewritten as x minus 3 on 2 all squared. What the student was doing, in fact, is an application of the following algebraic identity. A plus b squared is a squared plus 2ab plus b squared, where a is equal to x and b is equal to minus 3 on 2. This trick of adding 9 on 4 to both sides, a few steps back, produces this perfect square effect. This technique is called completing the square. Okay, and it's a very important trick that you're going to see formalized in the next module when we discuss the quadratic formula. And now, what's the whole point of this? Well, notice at the last line, we've got an expression on the left-hand side with only one instance of x. So now to isolate x is relatively straightforward. It's reduce the problem to something similar to what we've seen before. You just strip away the expression until you get x on its own. So we get x minus 3 on 2. If we take square roots of both sides, on the left-hand side we get x minus 3 on 2. On the right-hand side we get plus or minus the square root of a quarter, which is plus or minus a half. By adding 3 on 2 to both sides, we isolate x as 3 on 2 plus or minus a half. 3 on 2 plus a half is 2. 3 on 2 minus a half is 1. So we get the two answers that we saw previously. Yeah, I thought I'd mention it because, firstly, it's a precursor to something that we see in more detail in the next module, the quadratic formula. But also, I just want to highlight the fact that even though this student had very little mathematical background, just thinking imaginatively about the numbers and the expressions involved, he was able to do something really original and creative. And I want to emphasize this fact because a lot of you possibly don't have much knowledge of calculus, but I want you to feel like you're on a journey of discovery, right? Even if you discover something that's well known, or even possibly very old or ancient, I want you to feel like you're discovering it for the first time. Now, so far we've just discussed equations. I want to move on to discuss inequalities where things aren't necessarily equal. But in order to formalize that or make sense of that, we need an ordering, what's called an ordering of the real number line. Okay, so let's take the real number line. If there's 2 points A and B, and A appears to the left of B, then we say that A is less than B, and we write that symbolically with a less than symbol. This here is a less than symbol. Notice that the pointy bit of the symbol points to the left-hand side. Where it sort of opens up, points to the right-hand side. Since B is to the right of A, we say A is less than B. We can rewrite this also using a greater than symbol. To say A is less than B is equivalent to saying B is greater than A. So the greater than symbol means that the thing that's greater is to the right of the thing that's less. There are two other symbols. We say A is less than or equal to B, using this symbol, if A is less than B, to the left of B, or possibly equal to B. We also write A is greater than or equal to B if A is greater than B, to the right of B, or possibly equal to B. So for example, here's a real number line and say 0 in the middle. Here's a few numbers. So because I've pointed out negative 20 on the line, that's less than negative 15, which is less than minus 10 and so on, less than 0, less than say 5, less than 10, less than 15. Okay, now notice that minus 20 is less than 5. Okay. Now minus 20 you might think of as a sort of large number in size, and indeed it has a large, what's called absolute value or magnitude, something I'll talk about in a future video. But in terms of the ordering on the number line, we still say negative 20 is less than 5. Okay? It might sound a little bit unintuitive, but when we say less than, we just mean to the left of on the number line. So now we've got these symbols, less than, greater than, less than or equals, and greater than or equals. Let's explore some relationships between numbers that use some of these symbols. Let's revisit the very first example we discussed, 2x plus 1 equals 7. But instead of equals, let's turn it into an inequality. Let's have less than. Now to solve this inequality, it's exactly the same process that you saw when it was equals. You subtract 1 from both sides and the inequality is retained. And you isolate x finally by dividing by 2. So the answer is x is less than 3. Okay, let's do something a little bit more elaborate. Let's solve this inequality. 1 minus x is less than 3x plus 6. Okay, so notice that x appears more than once, so there's a little bit of work to do to isolate x. Now it's really very similar to the first couple of examples, but a little bit of care is needed when you're dealing with inequalities. I'll show you what I mean. I could, for example, add x to both sides, which becomes 4x plus 6 on the right-hand side. Adding x doesn't change the inequality. And then I could subtract 6 from both sides, which also doesn't change the inequality. 1 minus 6 is minus 5. Okay. Now we usually like to have the x on the left-hand side, so now what I'll do is move this around. If minus 5 is less than 4x, then 4x is greater than minus 5. See how the inequality has changed? When I divide by 4, then we finally get x is greater than minus 5 on 4, and that's the solution. Let's approach this problem in a slightly different way, just to illustrate the sorts of variations in algebraic manipulation. Starting off with 1 minus x is less than 3x plus 6. What I'm going to do is multiply both sides by minus 1. Okay, so I'm going to take the negative of both sides. And now when you do that, when you multiply an inequality through by a negative number, it flips over. Okay. Now the reason for that is that when you multiply by a negative number, the relative left-right positions of numbers on the number line get inverted. It's like looking in a mirror. Left becomes right and right becomes left. Okay. So that's a geometric explanation, but I also give an algebraic explanation in the accompanying notes. Anyway, the rule is if you multiply by a negative number or just take the negatives, then the inequality flips over. So less than becomes greater than becomes less than, and so on. Okay, so now what's the negative of the left-hand side? That's just x minus 1. The negative of the right-hand side is minus 3x minus 6. And we can gather together the x's, add 3x to both sides. On the left-hand side we get 4x minus 1, on the right-hand side minus 6. Add 1 to both sides. Divide both sides by 4. And we've got the same answer that we had before. X is greater than minus 5 on 4. Okay. So most of the manipulations we did, in fact all but one, kept the inequality, maintained the inequality. You just have to be careful that when you multiply by a negative number, you change the inequality. This was just to give you a taste of manipulations of equations and inequalities, using a few contrasting examples. In the next video, we'll introduce the notion of solution sets, which apply generally in all situations, and provide a very convenient way of capturing important information about real numbers using interval notation. Please read and digest the notes accompanying this video, and then try the exercises. Thank you for watching, and we look forward to seeing you again soon. In this video, we discuss sign diagrams, which indicate when mathematical expressions are positive or negative. Solution sets, a formal way of describing collections of real numbers that satisfy a specific criterion or criteria, often associated with sign diagrams. And interval notation, which is a succinct way of describing lots and lots of real numbers that fill up certain parts of the real line. We begin by discussing the notions of positive and negative when applied to real numbers. The real line splits naturally into two halves, divided by the number 0, which we think of as exactly in the middle. We often denote positive with a big plus sign and negative with a big minus sign. Now 0 is neither positive nor negative. It's just stuck there in the middle, separating the positive from the negative real numbers. Now, in an earlier video, I discussed interpreting a product AB as an area of a rectangle, where one of the side lengths is A and the other side length is B. Now, notice when I labelled the edges of this rectangle, I was careful not to assign any sense of direction. If you include in your mathematics an idea of direction, then you get this notion of positive and negative. Okay? And when you do that, then areas can also have a positive or a negative aspect. Positive and negative orientations of numbers occur quite naturally in everyday life. For example, if you drive along a straight road, you can move forwards or you can move backwards. And if you think of moving forwards as positive and backwards as negative, then when you add up all the effects, you may end up with some net displacement that is modelled in the mathematics of positive and negative numbers. You're going to see this to great effect towards the end of this course when we do integral calculus. And they're areas under curves, like areas of rectangles, but areas more generally under curves have physical interpretations, and it's important to be able to assign a positive or a negative direction or orientation. This area can be positive or negative. And the rules are that AB is positive, and that's expressed by saying AB is greater than 0, precisely when A and B are both positive or both negative. Okay, the product AB is positive precisely when both the factors have the same sign. They're either both positive or both negative. On the other hand, the product AB is negative precisely if A is positive and B is negative, or A is negative and B is positive. In other words, if the two factors A and B have different sign. Okay, for example, 2 times 3 is 6. 2 times minus 3, 2 lots of minus 3 is minus 6, and that's of course the same as 3 lots of minus 2, and that's the same as minus 2 times 3. Okay. If you introduce another minus, say you take minus 2 lots of minus 3, you don't get minus 6, you get plus 6. The product of two negative numbers is a positive number. If we revisit an example from the previous video, we saw in 2 steps that x is equal to 1 or x is equal to 2. Okay, so the expression x minus 1 times x minus 2 is equal to 0 precisely when x equals 1 or x equals 2. But what happens if we vary x if we change x, it's not 1 or 2? Okay, so if it's not 0, if the expression is not 0, then it will either be positive or negative. And it's very important in calculus to know when certain mathematical expressions become positive or negative. It's related to slopes of curves. Once we introduce calculus, you'll see lots of applications of knowing when an expression is positive or negative. The situation where an expression is positive or negative can be expressed very concisely using something called a sign diagram. And I'll explain it using examples, and you'll catch on very quickly. I draw what looks like a table. I have x on top, and I have the expression that we're investigating below. And there's a line in the middle which is meant to represent the real number line in as much as that it captures the important points where the expression becomes 0. So in this example, the expression is 0 when x is 1 or 2. So I label those points on the x side as 1 and 2. On the expression side, I put the expression evaluates to 0. If we consider x which are bigger than 2, to the right of 2 on the number line, then both the factors x minus 1 and x minus 2 are positive. And a product of positive numbers is positive. Now if we consider x between 1 and 2, then x minus 1 is positive, but x minus 2 is negative. A product of a positive and a negative number is negative. So on the sign diagram I put a minus sign between 1 and 2. Now if x is to the left of 1, then both x minus 1 and x minus 2 are negative. And remember, a product of two negative numbers is positive. And that completes the sign diagram. It gives you complete information about the sign of the expression as x varies over the real line. Okay, let's do a slightly more elaborate example. Just gradually increase the complexity. Okay, let's find the sign diagram for the expression x plus 1 times x minus 3. And the technique is you first of all work out where the expression is equal to 0. And it's very similar to the previous example. Where you've got a factorization of 0, that implies that at least one of the factors is equal to 0. And you quickly deduce that x is either minus 1 or 3. So now we build our sign diagram where the critical points where the expression is 0 is x equals minus 1 and x equals 3. So I draw points that correspond to minus 1 and 3, and the expression evaluates to 0. And then I just think about the sign of the expression as I move about the real line, backwards and forwards, past 3, between minus 1 and 3, and beyond minus 1. So let's do that. So if x is bigger than 3, then both x plus 1 and x minus 3 are positive. So the product is positive. Okay. If x is between minus 1 and 3, x plus 1 is positive, but x minus 3 is negative, so the product is negative. And finally, if x is less than minus 1, then both factors are negative. A product of two negative numbers is positive. Okay, and that's the complete sign diagram. Notice it's exactly the same as the previous sign diagram, except that the numbers, the critical points where the expression is 0 are minus 1 and 3. If you look at the notes that accompany this video, you'll see some more variations and an increase in complexity in the types of problems. Okay, now once you've got a sign diagram, you can ask yourself which real numbers satisfy a certain criterion, like being positive or negative or non-negative, which means positive or 0, or non-positive, which means negative or 0. And there's lots of other criteria. And we capture this idea of a collection of numbers satisfying a criterion using the notion of a solution set. A solution set is a collection of numbers that satisfy some criterion. So it's very general, and we talk about the solution set of an equation or of an inequality. So for example, the solution set of the equation x plus 1 times x minus 3 equals 0 is the set consisting of minus 1 and 3. Okay, now there's a few things to notice here. There's these curly brackets denote set or collection, and there's a comma that separates the elements. Okay, let's write down the solution set corresponding to an inequality. So let's write down the set of all numbers x that satisfy the inequality x plus 1 times x minus 3 is greater than 0. So once again we have curly brackets to denote set or collection, and then we write x in R such that x is less than minus 1 or x is greater than 3. Now this needs a bit of explanation. The curly brackets, as I said, denote set. This funny symbol that looks like a Greek epsilon is an abbreviation for element of. This strange looking R symbol is just an abbreviation for the set of all real numbers, or the real number line. And this vertical line is an abbreviation for such that. A lot of maths teachers use a colon, but if you try and do a colon on a blackboard or a whiteboard, often it's not very clear, and a vertical line turns out to be very clear. So you read this as the set of real numbers such that x is less than minus 1 or x is greater than 3. Now where did this come from? Well, that came from the sign diagram. If you go back to the sign diagram, where you see a plus sign for the expression corresponds to x being less than minus 1 to the left of minus 1, or x being bigger than 3 to the right of 3. By contrast, the solution set of the inequality where the expression we had before is less than 0, if we go back to the sign diagram, this expression is less than 0 if x is between minus 1 and 3. So when we describe the solution set, we get curly brackets, the set of x in the real number system such that minus 1 is less than x, which is less than 3. Okay, so this condition here, this captures precisely the fact that x is to the right of minus 1 and to the left of 3. Okay, now this set notation that I've sort of introduced you to takes a little bit of getting used to. It probably looks like a foreign language. There is a very succinct way of describing lots of real numbers using interval notation. Now, if I take, for example, the set of real numbers such that x is greater than 3, okay, if I picture the real number line and I find the number 3, all the numbers that are greater than 3 are the numbers that appear to the right of 3 on the number line. I'm not including 3, so I'll put a little circle around 3 to exclude 3, and then I'll just imagine covering the whole real line all the way off towards, indefinitely to the right, towards infinity. Okay. This is called an infinite interval to the right, and it's denoted very succinctly with a round bracket 3, comma, and then an infinity symbol. The round bracket means that you exclude 3. We of course exclude infinity because that's not a number. So I'll just introduce in general interval notation. There are several possibilities. Suppose I've located points A and B on the real number line. If I want to capture succinctly all the numbers between A and B, including A and B, this is denoted using square brackets. The square bracket A, comma, square bracket B is the set of all real numbers x such that A is less than or equal to x, which is less than or equal to b. The square brackets indicate that both A and B are included as possible values of x. Okay, now if we want to exclude A and B, we imagine tiny little circles that exclude A and B, but then we include everything in between. And then we use what's called round bracket notation. Round bracket A comma B is a set of all real numbers x such that A is less than x, which is less than B. Now you can have mixtures of rounded square brackets. For example, I could include A, which I'll indicate with a dot, but I could exclude B, which I'll include with a little circle, and then include all the numbers in between. Okay, using interval notation, this is denoted by square bracket A, comma, B round bracket, and that's all the real numbers, such that A is less than or equal to X, which is less than B. Another possibility is that put a little circle around A and a dot at B and then include everything in between. And that's captured with round bracket A, comma, B square brackets. And that's all x in R, such that A is less than X, which is less than or equal to B. Another possibility, which is in fact an example we had before, where you take some point, say B on the real line, you exclude it, and then you go on forever to the right. That's captured with round bracket B, comma, infinity round bracket. So that's all x in R, such that X is greater than B. If we wanted to include B, then we'd use square bracket notation, square brackets B infinity, that's all x in R, such that X is greater than or equal to B. There's a similar notation to the left, but we use minus infinity. So we could take some point A, we could exclude it or include it, and move infinitely to the left. Okay, in the first case where we exclude A, we use the notation round bracket minus infinity, indicating moving indefinitely to the left, comma A, round bracket to exclude A, that's all x in R, such that X is less than A. Or if we want to include A, we have the square bracket notation, or round bracket negative infinity, comma A, square brackets to include A, that's x in R, such that X is less than or equal to A. Okay. There's one other case. Okay, what happens if we want to include all real numbers? Well, of course, we get the whole real line, denoted by R. Using interval notation, that's round bracket negative infinity, comma, infinity round brackets. Okay, let's just apply, we'll finish by applying interval notation to one of the sign diagrams. Okay, remember that we had this sign diagram for the expression x plus 1 times x minus 3, and we can read off information and express it using interval notation. For example, we could look at this collection of real numbers x such that this expression is negative. Okay, so on the sign diagram, that's all the x between, but not including minus 1 and 3. So in interval notation, that's denoted by minus 1, comma 3. If we look at all the real numbers x, for which the expression is positive, then that comes in two pieces. All the numbers bigger than 3 or less than minus 1. And we capture that using two intervals. All the numbers to the left of minus 1 is captured by round bracket minus infinity, comma, minus 1. All the numbers to the right of 3 is captured by the interval notation 3, comma, infinity with round brackets. And then we glue them together using what's called a union symbol. When you use the union symbol, then you pull together all the elements in the two sets that are involved. There's a lot of material to digest in just a few minutes, especially if you've never seen the notation or never heard any of this terminology before. Please carefully read and digest the notes accompanying this video, and then, when you're ready, please attempt the exercises. We look forward to seeing you again soon. In the first half of this video, we briefly introduce X and Y axes that form the Cartesian XY plane and discuss coordinates of points with respect to the axes. The Cartesian plane is an incredibly useful device for using mathematics to analyse phenomena that occur in two-dimensional spatial settings. We go further in the second half of this video and introduce a third Z-axis that allows us to model phenomena in three-dimensional spatial settings. You might have heard the expression thinking outside the square or thinking outside the box, or maybe the term lateral thinking, originally due to Edward de Bono, all of which are synonymous with creative or novel ways of thinking or viewing ideas or problems, utilising a completely new or different perspective. The 17th century mathematician philosopher René Descartes was one of the most original thinkers in the history of mathematics. He literally thought laterally in many ways, and in particular to discover his remarkable invention, the Cartesian plane, the topic of this video. In Latin, his name was Renatus Cartesius, from which the adjective Cartesian is derived. We've discussed the real line in previous videos. Descartes imagined not just one, but two real lines, positioned in space so that they intersect at zero and are mutually perpendicular. What could be more lateral than that? The real line from left to right he called the x-axis. The real line up and down he called the y-axis. Think of the x-axis as horizontal and the y-axis as vertical. Notice how the axes are perpendicular to each other. The intersection point is called the origin, which we denote by O. O for origin and O also for 0. This is a special case of the following. Take any point at all on this diagram. We'll call this point P, and move down to the closest point on the x-axis, say A, and move across to the closest point on the y-axis, say B. Then the pair A, B forms what's called the coordinates of P. If you imagine this diagram extending infinitely to the right and left and up and down, you get what's called the Cartesian plane or the XY plane. Let's practice with some real points. So here's a copy of the XY plane with some points marked on the axes. And here are 3 points that we want to plot, P, Q and R. The point P has coordinates 2, 1. The point Q has coordinates 6, 4. And the point R has coordinates 6, 1. And you can see that they form the vertices of a right-angled triangle. You could ask, for example, for the length of the hypotenuse, h, say, and then use the theorem of Pythagoras. Remember, the square of the hypotenuse is the sum of the squares of the other sides of the right-angled triangle. As we move from P to R, we go from 2 to 6 on the x-axis, that's 4 units. As we go from R to Q, we move from 1 to 4 on the y-axis, that's 3 units. So the sum of the squares of the two sides of the triangle are 4 squared plus 3 squared, which is 5 squared. So h is equal to 5. This calculation is a special case of a more general result. If we have points P and Q in the xy plane, then the distance d between them is given by this formula. D is just the square root of the sum of the squares of the differences of the coordinates. The formula for D comes about, as before, by finding a right-angled triangle in the plane and using the theorem of Pythagoras. Now, we don't live in a flat world, we live in 3 dimensions, so you could ask, can we adapt Descartes' lateral thinking to include a third copy of the real line? Yes, we can think of the xy plane now as horizontal, like a tabletop in your kitchen or your dining room. And then we take a new copy of the real line, which we call the z-axis, that emanates out of the tabletop and moves up and down vertically. Again, we denote the origin by a big O, but now we have 3 zeros. So how do we model points in space? Here are the axes again, and I've got some point P suspended in space. Imagine it's sort of hovering over the tabletop, which is the XY plane. We drop down from P till we hit the XY plane at, say, the point Q. We move across to the X and Y axes at the points, say, A and B. And we can move directly across horizontally to the Z-axis at some point, say, C. These numbers A, B and C form what's called the coordinates of P. Notice that the coordinates of Q are A, B and 0. Then we can ask, for example, what's the distance from P to the origin O? Call this distance D, say. Can you see Pythagoras lurking? The triangle OPQ is in fact a right-angled triangle. With hypotenuse D, one of the shorter side lengths is this vertical length C. The horizontal length we'll call H, say. But H is itself the hypotenuse of another right-angled triangle formed by O, Q, and the point A on the x-axis. The shorter side lengths of this triangle are A and B. So if we apply Pythagoras to that triangle that I've shaded grey that's lying horizontally, we get that h squared is a squared plus b squared. But if we apply Pythagoras to the other triangle, we see that d squared is h squared plus c squared, which is just a squared plus b squared plus c squared. And so we conclude that d is the square root of the sum of the squares of the coordinates of P. Thus we have the following result, that the distance from a point in space to the origin is just the square root of the sum of the squares of the coordinates. And this works regardless of whether the coordinates are positive, negative or 0. In the diagram I had everything so that the coordinates were positive, but the mathematics still works. Let's look at an example. Do you remember the unit square with side lengths 1 and diagonal the square root of 2? What if we were to consider a unit cube where the side lengths are all 1? Here's an example of a cube, and we can imagine all the side lengths are 1. And then we can ask, what's the length of the diagonal of the cube? That is, the distance from one corner to the opposite corner. Of course you can figure it out directly, but let's put it in the context of our discussion of coordinates of points in space. Let's position the cube so that the point furthest away is at the origin, and then the point closest to us has coordinates 1, 1, 1 because it's the unit cube. Call that point P, and then by our formula, the distance from P to the origin is just the square root of the sum of the coordinates. If we draw in the diagonal, D, then D is the square root of 3. The theorem of Pythagoras is ubiquitous in mathematics because it describes the length of the hypotenuse as the square root of the sum of two numbers. You expect to see square root signs a lot. Remember, expressions using square root signs are called surds. So we'll see a lot of surd expressions in this course, and indeed in any course on calculus. We've covered a lot in just a few minutes. Please read and digest the notes accompanying this video. When you're ready, please attempt the exercises, and we look forward to seeing you again soon. In the last video, we calculated some distances between points in the XY plane, and even ventured into distances in space using the theorem of Pythagoras applied to certain right-angled triangles. In this video, I'd like to step back a little and just consider distances in the real line. In the last video, all the diagrams used positive numbers or 0 implicitly. Now I'd like to introduce an apparatus for dealing carefully with all numbers, whether they're positive, negative, 0, or mixtures of positive, negative, and 0. We'll look at the notion of absolute value or magnitude of a real number and some important related techniques. Absolute value or magnitude captures precisely the notion of distance along the real line. Let x be a real number. Define the absolute value or magnitude of x to be this symbolism with x inside two vertical lines, and that's equal to x if x is greater than or equal to 0, or minus x if x is less than 0. And this is just the distance between x and 0 on the real line. Well, how could that be? Well, here's the real line with 0 in the middle. If x is greater than 0, then the distance between x and 0 is just x itself, which matches the formula for the absolute value of x. If x is less than 0, then the distance is minus x. Remember, x is negative, so minus x becomes positive, again matching the formula for the absolute value of x. If x happens to be 0, then the distance, of course, is 0, which is, by definition, the absolute value of 0. For example, 1 and minus 1 are both 1 unit distant from 0, so their absolute value is 1. 2 and minus 2 are both distant 2 from 0, so their absolute value is 2. 1.5 and minus 1.5 are both 3 on 2 units from 0, so the absolute value is 3 on 2. And of course, as we've observed, the absolute value of 0, the same as minus 0, is 0. It's an important and useful fact that the distance between two numbers is the absolute value of their difference, and it doesn't matter which order you take the difference. For example, if x is greater than y, so x appears to the right of y on the number line, then the distance between them is just x minus y, and that's the absolute value of x minus y because it's positive. If x is less than y, then the distance between them now is y minus x, which is the negative of x minus y, and that's by definition the absolute value of x minus y. And in the final case, if x equals y, then the distance between x and y is 0, and that's just the absolute value of x minus y. For example, the distance from 2 to 4 is just the absolute value of their difference, which is 2. And you can see this on the real line. If you draw the point 2 and 4 on the real line, you can see that the distance really is 2 units. On the other hand, if we look at the distance between, say, minus 2 and 4, that's the absolute value of the difference, which turns out to be 6. And you can see that directly on the real line. The distance between the two numbers turns out to be 6. Right. Here's some practice for you. I want you to solve the following equation. That is, I want you to find all x distant exactly 3 units from 2. Okay, so here's the solution. Let's draw the line and locate some points. In particular, let's locate the number 2 and look for all the points that are distant exactly 3 units from 2. In fact, there's 2 possibilities, whether you move to the right or the left. If you move to the right, you find the number 5. And if you move to the left, you find the number minus 1. And so the solution set just consists of the two numbers minus 1 and 5. Let's vary the previous exercise by turning the equation into an inequality. Let's replace equals by greater than. Okay, let's solve it. Here's the diagram from the previous solution where we had equals, but now because we've got greater than, neither minus 1 nor 5 are solutions. So we want to exclude them, so we'll draw little circles around them. Now we want the distance to 2 to be more than 3, so we'll move further away from 2, either to the right or to the left. And then we can read off the solution set. It's just a union of 2 intervals. One interval extends indefinitely to the left from minus 1, but not including minus 1. And the other interval extends indefinitely to the right from 5, but not including 5. And we put those 2 intervals together with a union symbol. Wherever you can, it's best to use the geometric approach to solving such problems. Sometimes it's not easy or even possible to interpret the information geometrically, and then it's important to have strong technique and be able to fall back on algebraic methods. Several illustrations are given in the notes that accompany this video. Please read and digest the notes carefully. When you're ready, please attempt the exercises. And I look forward to seeing you again soon. In this video, we discuss and illustrate lines and circles in the Cartesian plane and their associated equations. Now, why lines and circles? Well, they're amongst the most fundamental classical objects in geometry, and they turn out to be of fundamental importance in calculus. Lines involve simple arithmetic. But isn't calculus meant to be complicated? No. Calculus is the art of thinking deeply about simple things. And lines are those simple things we need. As you will see, lines are the core business of calculus, which aims to reduce complicated processes to simple arithmetic. What about circles? Well, they model repetitive or periodic behaviour. You've heard the expression going around in circles, which sounds like you're not getting anywhere. Well, repeated patterns are part of our life. Think of day and night, the tides, the seasons, your heartbeat. Where would we be without our hearts beating? The mathematics of circles is fundamental to understanding phenomena that repeat indefinitely. Let's begin with lines in the plane. They have general equations in the form ax plus by equals c, where x and y are variables, and a, b, c are constants. You may be familiar with other forms, but this one is probably the most used by mathematicians because it can be easily generalized, as I might explain later. For example, let's sketch the line 2x plus 3y equals 6, where a is equal to 2, b is equal to 3, and c is equal to 6. And here's a copy of the xy plane. If we can find 2 points on the line, then we just need to join them up. And it's simplest to look for points on the axes. When x is equal to 0, the equation becomes 3y equals 6, so y is equal to 2, so the y-intercept is 2. And we can mark off 2 on the y-axis. Now, when y is equal to 0, the equation becomes 2x is equal to 6, so x is equal to 3, and we can mark off 3 on the x-axis, and then join the points to create a line. Now, we've just used the general principle that a line is determined by 2 points. In general, call these points, say, P and Q, and draw a line between them. Notice that we have horizontal and vertical directions in the xy plane, and this leads to the notion of slope, which is the fraction or proportion obtained by dividing the vertical rise by the horizontal run, typically denoted by m. Now, if the horizontal run is just 1 unit, then we're dividing by 1, so the fraction becomes the vertical rise. In other words, we move m units vertically for each unit we move horizontally. And it turns out there's a nice formula for m in terms of the coordinates of P and Q. Here are P and Q again, but now with coordinates, say, x1, y1 for P, and x2, y2 for Q. And I've added a little right-angled triangle with horizontal side length 1 and vertical side length m. Now let's build a larger right-angled triangle that captures movement from P to Q, but resolved into horizontal and vertical components. The horizontal run is just x2 minus x1 in this diagram, whereas the vertical rise is y2 minus y1. Can you see 2 similar right-angled triangles? Because the 2 triangles that we've highlighted are similar, the ratios of yellow to green are the same. For the smaller triangle, this is m divided by 1. For the larger triangle, this is y2 minus y1 divided by x2 minus x1. Thus, we've established that the slope m is the ratio of the differences in the coordinates, and we get this nice formula. And it doesn't matter if you reverse the roles of P and Q, as the ratio stays the same, as negatives cancel in the numerator and denominator. So, for example, what's the slope of the line joining P and Q with coordinates 2, 2 and 5, 6? We can just apply the formula to get m equal to 6 minus 2 divided by 5 minus 2, which is 4 over 3. Or if you reverse the order of the points, you get m is 2 minus 6 on 2 minus 5, that's minus 4 on minus 3, which still evaluates to 4/3. How might we visualize this? Here's a copy of the xy plane, and add the points P and Q, and draw a line between them. As you move from P to Q, you can see that the horizontal run is 3 units. And the vertical rise is 4 units, so the slope is 4/3, a bit more than 1. So the angle of inclination is a bit more than 45 degrees, and we'll have a lot more to say about angles in the next module. Now lines can have positive, negative or zero slope, depending on whether the line slopes upwards, downwards, or are horizontal as you move from left to right. Actually, there's one more possibility, infinite slope, where you don't move at all left or right, which we'll come to shortly. Here's some more practice with points P and Q with mixtures of positive and negative coordinates. Applying the formula for the slope, we quickly get that m is equal to -1. And visually, you can see that when we join the points, the line slopes downward with slope -1. 1 unit downwards vertically for 1 unit horizontally from left to right. And this is very clear, say moving from the y-intercept to the x-intercept. But how do we find the equation of a line? Well, the general form ax plus by equals c can be transformed in a few steps into the form y equals mx plus k, where m is equal to minus a on b and k is equal to c on b, provided the constant b is non-zero. M is our old friend the slope, and k turns out to be the y-intercept where x is equal to 0. The line passes through the y-axis at y equals k and moves m units vertically for each unit moved horizontally. Here's some practice. Find the equation of the line passing through P and Q with coordinates 2, 3 and 7, 13. To solve this, we must first find the slope m and quickly see that it evaluates to 2. So the equation must be of the form 2x plus k for some k. We can find k by subbing in coordinates of one of the points, say P, and you'll quickly find that k is equal to -1. Thus the equation is y equals 2x minus 1. And you can quickly check that this works, for P of course, but also as a double check for Q. And here is the graph passing through the y-axis at -1, and as you move 1 unit across to the right, the line moves up 2 units vertically. Warning, some lines are vertical, so have what you might think of as an infinite slope, and do not have the form y equals mx plus k. In our derivation of y equals mx plus k before, we assumed that b is not equal to 0. So what happens if b is equal to 0? The equation becomes ax equals c. And now dividing by a, we get that x is equal to, say, L, where L is the constant c divided by a. Note that if a and b are both equal to 0, then c is equal to 0, and the equation is degenerate and not very interesting. So assuming b is equal to 0 forces a to be non-zero. And here is what the vertical line x equals L looks like, passing through the x-axis at L. So why do we emphasize the general form ax plus by equals c? The reason is that it generalizes. Remember how Descartes went from 1 to 2 to 3 copies of the real line forming axes? If we add a third variable, say z, then there is a natural pattern, and the new equation should become ax plus by plus cz equals d, where now a, b, c and d are constants. Now your first guess might be that this is the equation of a line in space. But in fact, it is the equation of a two-dimensional plane in space. Like the walls, floor, or ceiling in your room. Each is a plane in space described by an equation like that. Why 2 dimensions? Though there are 3 variables, x, y and z, the equation places a constraint. so that after choosing any two of the variables independently, the third is completely determined by the equation and algebraic manipulation. We say that there are 2 degrees of freedom. Why stop at 3 variables? Well, further generalizations are mentioned in the notes if you're interested, and you'll become very familiar with higher dimensions if you do more mathematics. Returning to the XY plane, let's discuss circles and how to describe them. This is where Pythagoras comes in. Consider a circle centered at P with radius r. What should its equation look like? Well, let Q be a typical point on the circle with coordinates, say, x and y, and you can imagine Q spinning around the circle. We want to understand the relationships between x, y, a, b, and r. So we form a right-angled triangle involving P and Q using horizontal and vertical side lengths. In this diagram, the horizontal side length is x minus a, and the vertical side length is y minus b. By Pythagoras, the square of the hypotenuse is the sum of the squares of the sides of the triangle. So r squared is x minus a squared plus y minus b squared. And that gives us the equation of the circle. Though we usually write it round the other way with r squared on the right. Let's do an example. Say the circle C centered at P with coordinates 3, 4 and radius 5 units. We can simply read off the equation where a is equal to 3, b is equal to 4 and r is equal to 5. And you could ask various questions like whether the circle crosses the axes, and if so, where. Let's look at the y-axis where x is equal to 0. So what does this imply? Well, the equation simplifies, and in several steps you see that y is equal to 0 or 8. So there are 2 answers, points on the y-axis with coordinates 0, 0 and 0, 8. Now what about crossing the x-axis, where y is equal to 0? Again, the equation simplifies, and in a few steps we see that x is equal to 0 or x is equal to 6. So the points on the x-axis have coordinates 0, 0 and 6, 0. Notice that the origin, the intersection of the x and y axes, appears both times. And here the picture tells the full story for this particular circle. We chose this example so that the numbers fall out easily, in fact using a 3, 4, 5 right-angled triangle. But in principle you can use the equation of a circle to find out lots of information regardless of what the constants are. And typically these calculations involve square roots. We've covered a lot of ground: equations of lines and circles, gradients and intercepts with axes, and an application to circles of the theorem of Pythagoras. The important idea is that the geometry of lines and circles can be captured algebraically by these equations. Please read the notes, and when you're ready, please attempt the exercises. Now, this is the last video in the first module, and you may want to review ideas and techniques introduced so far. Let's see. We've talked about the real number line and decimal expansions, the theorem of Pythagoras in an historical context, and properties of the square root of 2. We've talked about surd expressions and some novel applications of algebraic manipulation, finding solutions to equations and inequalities, where we've exploited sign diagrams and interval notation. We've discussed coordinate systems, in particular Descartes' wonderful invention of the XY plane, distance and absolute value, and now today lines and circles in the plane. Thank you very much for your participation, and I look forward to seeing you again soon. Welcome back. You've just completed the first module, which set the stage and gave you lots of practice with real numbers and algebraic manipulation, especially in the context of equations, inequalities, approximations, and the theorem of Pythagoras. You also developed fluency with the Cartesian XY plane and started to think about the way we can visualize relationships between quantities. This next module is a natural progression, where we formally introduce the notion of a function that unifies the mathematics by capturing precisely ways in which we link together different quantities or measurements. Functions use precise rules and processes. You'll gain insight and an understanding of their myriad effects and subtleties by graphing them in the XY plane. Over a succession of videos, we'll develop an extensive repertoire, including quadratic, cubic, and general power and polynomial functions, exponential and logarithmic functions associated with exponential growth and decay, and trigonometric functions related to the mathematics of periodic behaviour. You'll also learn how to create new functions using composition and inversion, and discover tricks for moving backwards and forwards between quantities algebraically, but also visually by thinking about what happens by transformations in the XY plane. We hope that you'll find the material interesting and stimulating, that you find the videos helpful, and the practice and challenges provided by the many exercises beneficial. I look forward very much to your continued attention and participation. In this video, we introduce quadratic expressions and illustrate how they can be understood visually and geometrically using a fundamental class of curves known as parabolas. Recall from the last module that we discussed equations of lines, one of the main forms of which is the slope-intercept equation, which has the form y equals mx plus k, where m is the slope and k is the y-intercept. The combination of symbols on the right-hand side, mx plus k, is called a linear expression, and it is formed with just one multiplication and one addition, which, when you think about it, is very rudimentary arithmetic, which is the whole point of equations of lines. They are intended to be simple and easy to handle. Let's gradually increase the complexity by adding a further term involving the square of x, and another constant, so there are three constants, renamed alphabetically A, B, and C, to get what is called a quadratic expression of the general form y equals ax squared plus bx plus c. Remember, A, B, C are constants and x, y are variables. To be what we might call a proper quadratic, we want A to be non-zero, for otherwise the expression reverts to just bx plus c, the linear case which we've already considered. You might be curious, the prefix quad in quadratic comes about because there are four sides to a square, and x squared, of course, represents the area of a square of side length x. Indeed, the simplest case is just y equals x squared, when a is equal to 1 and b and c are both equal to 0. What might the relationship look like between x and y equals x squared when we consider or plot points in the xy plane? Let's look at some simple values. When x equals 0, then y is 0 squared, which equals 0. So we get the point 0, 0, which is just the origin. When x equals 1, we get y equals 1 squared equal to 1, so we get the point 1, 1. When x equals minus 1, we get the same square value plus 1, and now the point minus 1, 1. When x equals 2 or minus 2, we get the same square value plus 4. So we get the points 2, 4 and minus 2, 4. We can plot these 5 points on the Cartesian xy plane and join the points using a smooth curve. What we've produced is another very important curve in the history and development of mathematics, known as a parabola. Let's look at some variations. The simplest example, which we've just discussed, arises when a equals 1, b equals c equals 0. If we take a equals 1 and b equals 0 again, but take c equal to 2, we get y equals x squared plus 2. For another variation, we could take a equals 1, b equals 4, and c equals 4 to get y equals x squared plus 4x plus 4. Let's sample some points xy for each of these curves, where the values we input for x are 0, 1, -1, 2, and -2. Here are the 5 points that we obtained earlier for y equals x squared. And now points for y equals x squared plus 2. You can quickly check by adding 2 to the y values in the previous list. And also points for y equals x squared plus 4x plus 4. The values for the third example might look haphazard. But let's see what actually happens when we plot the points on the xy plane in each case and join the points with smooth curves. Here's the parabola for y equals x squared that we found before. The second quadratic, y equals x squared plus 2, simply shifts these y values upwards by 2 units. And so the curve joining these new points is just the original parabola shifted upwards by 2 units. To plot the 5 points for the third quadratic, we need some extra room, which we get by halving the scale on the x and y axes from the diagrams we used before. And you can easily check that we also get these other points when x equals -3, -4, -5, and -6. And then join up the points with a smooth curve, which again turns out to be a parabola. If you include the original parabola for y equals x squared, that's the blue curve, on the same diagram, you discover that the pink curve is obtained by shifting the blue curve uniformly 2 units to the left. Now, how can that be? The rules for the quadratics look so different. Observe that, in fact, x squared plus 4x plus 4 is a perfect square, in the sense that it is the square of x plus 2, which is really just x squared with x replaced by x plus 2. So that to get the y values for the pink curve, all one needs to do is input x values that are 2 units less than those feeding into the blue curve. And the shifting phenomenon is explained. In fact, every curve described by the general quadratic y equals ax squared plus bx plus c is a parabola, and just the result of dilation and shifting up and down, or back and forth, the simplest parabola associated with y equals x squared. This completely general fact is not obvious, but is explained carefully in the notes, together with some principles regarding dilations and shifts of general curves in the xy plane. If the constant a in the quadratic expression happens to be negative, then the dilation effect includes also flipping the parabola upside down. Or we often say by reflecting in the x-axis. For example, consider the parabola for y equals -x squared, where a is equal to -1 and b and c are both 0, and we get an upside down parabola. In fact, the result of reflecting the parabola for y equals x squared in the horizontal x-axis, bowl shape up becomes bowl shape down using any horizontal reflection. Notice that the apex of the parabola is at the origin. The apex turns out to be important for applications. Here's a trickier one, y equals 2x minus x squared, just rearranged slightly to emphasize the minus x squared term, and we know it must yield an upside down parabola because of the minus sign. But where does the parabola lie on the xy plane? Let's do some algebraic manipulation. First write y as the negative of x squared minus 2x, all in brackets. Then use the technique of completing the square by adding and subtracting 1 inside the brackets, as this doesn't change the overall value of the expression. Bring the -1 outside the brackets as +1, and then recognize the bracketed expression as the perfect square x minus 1 squared. So finally, we've written y as -x minus 1 all squared plus 1. To understand the curve, because of what we've just done, we can relate this in a natural way to the simplest upside-down parabola of all. Start with minus x squared, replace x by x minus 1, and then add 1, and you recover the expression minus x minus 1 all squared plus 1. You can see the visual geometric effect of these two algebraic steps. Start off with the upside-down parabola, y equals minus x squared. Take a copy of the parabola and watch the effect of shifting 1 unit to the right, corresponding algebraically to replacing x by x minus 1, followed by moving 1 unit vertically upwards, corresponding algebraically to adding plus 1. You can see that we recover the pink parabola from the green one. Notice how the apex of the green curve is at the origin, 0, 0, and this is shifted to the point 1, 1, which becomes the apex of the pink curve. Notice also how the pink curve crosses the x-axis at x equals 0 and x equals 2. This makes perfectly good sense, since this occurs when y is equal to 0. If we go back to the original expression, instead of completing the square, if we put y equal to 0, then we get a factorization of 0 in just one step, x times 2 minus x. And remember, in an earlier video, we said that a factorization of 0 is very useful, leading to x equals 0 or x equals 2, where the curve crosses the x-axis. There are lots of different ways of looking at these curves. With experience, you would realize that one of the fastest ways to visualize examples like the parabola y equals 2x minus x squared is to recognize that it's upside down, as the coefficient of x squared is negative, and crosses the x-axis at values dictated by a factorization of 0. There is much more that can be said about parabolas, especially about the apex, the point where it turns around. To get a more complete story, we'll introduce and discuss the quadratic formula in the next video. We've made a good beginning here and covered a lot of ground. We've introduced general quadratic expressions, shown how they correspond to important curves known as parabolas, and illustrated how different parabolas relate to each other, especially by shifting and turning things upside down by reflecting in the x-axis. Please read the notes, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. In this video, we'll discuss the quadratic formula, which enables you to solve any quadratic equation. We'll explain how this formula comes about by a trick you've already seen from examples in earlier videos called completing the square. We begin with a quadratic equation that looks rather innocent, but turns out to be linked to some very important and famous ideas that go even beyond mathematics, as I'll explain later. It's not obvious how to factorise the left-hand side, so we'll look for some trick for isolating x using algebraic manipulation. Notice that the coefficient of x is minus 1, and that turns out to be important. We begin by adding 1 to both sides of the equation, a first step towards isolating x. Then we add the square of minus 1/2, that is, the square of half of the coefficient of x. And then the left-hand side becomes a square of x minus 1/2, whilst the right-hand side simplifies to 5/4. In developing the left-hand side, you can now see the reason for adding the square of minus 1/2. We're exploiting the algebraic identity x plus k all squared equals x squared plus 2xk plus k squared, where in our case k equals minus 1/2, and then 2k is just minus 1, the coefficient of x in the original quadratic equation. So we have x minus 1/2 squared is equal to 5/4, where x appears only once, whereas in the original equation, x appears twice. We can now unravel the left-hand side in a couple of steps, first taking positive and negative square roots, and then adding 1/2 to both sides, and we can rewrite this as 1 plus or minus the square root of 5 all over 2. And that solves the equation. Let's adapt the idea of the previous example to solve a general quadratic equation ax squared plus bx plus c equals 0. We begin by taking c away from both sides, and it turns out to be convenient to divide through by a so that the coefficient of x squared is 1. And we'll just rewrite the left-hand side to emphasise that the coefficient of x is b on a. And continuing, half of the coefficient of x is b on 2a, so we add the square of this to both sides, and then the left-hand side becomes a perfect square. In fact, x plus b on 2a all squared, and the right-hand side tidies up to become b squared minus 4ac on 4a squared. So we have an equation now in which x appears only once. We just have to unravel the left-hand side by taking plus or minus the square root of the right-hand side, which can be rewritten as plus or minus the square root of b squared minus 4ac over the square root of 4a squared. And notice that the denominator can be taken to be 2a, because the square root of 4 is 2, of course, and the square root of a squared is either a if a is positive, or minus a if a is negative. But in that case, the minus sign can be absorbed in the plus or minus in the numerator. So continuing, we take b on 2a away from both sides of the equation, and rewrite this as a single fraction with 2a in the denominator. And what we get finally is known as the quadratic formula. Notice that the formula on the right-hand side is a surd expression involving a square root sign, and it only makes sense if the contents of the square root sign become non-negative, that is, positive or 0, as we're not allowed to take square roots of negative numbers in the real number system. Thus we require that b squared minus 4ac is greater than or equal to 0. Now, in higher mathematics, you'll learn about complex numbers, in which it is possible to consider square roots of negative numbers, and then the quadratic formula makes sense even if b squared minus 4ac is negative. This turns out to be very useful and powerful, but you don't need to worry about that for now, as techniques involving complex numbers go beyond the scope of this course. It's always good, when you discover or develop a general formula, to check it out on some particular or easier cases, where you already know the answer, or can find the answers easily by other means. Let's revisit the equation we solved before by ad hoc means, but now by applying the quadratic formula, where a equals 1 and b and c are equal to minus 1. Then x is negative b, plus or minus the square root of b squared minus 4ac all over 2a, which quickly simplifies, in this case, to 1 plus or minus the square root of 5 all over 2. Which is what we came up with before, which is very pleasing. Let's try another example, which we can easily solve by factorization, noticing by inspection that the left-hand side factorizes as x plus 6 times x minus 2, so that x plus 6 equals 0, or x minus 2 equals 0, yielding x equals minus 6, or x equals 2. Now, instead, let's apply the quadratic formula. So x is minus 4, plus or minus the square root of 4 squared minus 4 times minus 12, all over 2, which in a couple of steps becomes minus 4 plus or minus 8 all over 2, which simplifies to minus 2 plus or minus 4, yielding x equals 2, or x equals minus 6, which agree with the solutions we obtained by the factorization method, which is also very pleasing. Let's go back to the very first quadratic equation that we looked at today, in fact related to something known as the golden ratio, which is an important proportion traditionally used by artists in selecting a blank canvas. The associated rectangle has the property that when you remove the square formed by the shorter side, what's left over, coloured blue in this diagram, is another rectangle, but in the same proportion as the original, though the smaller rectangle is now standing upright on its shorter side. Notice that this is not the same as when we studied the A series of paper in an earlier video, where all you have to do is divide the rectangle in half to get two similar rectangles. The golden ratio is a fraction formed by dividing the longer side length by the shorter side length. So let's call the longer side length of the original rectangle A and the shorter side length B. The square that we're taking away has side lengths B and the blue rectangle remains, now having longer side length B and shorter side length A minus B. Let's give the golden ratio a name, say capital X, which is the unknown quantity that we want to find. So X equals A on B from the larger rectangle, and also B on A minus B from the smaller rectangle. Dividing the top and the bottom by B, we get 1 over A on B minus 1, which is just 1 over X minus 1. How do we find X? Well, in a couple of steps, we can transform this into a quadratic equation. First by multiplying both sides by X minus 1, expanding the left-hand side, and then subtracting 1 from both sides. But this is just the equation we started with in our first example, with capital X instead of small x. And the complete solution gives two answers, 1 plus or minus root 5 over 2. But the solution involving the minus sign, 1 minus root 5 over 2, is negative. And of course, the golden ratio has to be positive, so it must be 1 plus root 5 over 2. And we can type this into a calculator and start to write out its decimal expansion. And because root 5 appears, this number turns out to be irrational, so the decimal expansion is not recurring. Do you remember in an earlier video we played with continued fractions when exploring properties of the square root of 2, with something that resembled a packet of oats that kept referring to itself ad infinitum? Well, we can play similar games with the golden ratio. It has an expansion that begins with 1 plus, 1 over 1 plus, 1 over 1 plus, 1 over 1 plus, and the nested pattern keeps going forever. It's a very elegant expansion and only uses the number 1. In a certain sense, the simplest, non-trivial continued fraction that you can imagine. The golden ratio is also known as the divine proportion and is celebrated in the art world. For example, Leonardo da Vinci's Mona Lisa, one of the most famous paintings of all time, has a divine proportion appearing in all sorts of different ways throughout the painting. Leonardo da Vinci was a scientist as well as an artist and was expert at reproducing anatomical proportions exactly as they appear in nature. When you're aware of the divine proportion, you will start to see it everywhere. The reason it occurs so naturally is related to something called the Fibonacci sequence, which plays a central role in mathematics and theories of computation. And you can learn more about these topics if you continue with mathematics beyond this course. We've covered a lot of ground today. We've established the quadratic formula, which can be used to solve any quadratic equation, explained where it comes from, using the technique of completing the square, and checked it out on some examples, including one of the most famous applications of a quadratic equation, namely finding a surd expression for the golden ratio. There are more details in the notes. Please read and digest them, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. In this video, we'll introduce and discuss functions, which are formal mathematical devices for capturing precisely the relationships that occur or might occur, especially if you're making predictions, between quantities or measurements. Functions typically involve formulae built up in a variety of ways and may only make sense for certain numbers, leading to the notion of the domain. Only certain values might be created, leading to the notion of the range. The Cartesian plane helps us visualize relationships using what we call formally the graph of a function, which provides a powerful pictorial representation that gives great insight. You'll quickly become expert at creating or sketching graphs of functions, even just in your mind's eye. So let's get started with the fundamental idea of a function. A function f is a rule or process that takes an input, typically a real number x, and produces an output, also typically a real number denoted by f of x. If it helps, you can think of the function f as a factory for processing or crunching numbers. We feed in an input, say x, and set the process in motion. And the function f transforms x into the output f of x. And we can do this as many times as we like, with as many different numbers x as we like, processing them and churning out lots of outputs. We have an arrow notation with x and an arrow with a little stick at the left-hand end pointing to f of x, and we say f takes x to f of x, and it's typical to call the output y. We also call the input x the independent variable, and the output y the dependent variable, and it's common to write y equals f of x so that the independent and dependent variables are linked by an equation. For example, consider the following rule for f, where m and k are constants. The function takes an input x, multiplies it by m, and then adds k. We call this a linear function because when you plot y equals mx plus k in the xy plane, you get a line with slope m and y-intercept k. For example, we could take m equals 2 and k equals 3, and then f of x is 2x plus 3. We could choose different constants to get a different function, say g, and another choice of constants to get another function, say h. Notice we can rewrite the rule for h as 7x minus 2 over 5, if we want, which doesn't change the value produced by the function, just changes the way we describe it algebraically. Here's some practice evaluating the rules of these functions. For example, f of 0 means input 0 for x, and you output 2 times 0 plus 3 equals 3. F of 1 means input 1 for x, and you output 5. F of 6 means input 6, and you output 15. You can try this for g and h with those same inputs 0, 1 and 6 for x. So we get 1, minus 5, minus 35 for g, minus 2/5, 1, and 8 for h. We now introduce the concepts of domain and range of a function. The domain of f is the set or collection of all real numbers x that are valid inputs for the rule f of x. For example, for a linear function, the rule makes sense for all real numbers x, so the domain is the whole real line. The range of a function, by contrast, is the set of all outputs y produced by applying the rule. For example, for a linear function, provided the slope m is non-zero, it's easy to see that the range is again all of the real numbers. This becomes transparent in a moment when we discuss the graph of a function. However, if the slope is equal to 0, then the rule simplifies and y is just the constant k. In this case, no matter what input x we feed into the rule, we just output the same constant k over and over again. So the range is the set consisting of one real number, k. We also need to discuss graphs of functions. The graph of a function, f, is the set of all points xy in the Cartesian plane such that y equals f of x. The graph captures visually the relationship between the input x and the output y. For example, the graph of a linear function is, as you expect, a straight line. If the slope m is non-zero, then the line can slope upwards or downwards. And you can see from the graph that all points on the vertical y-axis become outputs for the function. That's why we observed earlier that for non-zero slope, the range becomes the whole real line. However, if the slope is 0, then the graph is a horizontal line passing through the y-axis at some constant k. And this is the only value produced by the function, which is why we observed earlier that the range is the set consisting of k in this case. Let's look at an example of a quadratic function where the rule is a quadratic expression involving the input x. Take, for example, f of x equals x squared minus 4x plus 3. If we look at some values for various inputs, we see that f of 0 is 3, and f of 1 is 0. And you can work out some other values. F of 2 is minus 1, f of 3 is 0, f of minus 1 is 8, and f of minus 2 is 15. Now the rule for this function, indeed any quadratic function, makes sense again for all real inputs x, so the domain is all of the real line. But what's the range? The answer is not at all obvious. Let's try rewriting the rule in a different form by completing the square. The coefficient of x is minus 4, and half of minus 4 is minus 2, so we add and subtract minus 2 squared, just before the plus 3, without changing the overall value of the left-hand side. We then combine the plus 4 with the first two terms to get x squared minus 4x plus 4, which is a perfect square, and the minus 4 with the plus 3 at the end. And the left-hand side becomes x minus 2 all squared minus 1. And so we're able to rewrite f of x in a very useful form. But x minus 2 all squared is always greater than or equal to 0. That's true for the square of any number. So f of x, which is 1 less, is always greater than or equal to minus 1. It follows that the range must be the interval of all real numbers greater than or equal to minus 1. Expressed here using interval notation. And this will be confirmed shortly by drawing the graph of f. Note, from a different point of view, we can simply factorize f of x as x minus 3 times x minus 1. So the graph must be a parabola that crosses the x-axis, that is when y is equal to 0, at x equals 3 and x equals 1. We can plot some points and join them up to get a smooth parabola. Note that the apex, the lowest point, occurs when x is equal to 2, in order to minimize y equals x minus 2 squared minus 1. In fact, with minimum value, minus 1. The domain is all of R, and the range is the interval from minus 1 to infinity. There's another important family of curves known as hyperbolas. The simplest example is the graph of the reciprocal function y equals f of x equal to 1 over x. So f of 1 is 1 over 1, which is just 1. F of 2 is just 1/2, f of 3 is a third, and so on. Notice that if you reciprocate the reciprocal, you get back to where you started. So f of a half, which is 1 over a half, is 2, f of a third is 3, and so on. F of minus 1 is just minus 1, f of minus 2 is minus a half, and f of minus a half is minus 2, and so on. But what about f of 0? In fact, it's undefined because you're not allowed to divide by 0. X equals 0 is not allowed as an input. This is the only restriction, so the domain of f is the set of all non-zero real numbers, expressed this way using set notation, and also this way using what's called slash notation, where whatever is being slashed is removed from the set. So in this case, we remove 0 from the real line and can express the domain also as the union of two intervals, putting together the positive and negative reals, avoiding 0. What does the reciprocal function produce as outputs? Well, just all non-zero real numbers. So the range, in fact, is the same as the domain in this example. Thinking about the graph, we can plot a few points, x, y, where y is the reciprocal of x, and then join the points with a smooth curve, which in fact becomes two disconnected pieces called the branches of the hyperbola. One branch where everything is positive, and another branch where everything is negative. Notice that the branches never touch the x or y axes. The branches get closer and closer to the axes as you move further and further away from the origin. The axes are called asymptotes. The x-axis is a horizontal asymptote, and the y-axis is a vertical asymptote. We've covered a lot of ground in just a few minutes. We've discussed functions, which are rules for producing outputs from inputs, the domain, the set of permissible inputs, the range, the set of outputs produced, and the graph of a function, which is a set of points x, y in the Cartesian plane where x is the input and y is the output. We illustrated these ideas using linear functions whose graphs are lines, a quadratic function whose graph is a parabola, and the reciprocal function whose graph is a hyperbola, forming two branches with the x and y axes acting as asymptotes. There are more details in the notes. Please read and digest them, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. In this video, we discuss polynomial functions, which include linear and quadratic functions as special cases, and power functions, which focus on particular powers of a variable x. Square roots and other types of roots arise as fractional powers, which may look a bit surprising if you've never seen this before. In fact, we'll start with very simple powers, and you'll see the potential to develop ideas in several directions. A power function has the form y equals x to the n, where x is the input, an independent variable which you can choose freely, n is some fixed number called an exponent to be used to form a power of x, and y equals x to the n is the output. Let's start off with the simplest cases when the exponent n is a positive integer, 1, 2, 3 and so on, and x to the n is x times x times x and so on with n occurrences of x, called the nth power of x. For example, when n equals 1, we get the so-called lazy function y equals x to the 1, which is just x, that simply returns the input as the output, without making any changes at all. This is also known as the identity function. When n equals 2, we get f of x equals x squared, the square function, which you're familiar with already. And when n equals 3, we get the cube function, so called because x times x times x is the volume of a cube of side length x. For example, 2 cubed is 8, minus 2 cubed is negative 8, a negative volume, 3 cubed is 27, and negative 3 cubed is negative 27, and so on. If we undo the nth power function, then we get what's called the nth root function, whose rule is denoted like this, with a tiny n sitting inside a root symbol. And we say y is the nth root of x. When n equals 2, this becomes the usual square root, which you can think of as undoing the square function. And when n equals 3, it becomes what we call the cube root, which you can think of as undoing the cube function. The idea of undoing functions is called inversion in mathematics, and an entire video is devoted later to formalizing the concept of an inverse function. Here are some examples of undoing: square and cube roots, and a couple of fourth roots. For example, 2 to the fourth is equal to 16. So if we undo that, we get the fourth root of 16 gets you back to 2. And 3 to the fourth is 81. So if we undo that, we get the fourth root of 81 gets you back to 3. We have a really useful notation for taking roots. The reciprocal of n as an integer is 1 over n, and for reasons that we discuss later, it's convenient to write the nth root of x as x to the 1 on n, exploiting the reciprocal of n in the exponent. Something rather extraordinary happens. Nth root functions turn out to be power functions, but using reciprocals of integers as powers. For example, the square root of 2 becomes 2 to the power of 1/2. The square root of 3 becomes 3 to the power of 1/2. 2, the square of 4 becomes 4 to the half, and also, being the cube root of 8, is 8 to the 1/3. 3 is 9 to the half, and also 27 to the 1/3, and so on. There are some important laws for manipulating fractional powers, and you'll see them in a wider context in a later video when we discuss general exponential laws. For example, the fact that the square root of a product is the product of the square roots converts into an elegant equation involving fractional powers. AB to the half is a to the half multiplied by b to the half. Similarly, we have a over b, all to the half, is a to the half divided by b to the half. For now, though, I want to return to integer powers of x and combine them in a special way to form what are called polynomials or polynomial functions. These are formed by adding together constant multiples of powers of x. Of course we have x, x squared, x cubed and so on, but we also have x to the 0th power of x, which is defined to be the constant number 1. And then we can talk about combining non-negative powers of x. A polynomial, which we typically call p of x, p for polynomial, has the form a0 plus a1x plus a2x squared plus all the way up to an x to the n, where n is an integer greater than or equal to 0, called the degree of the polynomial, and a0 up to an are real constants such that an is not equal to 0. Note that the polynomial is constructed from x and all the constants using just simple arithmetic, additions and multiplications, used even to form powers of x. The simplest cases are, for n equals 0, p of x equals a0, which is a constant. For n equals 1, p of x is a linear function. For n equals 2, p of x is a quadratic function. And for n equals 3, p of x is called a cubic function because it involves a term with x cubed. In a certain sense, polynomials are the nicest of all functions. You only need basic arithmetic to work with them. For this reason, it's a common theme in mathematics to reduce problems about arbitrary functions to polynomial functions. The key that enables all of this to work turns out to be calculus. It is very important to be able to factorise polynomials related to solving equations, and a central fact is the following. Suppose that p of x is a polynomial of degree n, and p of lambda is equal to 0 for some real number lambda, by which we mean that we end up with 0 after evaluating the polynomial expression with x replaced by lambda. The conclusion is that we can factorise p of x as x minus lambda times q of x for some polynomial q of x of degree n minus 1, which is of degree 1 less than that of p of x. This is substantial progress to be able to reduce the degree of a polynomial by means of a factorisation. The reason why this works is explained in the notes. It may look rather abstract, but it's really neat because if you know a root of the polynomial, that is, a number that causes a polynomial to evaluate to 0, then you can simplify things by factorising the polynomial. Let's look at some examples. Suppose that p of x is x squared minus 3x plus 2. Observe that p of 1 evaluates to 0. So using this fact mentioned earlier, we have that p of x is x minus 1 times q of x, where q of x has degree 2 minus 1 equal to 1, so q of x is a linear polynomial. Now by inspection, p of x is x minus 1 times x minus 2, so q of x is in fact x minus 2. But sometimes you're unable to see things by inspection, so we have another trick up our sleeves called long division of polynomials. You may not be familiar with this method, so we'll apply it carefully to this previous example. First you write x squared minus 3x plus 2 inside this long division symbol, with x minus 1 outside. The idea is to scoop out multiples of x minus 1 from what's inside the long division symbol, trying to reduce things down, ideally to make the contents vanish completely. First we write x on top. On the second line we write x copies of x minus 1, which is x squared minus x, and then take this away from x squared minus 3x plus 2. Notice when we do this, the x squared terms disappear, and what is left over is minus 3x plus 2, take away minus x, which is just minus 2x plus 2. Now we try to make this in turn simplify, so we put minus 2 on top and scoop out minus 2 copies of x minus 1, which is minus 2x plus 2, which we write on the line below. When we take this away, we're left with 0. The whole point is that p of x, our original quadratic inside the long division symbol, is just the thing on top, x minus 2 multiplied by x minus 1. So the thing on top turns out to be our q of x. And p of x equal to x minus 1 q of x just recovers the factorisation we noted earlier. Now let's do a difficult example, which is to factorise p of x given by this cubic polynomial. It's not even clear how to get started. Just for exploration, let's start evaluating P of x at some simple inputs for x. For example, you quickly see that P of 1 evaluates to minus 24, P of 2 evaluates to minus 21, and P of 3 evaluates to 0. We're lucky. We've stumbled on a root of P of x, namely x equals 3. So we can use the earlier fact that guarantees that x minus 3 is a factor of P of x. Thus we may write P of x is x minus 3 times q of x for some polynomial q of x of degree 1 less than 3, which is 2, so q of x will be a quadratic. Let's do the long division. First by writing a long division symbol with P of x inside and x minus 3 outside. Then we try to make what's inside the long division symbol vanish completely. We begin by scooping out x squared copies of x minus 3. So write x squared on top and x squared times x minus 3, which is x cubed minus 3x squared underneath. Taking this away causes the x cubed terms to vanish, and we're left with 6x squared minus 13x minus 15 at the next line. So now we try to make this simplify by writing plus 6x on top and 6x squared minus 18x on the line below. The result is scooping out 6x copies of x minus 3. Now the x squared terms vanish when we take this away from the previous line, and we get 5x minus 15. Now we write plus 5 on top and 5x minus 15 on the line below, scooping out 5 copies of x minus 3. And when we take this away, we're left with 0. That's great, because it means the polynomial on top, the quadratic x squared plus 6x plus 5, when multiplied by x minus 3, manages to scoop out all of P of x. So it becomes the q of x that we've been looking for. Thus P of x is x minus 3 times this quadratic q of x. And once we have a quadratic, we feel like we're at home, because we have methods for factorising them, either by inspection or, if necessary, by resorting to the quadratic formula. Here the quadratic factorises as x plus 5 times x plus 1, and we get a full factorisation of the original cubic into linear factors. If, for example, we needed to solve the equation P of x equals 0, then we would now have a factorisation of 0. So one of the factors has to be 0, either x minus 3, x plus 5, or x plus 1, and it's immediate that x equals 3, minus 5 or minus 1, and we can write down the solution set. Now before, we stumbled on the root 3 and then used this method involving long division of polynomials. If we'd stumbled on one of the other roots, minus 5 or minus 1, then we could have used exactly the same method but using a different linear factor in the long division. You can try that out for practice, using say x plus 5 or x plus 1 in the long division, and you should end up ultimately with the same factorisation of the cubic. We're gradually building up our repertoire of functions, useful tricks and techniques, all of which will provide us with an excellent foundation for the calculus modules that lie ahead. Today, we've introduced and discussed power functions, including notation involving fractional powers, which are really just nth roots in disguise, and polynomial functions, which are formed from power functions by adding up constant multiples of non-negative integer powers of our variable x. We've described and illustrated important techniques for factorising polynomials, in particular the method of polynomial long division. Factorisation is very important, so it's well worth investing some time in mastering these techniques. Please read the notes that accompany this video, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. In this video, we'll discuss inverse functions, what it means to invert or undo a function, how this arises by interchanging the roles of input and output, and how this relates to taking reflections in the line y equals x in the xy plane. We also explain and illustrate how to find the rule for the inverse function by algebraic manipulation. Let's begin with a familiar quadratic function, we'll call f, with rule y equals x squared, whose graph is a parabola, And next to it, we display a parabola on its side, half of which is the graph of a function we'll call g, the square root function, whose rule is y equals the square root of x. How do we know that the graph of g should also be a parabola? Well, if we put y equal to root x, then squaring both sides gives y squared equals x, that is x equals y squared. So the graph should be almost the same as for y equals x squared, except that we've interchanged the roles of x and y. I say almost the same because we only use the top half of the parabola to get the positive square root. If instead, for some reason, we wanted the negative square root, we could consider a new function, say h, with rule h of x equals negative square root of x, and get the other half of the parabola on its side. The point is that there's really these two halves of the parabola on its side that are associated with undoing the square function by taking positive and negative square roots. What's going on? Well, we have this simple but important fact about graphs of functions. They satisfy the so-called vertical line test, which means as you scan a vertical line from left to right, the vertical line never passes through the graph at more than one point. The reason is that for each potential input x from the x-axis, we want at most one output y on the y-axis. If some input x corresponded to two or more outputs, then the function would be ambiguous, and an important feature of a functional process is that it produces a single, clear, unambiguous outcome for each input. For example, the graph of the square function has this property. As we scan from left to right, vertical lines only pass through the graph once. However, for the curve x equals y squared, which is the full parabola on its side, this property fails. Except at the origin, vertical lines cross this parabola on its side at 2 points, so for every input x greater than 0, there will be two possible outputs, creating ambiguity, resolved earlier by considering just the positive or just the negative square root. And each of those halves of the parabola on its side then satisfy the vertical line test. Any circle in the plane is another example where the vertical line test fails. Take, for example, the unit circle with equation x squared plus y squared equals 1. Over the interior of the circle, all vertical lines cross at 2 points. If we rearrange the equation for the circle to get y as output in terms of x as input, we get, in a couple of steps, two possibilities for y, namely plus or minus the square root of 1 minus x squared. Having two possibilities explains why the vertical lines cross the graph twice. If we take the positive square root, we get a function whose graph is the upper semicircle. If we take the negative square root, we get a function whose graph is the lower semicircle. In each of these cases, clearly the vertical line test holds. If the graph of a function also satisfies the horizontal line test, by which we mean all horizontal lines pass through at most one point of the graph, then the function turns out to be invertible, which means we can undo the function, reverse the original process, go back from output to input. For example, the parabola y equals x squared does not satisfy the horizontal line test. The test fails for this graph. But if we restrict the domain, say to non-negative reals, that is x greater than or equal to 0, then we get the right-hand half of the parabola only, and the horizontal line test now is satisfied. This graph passes the horizontal line test. Satisfying both the horizontal and vertical line tests mean that you can move both forwards and backwards between inputs and outputs without any ambiguity. The process of unravelling the output to get back to the original input is called inverting the function. To invert a function, we need to go back from output to input, to interchange the roles of x and y, which act as input and output respectively, and therefore to interchange the roles of the horizontal x-axis and vertical y-axis, all of which is achieved visually or geometrically by reflecting the graph in the line y equals x. Here's the line y equals x, creating a diagonal in the xy plane. Reflecting in this line has the effect of interchanging horizontal and vertical, and therefore interchanging the x and y axes, which is just what we need. Let's demonstrate this physically, say with the half parabola y equals x squared for non-negative x only. Here's the graph on a transparency. To reflect in the line y equals x, we just flip it over so that the original vertical axis becomes horizontal and the horizontal axis becomes vertical. Here are the graphs all together on one diagram, and the reflected graph just on its own, which you may recognise as the positive square root function. We can do the same thing, but now with the other half of the parabola, where x is less than or equal to 0. Here is a new graph on another transparency, and again we get the reflection effect by flipping it over. Here are the graphs all together on one diagram, and the reflected graph just on its own you may recognise as the negative square root function. We have this important notation. The inverse of a function f is denoted by f to the minus 1, which is related to reciprocal notation for real numbers. It comes from composition of functions and the role of the identity function, which behaves like the real number 1 in function arithmetic, and details are given in the notes. The rules for f and its inverse are tightly held together. Y equals f of x precisely when x is f inverse applied to y. That is, if f takes x to y, then f inverse brings y back to x, and vice versa. All of these say the same thing, that f and f inverse undo each other. We can apply this notation in the cases that we looked at earlier in undoing the square function. If f of x is x squared for x greater than or equal to 0, then the rule for f inverse is to take the positive square root. By contrast, if f of x is x squared for x less than or equal to 0, then the rule for f inverse is to take the negative square root. A very beautiful example is the function h given by the rule h of x is 1 over x, whose graph is a hyperbola. The hyperbola has two branches, and the domain and the range are both the real line with 0 removed. The graph satisfies both horizontal and vertical line tests and is perfectly symmetrical about the line y equals x. So if you reflect in that line, you just get the hyperbola back again. You can see this physically by making a transparency and seeing that if you flip it over to interchange the axes, then the hyperbola will reproduce itself. So the inverse of h must be itself. Now we can check this works algebraically. H of x is h of the reciprocal of x, which is the reciprocal of the reciprocal of x, which is just x, which gets you back to the original input. So indeed, h does undo itself. Now we can create an algebraic method for undoing a function, essentially by interchanging the roles of input and output, of x and y. To invert y equals f of x, first simply rearrange the rule to express x in terms of y. And then we must have x equals f inverse of y. Typically, we denote the input by the symbol x, so finally we just rewrite this with x instead of y and y instead of x. Here's an example. Find the rule for the inverse function, f inverse, when f is given by this rather complicated rule. X goes to the square root of x plus 2 minus 1 divided by 3. To solve this, we first put y equal to the expression that gives the rule for f, and then in a sequence of easy steps, using algebraic manipulation, we unravel this to express x in terms of y. Thus x equals f inverse of y, which equals in this case 3y plus 1 all squared minus 2. So, reverting to using x as a typical input, we finally get the rule for f inverse, namely f inverse of x is 3x plus 1 all squared minus 2. And this finally solves our original problem. We can check this really works, that the rule does indeed undo the rule for f by looking at f inverse of f of an input x and carefully checking that we recover the input x. Let's quickly revisit the earlier example using the unit circle. To satisfy the vertical line test, to get the graph of a function, remember, We could, for example, take either the upper or lower hemisphere, but neither of these satisfy the horizontal line test. There are different ways of remedying this. We could, for example, restrict the domain to real numbers between 0 and 1. So we get 1/4 of the unit circle, where everything is non-negative and both the vertical and horizontal line tests are satisfied. Call the function with this graph k, so we get the rule k of x is the square root of 1 minus x squared. To find the inverse of k geometrically, we can reflect in the line y equals x. Like the hyperbola example before, this graph has perfect reflectional symmetry about this line, so the graph of the inverse function is just the graph of k. Hence k is k inverse, so the rules for k and k inverse are the same. You can also check this algebraically, though we won't do that here. We've covered a lot of ideas in just a few minutes. We've introduced and illustrated inverse functions, and along the way discussed the vertical line test, which is satisfied by all functions, the horizontal line test, which is satisfied by all invertible functions, illustrated how we can invert a function by reflecting its graph in the line y equals x, corresponding to interchanging input and output, and also how we can invert a function using algebraic manipulation. There's a lot more detail in the notes, so please read them, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. In this video, we introduce and explore exponential functions, give an example of exponential explosion, and come across another very important number in mathematics called E, Euler's number. We'll rapidly expand our repertoire of functions and move from very familiar types of numbers and operations to something sophisticated and powerful. To start with, consider any real number x and any positive integer n. Then x to the n is just x multiplied by itself with n occurrences of x appearing. So x to the 1 is just x squared is just x times x cubed is just x times x times x, and so on. So if x is some particular number, say 2, then 2 to the 1 is 2, 2 squared is 4, 2 cubed is 8, and so on. But we also have powers using 0 and negative integers. It turns out to be very convenient to define x to the 0 to be 1 and x to the minus n to be 1 over x to the n. For example, 2 to the 0 is 1, 2 to the minus 1 is 1 over 2 to the 1, which is 1/2. 2 to the minus 2 is 1 over 2 squared, which is 1/4. 2 to the minus 3 is 1 over 2 cubed, which is 1/8, and so on. We have the following exponential laws. The first says that to multiply two powers together, just add the exponents. The second says that to take a power of a power, just multiply the exponents. The third says that to divide one power by another, just subtract the second exponent from the first. And the fourth says that to multiply two powers with different bases, but the same exponent, just multiply the bases together. These should become familiar with practice and are very easy to verify when the exponents are integers. For example, 2 squared times 2 cubed is just 2 to the 5th, because 2 plus 3 occurrences is 5 occurrences of 2, and you get 32, as predicted by the first exponential law. On the other hand, 2 squared divided by 2 cubed, you can see directly, simplifies to 1/2, which is 2 to the minus 1, and the exponent -1 is just 2 minus 3, as predicted by the third exponential law. If we take 2 squared and raise it to the third power, then we have 3 lots of 2 squared multiplied together, which is multiplying 6 lots of 2, yielding 64, as predicted by the second exponential law. If you multiply 2 squared by 3 squared, the exponent 2 is fixed and the base is changed from 2 to 3. We can rearrange this as 2 lots of 2 times 3, which is 6 squared, giving 36, as predicted by the fourth exponential law. But we can go further and define fractional powers where the exponent is a fraction. Suppose that x is a positive real number and n is a positive integer. We define x to the 1 on n to be the positive nth root of x. That is, the positive number which, when raised to the nth power, gives just x. Notice now the notation is consistent with one of our exponential laws, since 1 on n multiplied by n is just 1, and x to the 1 is x. Now we can define fractional powers of x for any positive fraction. Let m and n be positive integers, so m on n is a positive fraction. Define x to the m on n to be either the nth root of x, or raised to the mth power, or alternatively, first form x to the m and then take the nth root. We end up at the same place, consistent with the exponential laws, since 1 on n times m and m times 1 on n are both just the fraction m on n. For example, 32 to the 4/5 may be taken to be the fifth root of 32, which is 2, all raised to the 4th power, giving 16. We can always define a negative power by reciprocation, that is, x to the minus alpha equals 1 over x to the alpha for all exponents alpha. We noted this before with positive integer exponents. This gives us in particular all negative fractional powers. For example, 32 to the minus 3/5 is the reciprocal of 32 to the 3/5. And we can rewrite this as 1 over 32 to the 5th all cubed, which becomes 1 over 2 cubed, which is 1/8. The exponential laws in fact hold for all positive real numbers used as bases and any exponents, and you'll get used to them in no time. For example, we calculated 32 to the negative 3/5 before using the definitions. Alternatively, you could use one of the exponential laws to write this as 32 to the 5th all to the negative 3. So this becomes 2 to the negative 3, the reciprocal of 2 cubed, which is 1/8 as before. Another example, take 81 to the 3/4. You can rewrite this as the 4th root of 81 all cubed. But 81 is 9 squared, so you get these nested powers, 9 squared all to the quarter all cubed, and use an exponential law to simplify this to get 9 to the half all cubed. But the square root of 9 is 3, so you get 3 cubed, which is 27. Here's some practice that looks tricky, and your first reaction might be to use a calculator, probably expecting messy numbers. In fact, it simplifies quickly and cleanly using exponential laws. The numerator can be rewritten as 2 times 3, all to the 2.5, using one of the laws. And 2.5 is just 5 on 2. 2 times 3 equals 6. And root 6 is just 6 to the half. And then this can all be rewritten as 6 to the 5 on 2 times 6 to the negative a half, which becomes 6 to the 5 on 2 plus negative a half, which is 6 to the 4 on 2, which is 6 squared, which is 36. We now work towards introducing exponential functions. But first recall the shape of the rule for a power function. We have a variable base, typically called x, but the exponent is fixed throughout. Now we change our point of view completely. Remember the power of lateral thinking to create what we call exponential functions. We now consider the base as fixed, a say, and the exponent as a variable. And again, we like to use x as the variable. For the theory and apparatus to work in general, we need the base a to be positive. If you want a negative base, you need to work with complex numbers, which is beyond the scope of this course. Here are some common examples. And note the variable x is the exponent, not the base. Y equals 2 to the x, 3 to the x, 0.5 to the x, 10 to the x, and something called e to the x, and I'll come back to that last one in a moment. 0.5 to the x is just a half to the x, which is really just 1 over 2 to the x, and that can be rewritten as 2 to the minus x. This last one, e to the x, uses perhaps the most important base in mathematics. The number e, also called Euler's number, and its decimal expansion begins 2.718. E is another famous and important real number with a non-recurring decimal expansion. So E is irrational, and the proof of that is difficult. I'll explain its importance in a moment. Euler was an 18th century mathematician. To have a number named after you is a great honour, and the ultimate honour is to have a number called by the first letter of your surname in lowercase. Let's first try to understand and visualise the exponential function y equals 2 to the x. And we have a pair of axes and some values for a few inputs x. 2 to the 1 is 2, 2 squared is 4, and so on. 2 to the 0 is 1, 2 to the minus 1 is a half, 2 to the minus 2 is a quarter, and so on. And we can plot corresponding points on the xy plane. And then join these points to get the full curve. And it gets very steep, very quickly as you move to the right. Let's try to think about how steep it gets. On the x-axis, as we've drawn it here, the scale is about 1 unit per centimetre. And on the y-axis, the scale has been made about 4 units per centimetre to fit in just these points. Now imagine if we wanted to include points on the graph for x equals 6, 7, 8, 9 and 10. Just an extra 5 centimetres of x-axis. Clearly the y values are large, and points to be plotted will go beyond this page. How long would the y-axis need to be to capture them all on the graph? With this scale on the vertical axis, to accommodate an extra 5 centimetres horizontally, when you do the calculation, we would need a page which is about 2.5 metres long. This is an example of something called exponential explosion, often associated with population dynamics. We'll have more to say about this in a later video. Now what about Euler's number E? What's so special about it? I'll try to explain. First, draw the x-y axes, and we'll keep the same scale on both axes. Then we add the line y equals x plus 1, which has slope 1 and passes through the y-axis at y equals 1. Note that 1 is e to the 0, so this y-intercept is also where the curve y equals e to the x crosses the y-axis. Now we add the curve y equals e to the x, and something nice happens. The line y equals x plus 1 becomes a tangent line to the curve at the y-intercept. Euler's number E is chosen to shape or sculpture the exponential curve precisely to have this property, and it's so important that we don't care that E happens to have a difficult decimal expansion. What this means is that the curve y equals e to the x, as well as the tangent line, has slope equal to 1 at the y-intercept. And the notion of slope of a curve will be formalised when we learn calculus in the next module. So what? Well, remember we mentioned in an earlier video that self-reference almost always leads to something useful in mathematics. In this case, we really do mean useful, big time. A consequence of this slope and tangent property is that the function y equals e to the x has a self-replicating property. After we've defined derivatives in the next module, you'll discover that the derivative of e to the x is just itself, e to the x. This is one of the most important facts in calculus and the key to developing a theory of differential equations. We've done a lot today. Discussed how some lateral thinking, changing your point of view, applied to power functions where the variable is the base, leads to exponential functions where the variable now is the exponent. Explored an example of exponential explosion and introduced Euler's number E, which has the property that the slope of the tangent to the curve y equals e to the x to the y-intercept is equal to 1, which has important consequences that we'll explore in future videos. Please read the notes, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. In In this video, we introduce logarithmic functions by reflecting the curves of exponential functions in the line y equals x, describe and illustrate very elegant logarithm laws related to exponential laws that we've discussed in an earlier video, and see that logarithms are a useful device for decreasing the complexity of arithmetic. You might recall that to invert a function, we reflect its graph in the line y equals x, which interchanges the roles of x, the input, and y, the output. Let's try this with y equals e to the x, where e is Euler's number. Flipping this transparency over, interchanging the horizontal and vertical axes has the effect of reflecting in the line y equals x and produces the graph of the inverse function. The curve we get corresponds to a function we call the natural logarithm, often written as y equals ln of x. ln is an abbreviation, though the origin of this is historically obscure, possibly related to the French word naturel for natural, used as an adjective coming after the noun. The exponential function using e as the base is often also called the natural exponential function. The rule for the natural logarithm may also be written with this log notation, an instance of something more general that we come to shortly. Observe that the domain of y equals e to the x is the whole real line. Even though the y values quickly disappear into the distance in this diagram, e to the x is defined for all real numbers x. The range is a set of positive reals, only taking values greater than 0. When we reflect in the line y equals x to get the inverse function, the roles of horizontal and vertical are interchanged, as are the roles of input and output, and domain and range. So the domain for the natural logarithm becomes the range of the exponential function, which is r+. And the range for the natural logarithm becomes the domain of the exponential function, which is all of r. Notice that we have this restriction on the natural logarithm that you only input positive real numbers. In the real number system, it doesn't make sense to take the log of a negative number. That was a lot to absorb, so recapping, the domain and range of y equals e to the x are the whole real line and the set of positive reals respectively. And you can denote the positive reals using interval notation if you like. Inverting functions interchanges domain and range. Therefore, the domain and range of y equals ln of x are the set of positive reals and the set of all reals respectively. Because they're inverses of each other, these functions undo each other in the following two ways. Firstly, the natural logarithm of e to the x is just x for all real numbers x. Secondly, if we raise e to the power of log x, then we get x back again, provided x is positive. Now what about other positive real numbers a used as a base for an exponential function? We can find a direct connection to the natural exponential function by exploiting one of the inverse function properties. For any positive a, we have a equals e raised to the power of ln of a. So a to the x becomes e to the ln of a, all to the x, which by an exponential law becomes e to the product of ln of a with x. And we can rewrite this as e to the x times ln of a, to avoid some brackets. And then the curve y equals a to the x becomes y equals e to the x ln of a. And it must have the same shape as the curve y equals e to the x, because we're multiplying the input x by a constant, ln of a, so the effect is just a rescaling of the horizontal x-axis. Here's a general picture of the curve y equals a to the x, for the base a being positive and greater than 1. We never consider a equals 1 as it's not interesting. 1 to the x equals 1 produces a constant function. And for a between 0 and 1, we have to reflect this shape in the y-axis, related to something called exponential decay, but we'll save that up for the next video. As before, we can reflect in the line y equals x to get the inverse function, now called the logarithm to the base a. And we use this log notation. In particular, when a equals e, this reduces to the natural logarithm. I'll just warn you that abbreviated notation for logarithms is not universal. Some people write simply log when they mean log to the base 10, and others, including some calculators, write log for log to the base e. Logarithms satisfy important laws that follow from the exponential laws which we discussed in the last video. The first law says that the logarithm of a product is the sum of the logarithms. The second law says that the logarithm of a quotient is the difference of the logarithms. The third law says that the logarithm of a kth power is the kth multiple of the logarithm in the sense that the exponent k falls down to the front. These laws also have succinct forms using the notation for the natural logarithm. These laws decrease the complexity of arithmetic. Logs turn products into sums, converting multiplication into addition, which is simpler. Quotients into differences, converting division into subtraction, which is simpler. And powers into multiples, converting exponentiation into multiplication, another simplification further up in the hierarchy of arithmetic. Here's some practice. Simplify log to the base 10 of the square root of 1,000. Now the square root of 1,000 is not a nice simple number, so you might expect to need a calculator. But in fact, we can simplify this quickly using the laws that we've introduced. First observe that the square root of 1,000 is 1,000 raised to the power of 1/2. And then bring the half out the front, because logarithms convert powers into multiples. But 1,000 is 10 cubed, and log to the base 10 undoes the exponential function using base 10. So log of 10 cubed to the base 10 must be just 3. So we get a half of 3, which is 3 on 2. And if you used a calculator, it should show 1.5. Now in the process of our development earlier, we used the fact that if a is positive and b is any real number, then a to the b is e to the b log a, which is quite amazing. It reduces questions about very general exponential expressions to natural logarithms and natural exponentials, in a certain sense, reducing everything to the mathematics of Euler's number. There's another useful fact. Let a be a fixed positive base and x any positive real number. Then x equals a to the log of x to the base a, since the exponential undoes the logarithm. We can then take natural logs of both sides. But remember, logs turn powers into multiples, so the right-hand side becomes log of x to the base a times ln of a. And then dividing both sides by ln of a and rearranging, we get finally log of x to the base a is the fraction ln of x divided by ln of a. This means that we can work out logs to any base just using natural logs and fractions. We've managed a lot today. We first defined the natural logarithm as an inverse function by reflecting the curve y equals e to the x in the line y equals x in the plane. Saw that we can do this also in general for y equals a to the x for any positive real number a, which defines the logarithm to the base a, then discussed logarithm laws and how these decrease the complexity of arithmetic. And finally developed some formulae which tell us how to calculate general logs and exponentials using natural logs and natural exponentials related to Euler's number. Please read the notes accompanying this video, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. In this video, we use exponential functions to model exponential growth and decay, and explore some contrasting examples and applications. We draw on techniques from recent videos to help us successfully perform calculations and make predictions using these models. Recall the shape of the curve for the natural exponential function y equals e to the x. What happens if we reflect this curve in the y-axis? Here are the two graphs on the same diagram. The pink curve is the result of reflecting the green curve in the y-axis. To get the reflected image, we're keeping the same y values but just switching each input x with its negative. This means that the rule for the pink curve must be y equals e to the minus x. Observe that e to the minus x is 1 over e to the x, which is 1 over e all to the x. If you type the reciprocal of e into your calculator, you get about 0.3678. So we get an exponential function with a base, 1 over e, which is less than 1. It's the case that every exponential function, y equals a to the x, with base a less than 1, is a scaled version of this particular shape. In the earlier videos, all of the graphs that we exhibited, in fact, had a base a greater than 1, like a equals e or a equals 2. And they become extremely steep as you move to the right, which models something called exponential growth. But just for now, I want to focus on the case where the base a is less than 1, and concentrate on this part of the graph where the curve looks like it's hugging the positive x-axis. The behaviour of the y values, getting closer and closer to 0 very rapidly, models what we call exponential decay. Physical examples include decay of radioactive elements such as uranium and certain isotopes of carbon used for carbon dating, decay or dissipation of drugs in the bloodstream, and reduction in air pressure as you increase your altitude above the Earth's surface. To capture the mathematics as flexibly as possible, we scale in both the x and y directions by considering functions of the form y equals a e to the kx, where a and k are constants. Note that e to the kx can be rewritten as a to the x by setting a equal to e to the k, so that the rule for the function can also be written as y equals capital A times little a to the x. If little a is greater than 1, then we have exponential growth, and if little a is less than 1, then we have exponential decay. In many applications, the input variable x denotes time, but let's apply the exponential decay to model air pressure, and in this application, the variable x will denote altitude above sea level. So y, written as a function of x, measures air pressure at altitude x, and altitude x equals 0 just means at sea level. The Summer Olympics were held in Mexico City in 1968. And there was a huge controversy about athletes who trained near sea level being disadvantaged and having to acclimatise to the high altitude and thinner air of Mexico City. What in fact was all the fuss about? Well, let's find the percentage reduction in air pressure as you move from sea level to Mexico City, which has an altitude of 2,237 metres. There's a useful scientific fact we can use that air pressure decays exponentially at about 0.4% per 30 metres. Put y equal to air pressure, in some appropriate units, as a function of altitude x metres above sea level. Using an exponential decay model, y equals a e to the kx for some constants a and k, and in fact k will turn out to be negative. Capital A equals y evaluated at 0 and represents the air pressure at sea level. But we never need to know the actual value of A, which you might find surprising. However, we do need to get information about the constant K. The first step is to find K. Observe that 0.4% is 0.004 as a real number. And if you take that away from 1, you get 0.996. So the science tells us that y of 30 is 0.996 times y of 0, which is a direct mathematical translation of the fact that air pressure at 30 metres is 99.6% of air pressure at 0 metres, that is at sea level. Putting this together with the rule for the function, we get a times e to the 30k, putting x equals 30, is 0.996 times y of 0, which just becomes 0.996 times a. Cancelling a from both sides gives e to the 30k is 0.996. Taking natural logs of both sides, we get 30k is the log of 0.996, because the log undoes the exponential on the left-hand side. So we get k is log of 0.996 divided by 30. You can approximate k on a calculator if you wish, but it's best to keep k in exact form for now rather than risk introducing rounding errors. This completes the first step. Remember, we're trying to find the percentage reduction in air pressure as we go from sea level to Mexico City. It will help to know what fraction of the air pressure at sea level, when x equals 0, is represented by the air pressure in Mexico City when x is 2,237. The second step, therefore, is to calculate the fraction y of 2,237 divided by y of 0. The ratio of the air pressure at Mexico City to the air pressure at sea level. Feeding these values for x into the formula for y, the ratio becomes this expression. But again, the a's cancel, and e to the 0 is 1, so this simplifies to e to the 2237 times k. We then feed in our expression for k, which we found from the first step, rearrange the order of the exponents to get e and the natural log next to each other, which simplifies because the exponential undoes the logarithm. Hence the ratio we're looking for becomes this fractional power 0.996 to 2237 divided by 30, which we can type into our calculator and see that it equals 0.74 to 2 decimal places. This completes the calculation for the second step. We can now convert this information into a percentage reduction. The ratio of the air pressures is 0.74, which equals 74%. So the percentage reduction must be 100 minus 74%, which is 26%. This solves our original problem. The answer we estimate to be about 26%. In fact, the true reduction is about 25%, so the model gives quite a good estimate. And you can appreciate why athletes might have had trouble breathing whilst competing in the Mexico City Olympics. What about examples of exponential growth? In fact, your bank account grows exponentially, but the base A on default savings accounts with paltry interest rates is so close to 1 these days that you might not notice the difference. Examples where the base is large occur commonly in population dynamics and the spread of diseases and early stages of epidemics. For example, if food is prepared and left out in the sun, exposed, and a fly lands on it and deposits some bacteria, it might be safe to eat straight away if your body's immune or defence system is robust enough to handle relatively small numbers of bacteria. But if the food is sitting there for an extended period of time and the bacteria has a chance to propagate and multiply, then there can be an exponential explosion in the population. If you then eat the food, then your body's defences could be overwhelmed and you might get sick. A more benign example of exponential explosion occurred in a previous video when we drew part of the graph of y equals 2 to the x and contemplated what would happen if we increased the sizes of the inputs. I'd like to take that example 2 to the x a bit further and tell you a story about Aladdin. You know, the guy with the lamp and the genie. Well, Aladdin and Princess Jasmine wanted to get married, but the Sultan wasn't keen on the idea and didn't immediately grant permission. The Sultan said, "Aladdin, to obtain my consent, you must perform the following simple task spread over 64 days. One of my courtyards is designed as a gigantic chessboard. There are 8 times 8 equal to 64 huge empty squares. Tomorrow is the first day of your task, and you must bring 1 grain of rice and place it on the first square in the courtyard. On the next day, you must bring 2 grains of rice and place them on the second square. The day after that, you must bring 4 grains of rice and place them on the third square. Every subsequent day up to and including the 64th day, you must bring twice as many grains of rice as the previous day and place them on the next empty square of the courtyard. If you manage to do this for 64 days, then you will have my consent." Aladdin thought he had it made. This seemed such an absurdly simple task. Each square was big enough to take sacks and sacks of rice, and the Sultan was only talking about just a few grains. Let's look at the mathematics, and also something closer to home. Bondi Beach has a lot of sand. How many grains of sand do you think there are? The beach is about 1 kilometre long and about 200 metres wide. Suppose that the sand goes down about 10 metres. A grain of sand occupies about 10 to the minus 9 cubic metres. So a rough estimate of the number of grains of sand you can calculate turns out to be about 2 times 10 to the 15. Getting back to Aladdin, he has to bring twice as many grains of rice each successive day to the Sultan's courtyard. So the amount he brings on any given day is a power of 2 with a variable exponent. So it becomes an exponential function of the number of days that have passed. Let n equal to n of x be the number of grains of rice that Aladdin brings on day x, to put on square x of the Sultan's courtyard chessboard. If you think about the pattern of doubling from one day to the next, you get the formula n of x is 2 to the x minus 1, which is 2 to the x divided by 2. The reason for the minus 1 in the exponent is that on the first day, Aladdin brings 1 grain of rice, and 1 equals 2 to the 0, which is 2 to the 1 minus 1. Do you think, in completing his task, that Aladdin might ever have to bring to the Sultan more grains of rice than there are grains of sand on Bondi Beach? The answer might surprise you. Let's do the maths and work out the first day X on which the number of grains of rice must exceed the number of grains of sand on Bondi Beach. We want 2 to the x divided by 2 to be greater than 2 times 10 to the 15. So 2 to the x is greater than 4 times 10 to the 15. We want to find x, but it appears as an exponent. To bring it down, we apply the natural logarithm to both sides and use some log laws to get that x log 2 is greater than log of 4 plus 15 log 10. So dividing by log of 2, we get that x is greater than this fraction, which evaluates to approximately 51.8 on a calculator. So the 52nd day will be the first day in which Aladdin is lugging in more grains of rice to put on 1 square of the courtyard than there are grains of sand on Bondi Beach. Aladdin hasn't even reached the last row of the chessboard. The Sultan was cunning. This looks even too tough a task for Aladdin's genie. Such is the deceptive and mind-boggling nature of exponential growth. The moral of the story: don't eat food left out in the sun if there's any risk of flies and bacteria playing games with exponential explosion. In this video, we looked at 2 important aspects of the behaviour of exponential functions. This can be used to model exponential growth when the base is more than 1 and exponential decay when the base is less than 1. And we analysed the mathematics of some contrasting examples. Please read the notes accompanying this video, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. In this video, we introduce the sine, cosine and tangent of an acute angle, which are essential ingredients of trigonometry, leading to general definitions of circular functions in the next video. Trigonometry is the study of triangles through a careful analysis of the relationships between lengths and angles. Consider a right-angled triangle with side lengths A, B and C, where C is the hypotenuse and A and B are the shorter side lengths. Draw in the angle between the sides A and C and give it a name theta. Notice that theta is acute, that is, lies between 0 and 90 degrees. We say that the side A of the triangle is adjacent to theta and the side B is opposite theta. Now define the sine, cosine and tangent of the angle theta by the following rules. Sine theta is B on C, the opposite side over the hypotenuse. And note that it's conventional to abbreviate sine by dropping the E. Cos theta is A over C, the adjacent side over the hypotenuse. And note that it's conventional to abbreviate cosine by dropping the INE, and we say cos. And tan theta is B over A, the opposite over the adjacent. And note that it's conventional to abbreviate tangent to just TAN, tan. There's a connection to tangent lines which we'll explain in the next video. By the theorem of Pythagoras, a squared plus b squared equals c squared. So taking this equation and dividing through by c squared, we get a squared on c squared plus b squared on c squared equals 1. So that a on c all squared plus b on c all squared equals 1. So that in light of our definitions, cos theta all squared plus sine theta all squared equals 1. It's conventional to write cos squared theta for cos theta all squared in this way to try to remove some brackets, which is useful to decongest notation when formulae become complicated, and similarly sine squared theta for sine theta all squared. Then the earlier equation becomes cos squared theta plus sine squared theta equals 1, or equivalently sine squared theta plus cos squared theta equals 1. This is called the circular identity, related in a natural way to circles, as we'll see in the next video. If we take the ratio of sine theta with cos theta, something nice happens. Sine theta divided by cos theta is b over c divided by a over c, which equals b over a as the c's cancel, which just becomes the definition of tan theta. Thus we see that tan theta is just sine theta on cos theta. Let's work out some common trig values. Trig is an abbreviation for trigonometry. Consider first an isosceles triangle where the two shorter sides have equal length, and there's no harm scaling it up or down so that its hypotenuse has length 1. Using a hypotenuse of 1 gets you used to interpreting trig values in terms of the unit circle discussed in the next video. Because the angles add up to 180 degrees, and the other two angles are equal, they must both be 45 degrees. Hence theta in our diagram becomes 45 degrees and b equals a. Thus, 1 is 1 squared, which is a squared plus b squared, which is 2a squared. So a squared is a half, so a is the square root of a half, which is 1 over the square root of 2, which you can leave just like that, or you can also write it as root 2 over 2. Hence the two shorter sides of the triangle are both 1 over the square root of 2. So sine 45 degrees is opposite over hypotenuse, which is 1 on root 2, divided by 1, which is just 1 over root 2. Cos of 45 degrees is adjacent over hypotenuse, which is also 1 over the square root of 2. And tan 45 degrees is opposite over adjacent, which is 1 over root 2 over itself, which is just 1. Let's next consider a right-angled triangle with hypotenuse 1 and angle theta equal to 30 degrees. Just from the diagram, the opposite side length you might guess to be half the length of the hypotenuse, so should be a half. And this turns out in fact to be true. Why is that? To see why it must be a half, you can add the reflection of this triangle in the horizontal. And putting the two triangles together makes a larger triangle with all angles equal to 60 degrees. This is easy to see because the angle in the middle is got by doubling 30 degrees, and the other 60-degree angles are forced by the fact that angles of a triangle add up to 180 degrees. But then this larger triangle is equilateral, so all side lengths are equal to 1. So half of the vertical side length is just 1/2, confirming our earlier visual intuition or guess. What then is the adjacent side length a in the original 30-degree triangle? By Pythagoras, 1 is a squared plus a half all squared, which is a squared plus a quarter. So a squared is 1 minus a quarter, which is 3/4. So a is equal to the square root of 3/4. That is, a is the square root of 3 divided by 2. So now we have complete information to read off sine 30 degrees, which is a half over 1, just a half. Cos of 30 degrees is root 3 on 2 over 1, which is root 3 on 2. And tan 30 degrees is a half divided by root 3 on 2, which is 1 on root 3. We can use the same triangle to read off trig values for another case because the angles add up to 180 degrees, so the remaining angle must be 60 degrees. To make it easier or clearer how to read off the values with our setup, first just flip over and reorient the triangle. So the angle 60 degrees is between the hypotenuse and the horizontal side. Now we can read off sine 60 degrees, opposite over hypotenuse, that's root 3 on 2. Cos 60 degrees, adjacent over hypotenuse, which is just a half. And tan of 60 degrees, opposite over adjacent, which is just root 3. Here's the complete table for sine, cos and tan theta for those special angles theta equal to 45, 30 and 60 degrees respectively. Notice that surd expressions involving the square root of 2 and the square root of 3 arise quite naturally. In advanced trigonometry, there are more complicated surd expressions for other angles, but we won't need them, and typically it suffices to use your calculator for most angles. There's an important issue we'll get to later concerning the way angles are measured. For calculus, the most natural angle measure uses radians, and we'll discuss that in the next video. We'll finish with an example where we don't even know the value of the angle, but can use some detective work to deduce information about trig values. Suppose we have an acute angle theta such that tan of theta is 3. Find sine theta and cos theta. This looks at first sight like there just isn't enough information. We don't even have a diagram of a triangle to guide us. Well, we can quickly remedy that, and a rough sketch suffices. For tan theta to be equal to 3 means that in a right-angled triangle with angle theta, the ratio of the opposite side length to the adjacent side length is 3. So we draw a triangle with a vertical side length 3 times as long as the horizontal side length. The diagram is just a guide to finding the solution and doesn't have to be accurate. Label the hypotenuse h, say. By Pythagoras, h is the square root of 1 squared plus 3 squared, which is the square root of 10. But now we have enough information to read off sine theta and cos theta. Namely, sine theta, opposite over hypotenuse, is 3 on root 10, and cos theta, adjacent on hypotenuse, is 1 on root 10. We can use a circular identity, sine squared theta plus cos squared theta equal to 1, as a check. 3 on root 10 all squared, plus 1 on root 10 all squared, which is 9/10 plus 1/10, is 1, which checks out. We've made a good start introducing some trigonometry, working towards developing the theory of circular functions in the next video. Today we first define the sine, cosine and tangent of an acute angle using ratios of side lengths of an associated right-angled triangle. Worked out the details in the special cases where the angle is 45 degrees, 30 degrees and 60 degrees. And also discussed an example where we could figure out trig values from just one known trig value without actually knowing the value of the angle. Please read the notes accompanying this video, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. In this video, we introduce the radian measure of angles and extend the trigonometric definitions of the previous video by using points on the unit circle to define the sine, cosine and tangent of any angle. This leads to the so-called circular functions y equals sine x and y equals cos x and their graphs. We start off with the unit circle, centered at the origin, with radius 1. A typical point xy on the circle satisfies the equation x squared plus y squared equals 1, related to the so-called circular identity that we mentioned last time. There's also an angle we call theta between the positive x-axis and the radius that links the point to the origin. How do we measure angles? In the last video we measured angles in degrees and even referred to the fact that angles of a triangle add up to 180 degrees. It turns out, for calculus, that the radian measure of angles is more useful. But first, let's remind ourselves that there are 360 degrees in a single full revolution of the circle. This idea was introduced by the ancient Babylonian mathematicians. It's useful because 360 is a nice number. It's 2 times 180, which is 4 times 90, and so on. And there's so many different devices that capture lots of useful common angles. We'll keep using degrees, especially for applications, but the radian measure turns out to be the best and most appropriate for calculus. Radians measure arc length on the unit circle. What does that mean? Here's the unit circle again, with a point subtending an angle theta with the positive x-axis. The distance we travel along the circle to get to our point is the arc length, and this is defined to be the radian measure of the angle. For example, a full revolution of the circle subtends 360 degrees, and the arc length is just the perimeter, which is 2 pi times the radius, which is just 2 pi since the radius is 1. Hence 360 degrees corresponds to 2 pi radians. Half of a full revolution subtends 180 degrees, and the arc length is just half of the full perimeter, which is pi. Hence 180 degrees corresponds to pi radians. Similarly, 90 degrees corresponds to pi on 2 radians, and so on. So what should 1 degree be in radians? Well, we just divide 2 pi by 360, which simplifies to pi on 180 radians. What should a single radian correspond to in degrees? Well, by reciprocating, 1 radian is 180 on pi degrees. And if you type this into your calculator, you get about 57.3 degrees. With radian measure, we drop the word radians and just use numbers. So if an angle is quoted as a number, you know that radians are intended. So 360 degrees becomes the number 2 pi, 180 degrees becomes the number pi, and so on. A single degree is represented by the number pi on 180. And the number 1, interpreted as an angle, is 180 on pi degrees. Angles then are really just numbers, so it can be positive, negative, or 0. Positive angles are measured by anti-clockwise rotation about the unit circle. Negative angles are measured by clockwise rotation. For example, if we move anti-clockwise 45 degrees from the starting point, then we've moved pi on 4 radians. If we move clockwise 45 degrees, then we've moved negative pi on 4 radians. Here are some more angles. Note, with this last pair, pi and negative pi, we end up at the same point on the unit circle. Angles are said to be equivalent if you end up at the same point on the unit circle. Angles that are large in magnitude can involve multiple revolutions of the unit circle. For example, an angle of 4 pi uses up 2 revolutions. An angle of 6 pi uses 3 revolutions, and so on. The angles 2 pi, 4 pi, and 6 pi all end up back at the same starting point, so are equivalent. In the last video, we defined sine, cos, and tan of an acute angle in terms of certain ratios of side lengths of right-angled triangles. It turns out there's a much more general way of defining these for any angle, exploiting coordinates of points that wind around the unit circle. Here's the unit circle with the points subtending an angle theta with coordinates x, y, say. We now define cos theta to be the x-coordinate and sine theta to be the y-coordinate. You move directly to the x-axis to get cos theta, the first coordinate, and directly across to the y-axis to get sine theta, the second coordinate. In this particular diagram, the angle theta happens to be acute, and there's a right-angled triangle formed by the radius, a piece of the x-axis, and a vertical line segment parallel to the y-axis. The horizontal side of this triangle equals the adjacent over the hypotenuse, since the hypotenuse is 1, given cosine of theta, and the vertical side length equals the opposite over the hypotenuse, giving sine of theta, again since the hypotenuse is 1. So the coordinates of the point reproduce the definitions of cos theta and sine theta that we gave in the last video in terms of right-angled triangles. But the definitions work anywhere on the circle. Regardless of where you are, you get the cosine of the angle by moving down, or possibly up, to the horizontal axis, and the sine of the angle by moving directly across to the vertical axis. We define tan of theta always to be sine theta divided by cos theta, provided cos theta is not equal to 0. In this diagram, we're in the first quarter of the circle, also called the first quadrant, where the coordinates are all positive. Thus, sine theta and cos theta are both positive, and tan theta is also positive. In the second quadrant, the angle theta is now obtuse, and the x and y coordinates have mixed signs. In this case, sine theta is positive, but to get cos theta, you drop down to the negative part of the x-axis, so cos theta is negative. In this case, tan theta is the quotient of a positive by a negative number, so it will be negative. In the third quadrant, now both coordinates, cos theta and sine theta, are negative. So tan theta becomes the quotient of 2 negative numbers, which is positive. In the fourth quadrant, cos theta is positive and sine theta is negative. So tan theta becomes negative. There are some important extreme cases on the boundaries between the quadrants, where one of the coordinates is 0 and the other is plus or minus 1, corresponding to angles 0, pi on 2 pi, and 3 pi on 2 radians respectively. For example, the point 1, 0 equals cos of 0, sine of 0, corresponding to the angle 0. So sine of 0 is 0, and cos of 0 is 1. Hence, tan of 0 is just 0 divided by 1, which is 0. The point 0, 1 equals cos pi on 2 sine pi on 2, corresponding to an angle of 90 degrees. So sine of pi on 2 is 1 and cos of pi on 2 is 0. So if we try to apply the formula for tan pi on 2, we get into trouble, because this needs to be 1 over 0, which is undefined. The other points for angles pi and 3 pi on 2 are discussed in more detail in the notes. But let's try to understand the geometric significance of the fact that tan of pi on 2 is undefined. Here's the unit circle again. Let's draw a vertical line that just glances the circle where it crosses the x-axis at x equals 1. This is called a tangent, or tangent line to the unit circle, touching the circle at the x-intercept. Now at a point on the unit circle, say making an angle theta with the positive x-axis. Then we extend the radius from the origin through this point until we touch the tangent. We can drop a vertical from the point on the circle down to the x-axis, creating a right-angled triangle with horizontal side length x equals a, say, and vertical side length y equals b, say. So a is cos theta, the result of dropping down to the horizontal axis, and b is sine theta, the result of moving across to the vertical axis, which form the coordinates of the point. The point where the line extending the radius meets the tangent has a vertical distance, h, say, from the x-axis. What is h? Notice that the tangent is parallel to and located 1 unit from the y-axis. We can work out what h is by locating similar triangles, which are highlighted in the diagram. The ratio b on a, coming from the smaller right-angled triangle, is equal to h on 1 from the larger triangle. But this is just h. So h, being b on a, is just sine theta over cos theta, which, remember, is tan theta. This relationship with the tangent line explains the terminology involving the word tangent. Thus, tan of an angle theta is just the length of this piece that you get by extending the radius through the point on the circle until you hit the tangent line. If the angle theta happens to be negative, say moving clockwise around the unit circle but staying in the 4th quadrant, this method also works, but you hit the tangent line below the x-axis, and tan theta is then measured as negative. Now we can explain why tan of pi on 2, or 90 degrees, should be undefined. Start off with the unit circle and the vertical tangent line that touches the circle at the x-intercept. Now move the radius anti-clockwise from x equals 1 on the x-axis along the circle towards y equals 1 on the vertical axis, but extend the radius until it touches the tangent. Make note of the vertical distance from this point on the tangent line to the x-axis. And just keep repeating this as the radius rotates to get closer and closer to y equals 1 on the y-axis. But very quickly, we run out of room on the tangent line in the diagram. The vertical distances from the point on the tangent line to the x-axis are the tans of the angles, and these vertical distances shoot off towards infinity. As theta, the angle made with the positive x-axis, gets closer and closer to pi on 2, tan theta heads off towards infinity. This explains geometrically why tan of pi on 2 should be undefined. Now, in forming sine theta and cos theta, we're really thinking of theta as an input into a function. But remember, it's traditional to use x as an input. So here's the unit circle again, but think of x now as the arc length subtended by the angle. So x becomes the angle itself. From the unit circle, we can read off the sine and cosine of this angle by moving directly across to the vertical axis to get sine of x, and straight down to the horizontal axis to get cos of x. Let's just focus on sine x for the time being. Notice as x moves from 0 to pi on 2, covering the first quarter of the unit circle, sine x has moved from 0 to 1. The blue dot on the circle has carried the pink dot, representing the sine of x, up the vertical axis. As x continues then to move from pi on 2 to pi, then sine of x, the pink dot, comes back down from 1 to 0. As x continues then to move from pi to 3 pi on 2, sine x moves from 0 to minus 1. Finally, as x moves from 3 pi on 2 to 2 pi, sine x moves from negative 1 to 0, and we're back where we started. As x continues to wind around the circle as many times as you like, sine x will oscillate backwards and forwards between 0, 1, 0, minus 1, and 0. Now form the function with the rule y equals sine of x. We can ask, what does its graph look like? Here's part of the graph for x equals 0 through to x equals 2 pi, capturing this oscillation effect that we just looked at a moment ago, using a pink dot representing the y values. This curve is called sinusoidal. And the shape continues to repeat as x moves further along the positive x-axis, winding around the unit circle as often as you like. This captures movement anti-clockwise around the circle. Remember, clockwise movement corresponds to negative angles, so if we allow x to move to the left along the negative half of the real line, then sin x will also oscillate and the sinusoidal graph repeats ad infinitum to the left as well as to the right. Thus we get the full sine curve extending along all of the real line, creating a wave that oscillates infinitely often. Let's try to understand now how cosine of x behaves. We'll go around the unit circle again, but remember the cosine of x is located on the horizontal axis, represented here by a pink dot again. As the angle x moves from 0 to 2 pi, as the blue point makes a full revolution of the circle, the cosine of x moves from 1 to 0 to -1 and back from -1 to 0 to 1. If we continue to wind around the circle, cos x just repeats this pattern. Now form the function with rule y equals cos x. What does its graph look like? Here's the part of the graph, x equals 0 through to x equals 2 pi, capturing this oscillation effect of the y values, represented a moment ago by the pink dot. And this pattern is repeated ad infinitum to the right and left, forming the cosine curve. If we compare it with the sine curve, you'll notice that both have the same shape and only differ by horizontal translation. So the cosine function is also sinusoidal. The functions y equals sine x and y equals cos x are said to be circular because the pair of values, cos x sine x, represents points on the unit circle. There are also so-called hyperbolic functions, which form pairs of values that represent points on a hyperbola, but discussion of them goes beyond the scope of this course. The graph of the function y equals tan x is very interesting, and we'll save that up for the next video when we introduce inverse trigonometric functions. Again, we've covered a lot of ground in a short space of time. We've introduced radian measure of angles using arc lengths on the unit circle and shown how to convert degrees into radians and back again. Introduced rules for forming sine and cosine of any angles using coordinates of the unit circle, and discussed how to form the tangent of an angle provided the cosine is non-zero, and how the tangent of an angle arises geometrically. We've defined the circular functions y equals sine x and y equals cos x, and illustrated how the graphs arise as sinusoidal curves. Please read and digest the notes, which contain more details, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. In this video, we restrict the domains of the sine and cosine functions so that the graphs satisfy the horizontal line test and therefore become graphs of invertible functions. And use reflection in the line y equals x to visualize the inverse sine function. We also sketch the graph of the tan function and repeat this process to describe the inverse tan function. Here are the graphs of the two circular functions, y equals sine x and y equals cos x, both producing sinusoidal curves and wave patterns that replicate infinitely often as one moves back and forth along the real number line. Both sin x and cos x are defined for all real numbers x, interpreted as angles that wind around the unit circle. The domain in both cases is R, the whole real line. Because we move from points on the unit circle across to the vertical axis of sin x and down or up to the horizontal axis of cos x, the values are trapped between plus and -1, so that the range is the interval from -1 to 1, including both endpoints. Graphs of all functions automatically satisfy the vertical line test. What about the horizontal line test in these cases? In fact, any horizontal line that touches either graph passes through infinitely many points. So the horizontal line test fails spectacularly for both graphs. Remember, for a function to be invertible, we need the graph to pass the horizontal line test. So neither of these look like they have any hope of being invertible. Well, there is hope. We can severely restrict their domains so that we get a fragment of each graph that passes the horizontal line test. For the sine curve, we box in this tiny part of the curve, ignoring everything else. It's standard to restrict the domain to the interval from negative pi on 2 to pi on 2, including both endpoints, and then we get this fragment of the original sine curve. Note that the range remains the same, the interval from -1 to 1. This fragment has a very pleasant rotational symmetry about the origin. The curve coincides with itself if we rotate it 180 degrees, an instance of being an odd function, a concept that's important in future videos. For the cosine curve, it's not so clear what to choose, but everyone agrees to box in this part of the curve, restricting the domain to the interval from 0 to pi, producing this fragment, and again the range is unchanged, the interval from -1 to 1. Here are the two fragments, and you can see that horizontal lines pass through these curves at most once. They've been deliberately chosen to both pass the horizontal line test. Let's see what happens to this fragment of the sine curve when we reflect in the line y equals x. To simulate the reflection, we can take a transparency with this fragment and flip it over. Here are the fragment, the line y equals x, and the reflected image all on the same diagram. And here's the reflected image on its own. The roles of input and output have been interchanged, so the labels plus and minus pi on 2 now become points on the vertical axis, and the labels plus and minus 1 now become points on the horizontal axis. And we have the graph of y equals inverse sine of x. Remember, inversion interchanges domain and range, so the domain of inverse sine is the range of sine, which is the interval from -1 to 1, and the range of inverse sine is the domain of our fragment of the sine function, which is the interval from minus pi on 2 to pi on 2. Just think of the sine function as taking angles to numbers, and the inverse sine function as bringing numbers back to angles. Now, of course, angles are numbers if measured in radians, but it can help to have some kind of mental image of a geometric angle that is the output of inverse sine. For example, sine of 30 degrees, or sine of pi on 6 radians, is a half. So inverse sine of a half gets you back to 30 degrees or pi on 6 radians. Maybe you conjure up in your mind an image of a 30-degree right-angle triangle with opposite side length 1/2. Sine of 60 degrees, or pi on 3 radians, is root 3 on 2, so inverse sine of root 3 on 2 gets you back to 60 degrees, or pi on 3 radians. Sine of 90 degrees, or pi on 2 radians, is 1. So inverse sine of 1 gets you back to 90 degrees, or pi on 2 radians. Sine of minus pi on 2 is -1, so inverse sine of -1 gets you back to minus pi on 2. Here's an application. Suppose a kite is flying 40 metres directly above the ground, but fastened to the ground by a piece of string which is 50 metres long. Assuming the string is approximately straight, we want to estimate the angle of elevation, which we call theta. In the diagram, you can see a right-angled triangle with angle theta, opposite side length 40 metres, and hypotenuse represented by the string of length 50 metres. The adjacent side is the ground, but we don't need to know what its length is to solve the problem. To solve this, observe that sine theta is the opposite over the hypotenuse, which is 40 over 50, equal to 0.8. To get back to the angle theta, we take the inverse sine of 0.8. If your calculator is in radian mode, then you should get 0.93 radians to 2 decimal places. If it's in degree mode, you should see 53 degrees to the nearest degree. This checks out because 53 multiplied by the conversion factor pi on 180 is approximately 0.93 radians. The analysis for inverting the fragment of the cosine curve is similar and explained in the notes. I'd like to spend the remaining time discussing the inverse tan function, which plays a central role later in integral calculus. You might recall from the last video that tan of x heads off towards infinity as x moves towards pi on 2, or 90 degrees, in the first quadrant of the unit circle. We can graph the relationship between x and tan x for these values of x, and it looks like this. And we have similar behaviour in the negative direction if we move in the fourth quadrant from 0 towards negative pi on 2. The lines x equals plus or minus pi on 2 become vertical asymptotes to the curve. Because tan x is sin x on cos x, the periodic behaviours of sine and cosine mean that this picture reproduces itself ad infinitum, both to the right and to the left, with infinitely many vertical asymptotes, which in fact occur at odd multiples of plus or minus pi on 2. Again, the horizontal line test fails spectacularly, so we have to drastically restrict the domain in order to produce the graph of an invertible function. The convention is to restrict the domain to the interval from minus pi on 2 to pi on 2, but not including the endpoints where tan is undefined. So we focus on this very nice piece of the tan curve, which satisfies the horizontal line test. And we can reflect in the line y equals x to invert the function, producing the graph of y equals inverse tan of x, a beautiful shape called a sigmoid curve, sandwiched in between two horizontal asymptotes. Sigmoid curves are important in computer science and the mathematics of neurons used to model behaviour in the brain. Remember, inversion interchanges domain and range, so the domain of inverse tan is the range of tan, which is the entire real number line, and the range of inverse tan is the domain of our fragment of tan, which is the interval from negative pi on 2 to pi on 2, but not including the endpoints. Again, just think of tan as taking angles to numbers and inverse tan as bringing numbers back to angles. For example, tan of 45 degrees or pi on 4 radians is 1. So inverse tan takes 1 back to 45 degrees or pi on 4 radians. Maybe you conjure up in your mind an image of a 45-degree right-angled triangle with equal opposite and adjacent side lengths. Tan of negative pi on 4 is negative 1, so inverse tan takes minus 1 back to minus pi on 4. Here's an application. The Statue of Liberty is 46 metres tall, standing on a pedestal of the same height. Find the angle theta subtended by the statue if you're viewing it from a distance of 250 metres. Though we haven't been asked to find it, let's denote the angle subtended by the pedestal by another angle called phi. So there's a right angle triangle with angle phi, with opposite side length 46 metres and adjacent side length 250 metres. So tan of phi is the fraction 46 over 250. So undoing this gives us phi equal to inverse tan of that fraction. There's another right angle triangle with angle phi plus theta, with opposite side length 46 plus 46 equals to 92 metres, and adjacent side length again 250 metres. So tan of phi plus theta is the fraction 92 over 250. Undoing this gives us phi plus theta equals inverse tan of that fraction. Taking phi away gives us theta equals this very nice explicit expression involving fractions in inverse tan, and we can evaluate this using a calculator to get approximately 0.17 radians, which is about 9.8 degrees. This solves our original problem. The angle subtended by the statue from 1/4 of a kilometre away is almost 10 degrees. This is in fact the last video for Module 2. Over the course of this module, we've introduced and discussed so many different and contrasting ideas, all glued together by the unifying concept of a function and associated ideas of domain, range, and graph. We've talked about linear functions, whose graphs are lines, and quadratic functions, whose graphs are parabolas, and discussed techniques involving completing the square and the quadratic formula. We talked about polynomial functions, built out of non-negative integer powers of x, which can be evaluated using simple arithmetic. And on the way mentioned fractional powers, which are a neat way of interpreting square roots and other types of roots. We showed how to create new functions by means of composition and inversion, both geometrically by reflecting in the line y equals x and by algebraic manipulation. By changing our point of view with regard to the roles of constants and variables, we moved from power functions to exponential functions and discussed the most important base, Euler's number E. We described logarithmic functions and discussed exponential and logarithmic laws and applied them to exponential growth and decay. Recently, we introduced trigonometry and the sine, cosine and tangent functions. Just now we discussed the inverse sine and inverse tangent functions and briefly illustrated how they can be used to interpret numerical information in terms of angles. Please read and digest the notes, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. Welcome back. You've just completed the first two modules, which provided you with a comprehensive toolkit from pre-calculus and an extensive repertoire of functions and techniques for manipulating them, and also for visualizing them using graphs in the XY plane. This next module is the first of two modules introducing and developing techniques of differential calculus. We begin by discussing average rates of change, which become instantaneous as time intervals become vanishingly small, leading to the notion of a derivative. The motivating example of velocity is used throughout, which turns out to be the derivative of displacement with respect to time. If you're used to looking at and processing information from the speedometer of a moving vehicle, like a car or truck, then you already have practical experience with derivatives. The derivative is the limit of certain fractions associated with curves, namely the slopes of secants, which approach the slope of the tangent line to the curve at a point of interest. Tangent lines are very good approximations to the curve, and you'll learn techniques involving differentials that exploit this fact. The mathematics uses the beautiful and elegant Leibniz notation due to Gottfried Leibniz, one of the founders of calculus, along with Newton in the 17th century, and has endured to the present day. You'll become experts very quickly with Leibniz notation and see how to use it to get information easily about the derivative of a function and how to apply it. Again, we hope that you'll find the material interesting and stimulating, that you'll find the videos helpful, and the practice and challenges provided by the many exercises beneficial. I look forward very much to your continued attention and participation. As you'll see, calculus is really about developing, as fully and completely as you possibly can, an understanding of how things change. We work with functions which, as you know, provide a link or connection between inputs and outputs. In this video, we explore the way outputs of functions change on average as we vary the inputs. We restrict inputs to some given finite interval of the real line and capture this idea of averaging by finding the slope of the line joining 2 points on the graph of the function. This leads to the notion of the average rate of change of a function. Graphs of functions visualize relationships between quantities represented by variables, say x and y. Here's the graph of some fairly wild, fluctuating function, y equals f of x. Let's just focus on an interval of inputs x between a and b where a is less than b. There are 2 points on the curve with inputs x equal to a and b, with outputs f of a and f of b respectively. And we can tidy things up by throwing away extraneous points, restricting the domain to the interval from a to b. We'd like to know or try to gain insight about how one quantity affects or causes changes in another quantity. This is especially important if you want to make predictions. The Reserve Bank wants to know what effect changing the base interest rate might have on certain measures associated with the economy. It could do some kind of mathematical modelling to make reasonable estimates. Almost certainly sophisticated functional relationships will come into play, and the functions could involve many variables. In our case, we simplify things and have just 2 variables, an independent variable x, moving between a and b, and a dependent variable y, whose values are constrained by the graph pictured here. Now, values produced by functions like this one can fluctuate a lot. We can ask, on average, about the overall fluctuation. Here, f of b is bigger than f of a, but how much bigger? Well, the overall change in y values is the difference f of b minus f of a. But we want to interpret this in context. The rate at which this change has occurred is relative to the length of the interval, which is the difference b minus a. The shorter the interval, the faster we think of this change as occurring. The longer the interval, the slower we think of this as occurring. To capture the average rate of change, we should divide the change or difference in the outputs by the change or difference in the inputs. This becomes a formal definition. The average rate of change for y equals f of x over the interval from a to b is f of b minus f of a divided by b minus a. In a moment, you realise this is an instance of something familiar. If we join the endpoints, coloured pink in the diagram, by a straight line, coloured blue, then this quotient is just the slope of that blue line segment, the vertical rise divided by the horizontal run. We can think of the line between the endpoints of the curve as smoothing out or ignoring wriggles or fluctuations. So what? How does this relate to reality? Well, road traffic authorities are very interested in the concept of average rate of change. Here's a graph of a function in the xy plane. It describes one of my car trips from Sydney to Melbourne, and the curve emanates from the origin. The vertical axis denotes distance in kilometres from the starting point in Sydney, corresponding to 0, and the horizontal axis denotes time since the journey began. Observe that 873 kilometres is the full length of the journey, finishing in Melbourne. On the horizontal axis, 0 hours, minutes and seconds matches the usual 0. The endpoint of the domain on the x-axis denotes the total time spent on the journey, which happens to be just over 11.5 hours. Notation for counting time in hours, minutes and seconds originated with Babylonian mathematicians who invented the base 60 counting system. Based on dividing units into 60 parts, an hour is 60 minutes and a minute is 60 seconds. At this highlighted part of the journey, where the graph is flat, the car isn't moving and I'm at Holbrook, just over halfway to Melbourne, having a rest. Here's another flat part and I'm at Benalla having an even longer rest. Even though there's a lot of fluctuation, including periods of not moving, we can still ask about the overall average rate of change associated with this journey. We join the endpoints using a straight line and find its slope, which is 873 divided by just over 11.5 hours, which you can calculate to be approximately 75.4 kilometres per hour. This says that over the entire journey, my average speed was about 75 kilometres per hour. Let's zoom in on this part of the graph highlighted here, which looks roughly like a piece of straight line, but with a steeper slope than the average. Here's the highlighted piece enlarged and tidied up a little. The endpoints in fact correspond to speed cameras located at Coolac and North Gundagai. These are average speed cameras, which means that they're used to work out exactly the average rate of change, that is the average speed for that part of the journey. If it turns out to be more than the speed limit, 110 kilometres per hour, then the driver is breaking the law and receives a fine in the mail a few days later. Let's see what happened in my case. I drove fairly smoothly, but not exactly uniformly over that stretch. To get the average rate of change, we join the endpoints and find the slope, which is the vertical rise over the horizontal run, which becomes 16 kilometres divided by 9 minutes and 9 seconds. The denominator converts to a decimal and the fraction evaluates to about 104.9 kilometres per hour. So my average speed for this segment appears to be just under 105 kilometres per hour, safely within the speed limit. But we have to be cautious about accuracy. Notice that though the time has been measured very accurately, and indeed the Babylonians had a reputation for accuracy using their base 60 system, the distance on the y-axis is only quoted to the nearest kilometre. Suppose, for example, that the true distance to the camera at Coolac was slightly less than the whole number on the y-axis, and the true distance to the camera at North Gundagai was slightly more. Then we have to make some adjustments to the previous calculation. And we get an approximation of 110.2 kilometres per hour, which in fact is over the speed limit. You can see how sensitive these calculations can be with regard to possibilities of rounding errors, so one must exercise caution. Estimates of about 110 and 105 agree fairly well to two significant figures, so the mathematics is working, but the outcomes in terms of staying within the speed limit could be drastically different. There are a couple of important issues. The first is the sensitivity of conclusions to rounding errors, which we've just discussed. The second issue is that even if the estimate of 105 kilometres per hour is correct, it's only an average over that leg of the journey, and it's possible to exceed the speed limit at some moment. The graph isn't a straight line. If you were looking at the speedometer of the car, you would notice that my instantaneous speed is in fact fluctuating from moment to moment. It's possible, even though the average was about 105, that the speedometer was reading over 110 at some moment. We want to work towards understanding what we might mean by instantaneous speed. This will be formalised soon using the notion of a derivative, and here's a sneak preview. If you take a line segment with the same slope as the average and move it across the curve, there will be at least one moment in the journey when it becomes a tangent line to the graph. On my journey between Coolac and North Gundagai, you can see this occurred 5 times. At those moments, the speedometer of my car will be showing an instantaneous speed that agreed with the overall average of about 105 kilometres per hour. But if you take a series of snapshots at a cascade of moments, the tangent lines can have varying slopes, sometimes steeper and sometimes shallower than the average. It's the slopes of these tiny miniature tangent lines that become the speeds that are showing instant by instant on the speedometer. If your average speed exceeded 110, then you can be absolutely sure that at some moment your speedometer was showing a speed in excess of 110, which is the basis for receiving a fine. But if the average speed was less, there's no way of knowing for sure that the instantaneous speed was always less than 110. If you're used to glancing at speedometers, either as a driver or as a passenger, then you already have first-hand practical experience with derivatives, and we'll work towards formalising this later in the module. Today we discussed the average rate of change of a function defined on an interval, and saw how to interpret this in terms of the slope of a line joining the endpoints of the curve. This gives us information about how quantities change on average. We looked in detail at an example involving a car trip, interpreting the average rate of change in terms of average speeds over certain legs of the journey. When we start to think about instantaneous speeds or rates of change, such as what you see on the speedometer in a car, then we're well on the way to formalising the notion of a derivative. Please read the notes accompanying this video, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. In this video, we discussed displacement, velocity and acceleration, which are important specialised functions that use the quantity time as an input and have familiar physical interpretations. The relationships between displacement and velocity, and between velocity and acceleration, serve as prototypes for forming derivatives, the main theme of this module, and towards which we'll develop formal definitions in later videos. Displacement functions describe the position or distance an object has moved at any particular time. The last example in the previous video involved a displacement function, where we looked at distance travelled between Sydney and Melbourne as a function of time over an interval of about 11.5 hours. In that example, we looked at the average rate of change, which gave us the average velocity for the entire journey, being the slope of the line that joins the endpoints of the curve. We also introduced, without too much formalism, the idea of an instantaneous speed, which is what you see on the car's speedometer at any moment, and which is represented by the slope of a miniature tangent line attached to a point on the displacement curve. There were several places where the average speed for the whole trip must have appeared instantaneously on the car's speedometer. In examples so far, we follow conventions in using X to denote the input and Y to denote the output. It's common, however, when working with displacement functions to use t for time as the input variable and x to denote displacement, the output variable. This is one of the few instances in which we would use the symbol x as a dependent rather than as an independent variable. Consider a cannon positioned to fire directly upwards, and use an x-axis now to make measurements in the vertical direction. A cannonball is fired, and we watch its trajectory over 6 seconds. Its movement is subject to gravity, so the ball goes up and then comes down. We'll ignore things like air resistance. Here are all the snapshots spread out evenly on the page. We regard the aperture of the cannon at height 0 meters and draw a horizontal axis that denotes time passing. We also reposition the vertical axis so that the moment the cannon fires is regarded as time 0 seconds. Here's a table of values indicating the height x meters of the cannonball at time t seconds. Joining the points with a smooth curve in fact produces an inverted parabola, and there's a very good reason for this which we'll come to. Now the cannonball is slowing down under gravity, but is still rising for the first 3 seconds. We can work out the average velocity over these seconds, the slope of the line joining the points of the curve for t equals 0 and 3, and the answer turns out to be 17 meters per second. During the last 3 seconds, the cannonball just reaches its highest point and then is hurtling back down towards the Earth. The average velocity over these seconds turns out to be minus 13 meters per second. Note that the answer is negative because the cannonball is moving downwards and we're using upwards as positive. I was careful to use the word velocity rather than speed because velocity distinguishes between positive and negative directions. Now in fact, the table of values comes from an underlying formula which happens to be a quadratic function, x equals minus 5t squared plus 32t plus 3, and this turns out to be quite a good model of the physical reality. Now imagine there's a tiny speedometer on or inside the cannonball so that a tiny passenger can read the instantaneous velocity. The average velocity over the first 3 seconds was 17 meters per second. We can locate a miniature tangent line that just touches the curve, and at that moment, corresponding to that point, the tiny speedometer would show 17 meters per second. Similarly, for the last 3 seconds, there will be some moment when the cannonball is instantaneously travelling back to Earth at 13 meters per second. Now this works in general. Instantaneous velocities are represented by slopes of tangent lines anywhere on the curve, and of course the slopes can vary. For example, if we focus on this special point where the tangent line is horizontal, then the slope is 0. So the instantaneous velocity is 0, which is the moment where the cannonball stops moving, so is at the point of returning to Earth, and this corresponds to the apex of the parabola representing the displacement function. Because we have in fact a rule for the function, which turns out to be a quadratic, we can use the trick of completing the square to find out exactly where this apex occurs. You can carefully check the working. Here's the rule for x, now expressed in a very useful form. So we can read off the maximum, which is 271 divided by 5, or 54.2, which occurs when the square is 0, that is, t is equal to 32 divided by 10, or 3.2. Thus, after exactly 3.2 seconds have elapsed, the cannonball reaches a maximum height of 54.2 meters. Now we can go back to the original data and the graph that joins up the points and investigate the velocity of the cannonball as a function of time t, denoted by v. We can expand the table by adding a third row for v and try to figure out its values, that is, the instantaneous velocities of the cannonball at each of these points in time. Remember, the instantaneous velocity is the slope of the tangent to the curve at that point, and we can in principle use a diagram to find these slopes. For time t equals 0, the slope turns out to be 32, so v is 32 meters per second. For t equals 1, we find that the slope is 22, so v is 22 meters per second. And so on for t equals 2 and t equals 3. For t equals 4, 5 and 6, the slopes are negative and increasing in magnitude as the cannonball moves faster and faster as it falls back to Earth. Here's the displacement curve, which is a parabola. Let's plot the points for velocity from the table and join the points to form a smooth curve, which happens to be a straight line. In fact, v is equal to negative 10t plus 32. This follows from the data in the diagram, but later you'll learn a technique that enables you to deduce this algebraically from first principles. We can ask how the velocity changes, and in fact it decreases uniformly with time. Now, acceleration is the technical term used to capture the rate of change of velocity. In this example, the acceleration turns out to be negative and constant. Negative acceleration is also called deceleration. Write a for acceleration as a function of time t, And now we can add the graph for acceleration, and it's described by the constant function a equals minus 10. In this example, we have a quadratic for displacement, a linear function for velocity, and a constant function for acceleration. When we've developed some tools for calculus, you'll be able to derive the rules for v and a from the rule for x very quickly, and also armed with integration techniques from the last module of this course, given this rule for a, you'll be able to work backwards to get the rules for v and x. This is where the physics comes in. In fact, the deceleration of an object close to the Earth's surface, ignoring things like air resistance, may be regarded as constant, and it's about 9.8 meters per second. This is close to 10 meters per second used in this example. So what we described turns out to be a reasonable approximation of the true behaviour of this cannonball. What we did in this example generalises. Finding slopes of tangent lines takes displacement to velocity, and this also, in turn, takes velocity to acceleration. Our cannonball example was rather special in that the velocity and acceleration were a lot simpler than the displacement. But weird things can happen, and you might ask generally what lies beyond acceleration. Consider our cannonball again, but suppose it's attached by a very strong spring at the origin and bounces up and down vertically between 0, 1, 0, minus 1 and 0, just like the values of the sine function. What you're witnessing is something known as simple harmonic motion. If you plot the displacement curve, you'll discover it's in the shape of a sine curve. And its velocity curve, you'll discover, looks like a cosine curve. Its acceleration curve looks like the sine curve tipped upside down. So what comes next? What describes the instantaneous rate of change in acceleration? Engineers use the word jerk. Acceleration is related to forces acting on bodies, so if there are sudden changes in acceleration, then the associated forces change rapidly, as in the case with extreme rides in amusement parks, and there's much toing and froing or jerking. In this example, the jerk curve turns out to be the velocity curve upside down. So what comes next? What describes the instantaneous rate of change in jerk? The technical term is jounce. Amazingly, in our example, this becomes the original displacement function x equals x of t. Jounce is also called snap, so snap reproduces the original displacement curve. What's the instantaneous rate of change in snap? Physicists call it crackle. In the case of simple harmonic motion, crackle in fact coincides with velocity. So what's the instantaneous rate of change in crackle? Physicists call it pop, and this coincides with acceleration. We're now cycling through our original displacement, velocity and acceleration, and can continue reproducing these curves ad infinitum just by taking instantaneous rates of change, a truly remarkable phenomenon. So today we've looked in some detail at relationships between displacement, velocity and acceleration, and even mentioned briefly what happens beyond these. The direct link between displacement and velocity and acceleration is the concept of a derivative, which we're steadily working towards and which formalizes the technique of finding the slope of a tangent line at any given point on the curve. Please read the notes, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. In this video, we discuss how secants in geometry can be used to approximate slopes of tangent lines. Slopes of lines are just fractions involving the vertical rise divided by the horizontal run. The fractions associated with lines formed by secants happen to be linked to fractions associated with tangent lines by a natural limiting process. It's an amazing fact that under certain conditions we can understand and control the behaviour of approximations that occur, producing very precise outcomes. This leads us towards formal definitions of the derivative in terms of limits of fractions, which is the main theme of this module. The underlying idea of calculus is to use tangent lines to approximate smooth curves, which arise as graphs of sophisticated functions that model interesting phenomena. Lines, of course, use simple arithmetic, so if we can achieve this, then there's a substantial reduction in complexity, and we have the possibility of creating very powerful and wide-ranging tools. A tangent line typically just glances a curve at a single point of interest and acts as a good approximation to the curve near this point of intersection. There are cases where tangent lines actually cross the curve at the point of interest, but more about that later. Warning: not all curves are smooth, so might need special treatment. For example, this curve has a sharp point. This curve has a discontinuity where the curve breaks apart at some point. This curve also has a sharp point. In each case, there's some ambiguity about choosing an appropriate tangent line. The third curve is an interesting and important example, and the sharp point is known as a cusp. There is in fact a useful and meaningful tangent line for this cusp example, a vertical line that splits the cusp in the middle and even passes completely through the curve. Close to the cusp, this vertical line is a very good approximation to the behaviour of the curve on either side. In the previous video, we looked at a particular displacement curve associated with a cannonball fired directly upwards and eventually coming back down to Earth under the influence of gravity. The curve was in fact described by a quadratic equation. We looked at slopes of tangent lines in that example, and a linear function was produced that represented the velocity. This looked rather special, but in fact turns out to be typical of behaviour that occurs with all quadratic functions. To try to understand what's going on, let's carefully analyse the simplest quadratic of all, y equals x squared, and see if we can extract some general principles. Note that we're reverting to using x again as the independent variable and y the dependent variable. A typical point on the curve has coordinates x on the horizontal axis and x squared on the vertical axis. And we can draw a tangent line to the curve passing through this point. We can perturb the input x slightly, say by adding h, to get a new input x plus h, and then move up to the curve and across to the vertical axis to land at the value x plus h, all squared. Hence the new point on the curve has coordinates x plus h and x plus h, all squared. We can join these 2 points on the green curve with a straight line segment, coloured blue in the diagram. A line that joins 2 distinct points of a curve is called a secant in geometry. Because it's a line segment, this secant has a slope in the usual sense, that is, a vertical rise divided by a horizontal run. You can see that the horizontal run in the diagram is h, and there's no harm throughout this discussion in assuming that h is positive. The vertical rise in this diagram is the difference in the y-coordinates, namely x plus h squared minus x squared. We'll look at the quotient of these carefully in a moment. Note that as h is made smaller and smaller, approaching 0, without actually reaching 0, the slope of the secant approaches the slope of the tangent line, and it's conventional to use these arrows as abbreviations for the word approaches. To see this visually, imagine the second point slipping or sliding down the parabola towards the first point. Even though the secant gets shorter and shorter, the direction of the secant aligns more and more with the direction of the tangent line, so that their slopes look like they're going to coincide, and we think of them as actually coinciding in some kind of limit. Note that even though h approaches 0, it doesn't actually reach 0, as these diagrams require 2 distinct points in order to form a secant. If h were equal to 0, then there would be only 1 point on the curve, not 2. So, returning to the earlier diagram, with horizontal run h and vertical rise x plus h squared minus x squared, let's look at the quotient representing the slope of the secant. The numerator, representing the vertical rise, can be expanded, and then there's some cancellation. So the fraction becomes 2xh plus h squared divided by h, and the numerator factorises, and the h's cancel in the numerator and denominator, simplifying further to 2x plus h. As h gets closer and closer to 0, this expression, 2x plus h, for the slope of the secant, gets closer and closer to 2x. We regard 2x as the limit of this process of taking slopes of secants. So 2x represents the slope of the tangent line. We've derived this very important result that the slope of the tangent line to the parabola y equals x squared at the point with coordinates x and x squared is just twice x. Now if you go through the same process with y equals kx squared, where k is some fixed constant, then the previous calculation simply gets scaled by a factor of k, and we get the following result. The slope of the tangent line to the parabola y equals kx squared at the point with coordinates x and kx squared is just twice kx. We can now discover a surprising connection with areas of circles. Consider a circle of radius r. Its area, capital A, is given by the formula pi r squared. The perimeter, capital P, is given by the formula 2 pi r. That is twice pi r, which is precisely the slope of the tangent line to the parabola a equals pi r squared at the point with coordinates r and pi r squared, where we interpret our previous result using r for x, capital A for y, and pi for k. This isn't a coincidence, it's an instance of something quite profound in mathematics. Forming slopes of tangent lines is called differentiation. Finding areas of regions in the plane, like finding the area of a circle, is called integration. There's a remarkable connection between them, described in the last module of this course, called the fundamental theorem of calculus. Something as innocent looking as a simple relationship between slopes of tangent lines and areas of regions in the plane turns out to be one of the most transformative observations in the history of mathematics, and was first noticed by Newton and Leibniz in the 17th century. The idea behind the calculation we just did for y equals x squared generalizes to any smooth curve y equals f of x. Choose some point of interest with coordinates x on the horizontal axis and f of x on the vertical axis. Now attach a tangent line to the curve that passes through this point. Now perturb the input x slightly by adding h to get a new input, x plus h. The output corresponding to this new input is f of x plus h, marked on the vertical axis. We now join the 2 points on the curve to form this blue line segment, called a secant as before. In moving from the first point to the second new point, the horizontal run is h, and the vertical rise is f of x plus h minus f of x. So the slope of the secant is the quotient f of x plus h minus f of x divided by h. The slope of the tangent line is the limiting slope of the secant as h tends towards 0. You can see this visually. As a new point slides down the curve towards the original point, the secant gets shorter and shorter. But its slope gets more and more aligned with the slope of the tangent, and we think of it as actually reaching the slope of the tangent in the limit. We capture this idea using this limit notation. LIM is an abbreviation for limit, and together with h arrow 0 beneath, the full result reads: the slope of the tangent line is the limit as h approaches 0 of f of x plus h minus f of x over h. Whatever this limit evaluates to, representing the slope of the tangent line, is called the derivative of f at x. Now this technical expression involving limits has several equivalent formulations that we'll explore in later videos. It's quite astonishing, as you'll see, that we're able to calculate and control these limits precisely for so many important functions f. Today we considered in detail the process of taking the limiting slope of a secant to find an explicit formula for the slope of the tangent line to a parabola. The underlying method generalizes to any smooth function and is the basis for formal definitions of the derivative, which will be discussed and illustrated in detail in later videos. The idea has two main ingredients: forming slopes of line segments, which are special kinds of fractions, and then seeing what happens in the limit. Because of the importance of the notion of limits, we'll discuss them in more detail in the next two videos. Please read the notes, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. The expression stretched to the limit is apt in calculus. We push functions all the way to the boundaries of possibilities. The concept of a limit captures precisely the notion of accessing values that at first sight appear to be forbidden or out of bounds. In this video, we look at a range of phenomena that involve getting closer and closer to some kind of ideal point or value. We also make explicit some examples and notation involving infinities, which encapsulate the idea of being free to go on and on and on. How many times have we said ad infinitum in earlier videos? Slopes of tangent lines to curves are a prototype for this idea of an idealized value. Imagine you inhabit a typical smooth curve. It's your universe, and you're only able to access points on the curve to create secants. You might never be able to jump off the curve onto the tangent line, but the way the secants behave near the point of interest may be enough to tell you what's happening out there on the tangent line. In the last video, we demonstrated by pure thought and manipulation of symbols that the slopes of secants of the parabola y equals x squared approach the slope of the tangent line, which happens to be 2 times x at the point with input x, an amazing achievement. And we realized that the underlying method works for any smooth curve, leading to the notion of a limit in this notation. LIM is an abbreviation for limit, and refers to some limiting value or behaviour that is being approached. Let's discuss 2 similar looking but contrasting examples. f of x equals x squared minus 1 divided by x minus 1, and g of x equals x squared minus 2 divided by x minus 1. These are both examples of rational functions, ratios of polynomials. And in both these cases, x equals 1 creates a problem in the denominator, because trying to evaluate them with x equals 1 means dividing by 0, which is forbidden. Let's do some exploration for x close to 1. f of 1.1, you can check, evaluates to 2.1. f of 1.01 evaluates to 2.01. And f of 0.9999, taking an input very close to but just a tiny bit less than 1, evaluates to 1.9999. We seem to be getting closer and closer to 2 by taking our inputs closer and closer to 1. Now let's try the same thing using the rule for g, which at first sight appears to be only slightly different. g of 1.1, you can check, evaluates to negative 7.9. g of 1.01 evaluates to nearly negative 98, a largish negative number. And g of 0.9999 evaluates to over 10,000, a very large positive number. The behaviour of g for inputs near x equals 1 looks wild and unpredictable, compared with the apparently stable behaviour of f. Let's try to understand why the values of f appear to be converging to 2. In the rule for f, the numerator factorises as x plus 1 times x minus 1, and we get cancellation, and the entire fraction simplifies to x plus 1. Throughout, we're assuming that x doesn't equal 1. So the rule y equals f of x is almost exactly y equals x plus 1, the rule of a straight line. The only thing missing is a tiny hole where the rule for f prohibits an input of x equals 1. Observe that as x approaches 1 from either side, we slide up and down the line, approaching the hole, while at the same time the values of y approach 2 on the y-axis. We use limit notation and say the limit of f of x as x approaches 1 is 2, and this confirms what we anticipated from our exploration. So what about this wild function g? Let's try to simplify the fraction g of x by doing a long division of polynomials, dividing x minus 1 into x squared minus 2. In a few short steps, we have a quotient of x plus 1 and a remainder of minus 1. Hence the fraction g of x can be rewritten as the quotient x plus 1 plus the remainder minus 1 divided by x minus 1. Notice that the first part, x plus 1, is the rule for the line that we saw before in analysing f. We're also taking away a piece, 1 over x minus 1, which is the rule for a hyperbola. So the rule for g involves a line and a hyperbola. Let's focus on 1 over x minus 1, which is closely related to the simple hyperbola y equals 1 over x. To get the graph for y equals 1 over x minus 1, you translate the hyperbola for 1 over x to the right by 1 unit, and note that the line x equals 1 becomes the vertical asymptote. As x approaches 1 from above, using this arrow notation, with a little plus sign as a superscript, we see 1 over x minus 1 shoot off towards infinity, by which we mean getting arbitrarily large and positive. As x approaches 1 from below, but this time with a little minus sign as a superscript, we see 1 over x minus 1 shoot off towards minus infinity, by which we mean getting arbitrarily large and negative. So we have these two contrasting behaviours of 1 over x minus 1 expressed using limit notation and the infinity and minus infinity symbols, which is notation for getting arbitrarily large and positive or negative. Let's combine these with the overall rule for g. As x approaches 1 from above, x plus 1 approaches 1 plus 1 equals 2, which is straightforward, and 1 over x minus 1 becomes arbitrarily large and positive, so that when you take this away from something close to 2, we get something large and negative. And we capture this using limit notation. By contrast, as x approaches 1 from below, again x plus 1 approaches 2, but this time 1 over x minus 1 becomes arbitrarily large and negative. So that now when we take this away, we get something large and positive, and we capture this using limit notation. So we have these two concise descriptions of the behaviour of g of x as x approaches 1, either from above or below. But there's more information available from the hyperbola. As x gets large, positively or negatively, 1 over x minus 1 approaches 0. And we can see the overall effect on the rule for g of x. For large positive or negative x, g of x becomes approximately x plus 1, because the piece minus 1 on x minus 1 is close to 0. The rule for g becomes more and more identical to the rule for the line y equals x plus 1, the further you are away from the origin. Geometrically, that line becomes an oblique asymptote for the curve. We can visualize what happens. Here are the axes, the vertical line x equals 1 and the oblique line y equals x plus 1 dotted in. All of the asymptotic behaviour is captured by this green curve in two pieces or branches, which is the graph of y equals g of x. The line x equals 1 is the vertical asymptote, and the line y equals x plus 1 is the oblique asymptote, which becomes a better and better approximation of the curve the further you are away from the origin. You might be curious how we knew to draw it exactly like this, and why, for example, there are no wriggly bits or strange things happening in between the asymptotic behaviour. In the next module, we will be armed with techniques for curve sketching to determine very precisely the nature of curves like this one by exploiting the derivative and the second derivative. So let's return to both our examples f and g. The graph of f we saw was in fact a line, but with one point missing. As x approaches 1 from either side, f of x approaches 2, captured by this limit statement, and this confirmed our exploration. By contrast, now that we know about the graph of g, we can understand the wild fluctuations. Two statements using limits describe what happens as we approach 1 from either side, explaining the large positive and negative values that we saw. Then we have this other interesting phenomenon that as x gets large, either positively or negatively, the curve is approximated by the straight line y equals x plus 1, which forms an oblique asymptote. There are a number of important limits involving infinity symbols. If you take the simplest hyperbola, the graph of y equals 1 on x that we used earlier, then 1 on x approaches 0 as x gets arbitrarily large, positively or negatively, captured by these two statements in limit notation. And the x-axis becomes a horizontal asymptote. By contrast, if x approaches 0 from above, 1 on x gets arbitrarily large and positive, whilst if x approaches 0 from below, 1 on x gets arbitrarily large and negative, captured by these two statements in limit notation. And the y-axis becomes the vertical asymptote. If we look at the natural exponential function, we see that e to the x gets arbitrarily large and positive as x does, captured by this statement in limit notation. And notice that we're using the infinity symbol as a value for the limit, even though it's not a number. It's just notation and says that the values become arbitrarily large without bound. From the curve you can see, as x gets arbitrarily large and negative, the value of e to the x gets closer and closer to 0, captured by this limit statement. And the x-axis becomes a horizontal asymptote. The contrasting behaviours of e to the x as we move a long way from the origin in each direction are captured concisely by the limit notation. If we reflect this curve in the y-axis, we get the curve y equals e to the minus x. And we get the corresponding limit statements, which are mirror images of the first two. If we reflect the curve y equals e to the x in the line y equals x, then we invert the function and get the natural logarithm. As x gets large and positive, so does ln of x, but in fact very slowly. This is called logarithmic growth, in stark contrast to exponential growth. Instead of a rapid explosion, the natural logarithm grows at a snail's pace, and even then a very, very, almost unimaginably slow snail. Finally, we note that as x approaches 0 from above, ln of x gets arbitrarily large and negative, expressed using this one-sided limit, and the negative half of the y-axis becomes a vertical asymptote. We've introduced so many different ideas, all unified by the concept of a limit, which often captures or summarises some kind of ideal value or behaviour in the faraway distance, or involving getting arbitrarily close to some prohibited input. All of these can be expressed concisely using limit notation and various tricks, using infinity and minus infinity symbols to indicate getting arbitrarily large positively or negatively, and plus and minus symbols used as superscripts to indicate whether we're approaching something from the right or left, from above or below. We saw examples of rational functions where you can have, for example, a complicated looking rule reduced simply to a straight line with just one point missing, and by contrast, another function with almost the same rule but having much more complicated behaviour involving an oblique asymptote. Please read the notes, and when you're ready, please attempt the exercises. Thank you very much for watching, even if you are also stretched to the limits by all of this new material, and I look forward to seeing you again soon. In today's video, we'll discuss and illustrate several limit laws that enable you to combine simple or known limits to calculate or understand the behaviour of new limits that can arise and appear at first sight to be difficult or complicated. You'll become experts in no time. The first main collection of laws tells us that limits respect arithmetic. Arithmetic operations include addition, subtraction, multiplication and division, and these laws allow you to bring limits in sight, so to speak, any of these operations, provided all the components, as simpler limits, actually exist. The first law says that the limit of a sum is the sum of the limits. Symbolically, the limit of f of x plus g of x is the limit of f of x plus the limit of g of x. The second law says that the limit of a difference is the difference of the limits, expressed symbolically as before but with minus instead of plus. The third law says that the limit of a product is the product of the limits, expressed symbolically this way, now using multiplication. And it follows, as a special case, that the limit of a constant multiple is the constant multiple of the limits, expressed symbolically like this, where k is a constant. And we often say constants come out the front. The fourth law says that the limit of a quotient is the quotient of the limits, expressed symbolically like this, provided that at no stage are you dividing by 0. This last one is very important because we're often needing to deal with fractions in calculus, where the possibility of 0 as a denominator can become a serious and delicate issue. Notice that in describing these laws, I wasn't being explicit about what happens to x, in order to be general, to cover a range of possibilities. You can have x approaching some number a from either side, or approaching a number from the right or from the left, the so-called one-sided limits. We can also have x heading off towards infinity, by which we mean getting arbitrarily large and positive, or minus infinity, getting arbitrarily large and negative. There are a few basic building blocks, and you can combine them with the limit laws to progress very rapidly in many cases. Firstly, the limit of x as x approaches a is clearly just a. This is confirmed by looking at the graph of y equals x, which I've drawn, but made a tiny hole at x equals a, because we're interested in limiting behaviour as x approaches a, but doesn't necessarily actually reach a. As x approaches a on the horizontal axis, y equals x approaches a on the vertical axis. The limit of a constant c, regardless of what x is doing, is just the constant c. This is clear by looking at the graph of y equals c. Again, I've made a hole at x equals a. As x approaches a on the horizontal axis, y is stuck always on c on the vertical axis. If x gets very large and positive, or large and negative, then its reciprocal 1 on x tends to 0, so that the limit of 1 on x in both cases is equal to 0. This is clear from the graph, which is a hyperbola. As x moves further and further away from the origin in either direction, the value of y equals 1 on x gets closer and closer to 0. Let's look at some examples. Let's find the limit as x approaches 2 of 2x minus 1. By the second law, it becomes the difference of the limits of 2x and of 1 as x approaches 2, which becomes the limit of 2 multiplied by the limit of x, all take away 1, which quickly becomes 3. You can see the effect of this visually. The graph of y equals 2x minus 1 is just a straight line, and we place a hole in the line corresponding to 2 on the horizontal axis, which x is approaching. However, the hole lines up exactly with the value 3 on the y-axis, which is the limiting value of 2x minus 1. In this case, we can actually fill in the hole with x-coordinate 2 and y-coordinate being the limiting value as x approaches 2. As another example, the limit of x squared as x approaches minus 2 is, by a limit law, the square of the limit of x, which is minus 2 squared, which is 4. This also makes sense graphically. The graph is a parabola, and if we put a hole in the graph at minus 2 on the horizontal axis, which x is approaching, then the hole lines up exactly with 4 on the y-axis, the limiting value of x squared. Again, it's as though we can fill in the hole perfectly with x-coordinate minus 2 and y-coordinate being the limiting value as x approaches minus 2. The previous two examples were special cases of a general phenomenon. To find the limiting value of a polynomial, simply evaluate it at the input that x is approaching. This relates to a property called continuity, which we discuss in the next video. As a more elaborate example, consider the limit of this cubic polynomial as x approaches 1. Because the cubic is built up from x and constants by addition and multiplication, we can apply the limit laws to bring the limit inside the expression. And this has precisely the effect of evaluating the polynomial at x equals 1. Yielding in this case an answer of 2. We don't need to know what the graph actually looks like. In general, if p of x is any polynomial, then the limit of p of x as x approaches a is just p of a, the result of substituting a for x and evaluating the expression using simple arithmetic. Let's look at a more elaborate example involving a rational function, that is a quotient of two polynomials, and try to deduce some asymptotic behaviour by using the limit laws. Here's a very complicated expression. We want to see what happens as x goes to infinity. The leading terms in the numerator and denominator, involving x cubed, have been circled as they will dominate the expression as x gets large. The remaining bits and pieces involving lower powers of x start to look insignificant by comparison with the leading terms when x is large. In the limit, we expect the answer to be unchanged by simply throwing away these lower order insignificant pieces to get the limit of 3x cubed divided by 2x cubed. But then there's cancellation and we're just left with the limit of the constant 3 on 2, which is just 3 on 2. So for these heuristic reasons, we expect the answer to be 3 on 2. For a more thorough or careful analysis, we can do some algebraic manipulation first and then apply limit laws. The trick is to first divide through everything in the numerator and denominator by the highest power of x that appears, x cubed. This doesn't change the overall value of the expression. But by limit laws, we can bring the limit inside the expression and see what happens to each of the simple pieces that we have created. The constants 3 and 2 are unaffected, but each of the fractions with x, x squared and x cubed in the denominator have 0 as their limit as x gets arbitrarily large, and everything quickly becomes this expression which evaluates to 3 on 2, which is what we were expecting earlier for heuristic reasons. This tells us, in fact, that the horizontal line y equals 3 on 2 will be an asymptote to the curve for this particular rational function. We now discuss another important law that enables one to get information by making comparisons between known and unknown limits, aptly called the squeeze or sandwich law. If we have f of x sandwiched in between g of x and h of x, by which we mean g of x is less than or equal to f of x, which is less than or equal to h of x, for all x near x equals a, and the limits of g of x and h of x exist and are equal to L as x approaches a, then the limit of f of x also exists and equals this common limit L. Imagine a curve for g sitting beneath a curve for h, but they pinch together at some point, and the curve for f, even though possibly fluctuating wildly, is sandwiched in between, and the point where they all pinch together corresponds to x equals a and y equals L. Then all three limits exist and equal L as x approaches a. For example, let's use this squeezing idea to investigate the important but difficult limit sin x on x as x goes to 0. This limit is crucial later for developing the derivative of the sine function. Let's do some exploration first to get a feel for what we might expect. If you type in sin 1 divided by 1 in your calculator, you get about 0.84. Sin 0.1 divided by 0.1 is about 0.998. Sin 0.001 divided by 0.001 is really close to 1. As x gets closer to 0, the calculations suggest that sin x on x is getting closer to 1. So we suspect the limiting value is 1. Let's see if we can deduce this using general principles. Here's part of the unit circle with some angle in the first quadrant, and we've extended the radius to meet the tangent line that touches the unit circle at the point 1 on the horizontal axis. Suppose that the angle, measured in radians, is x, so that the arc length along the unit circle subtended by the angle is x. The point where the line extending the radius meets the tangent is at height tan x above the horizontal axis. Moving across from the point on the unit circle to the vertical axis produces the value sin x. Now we join the point on the unit circle to the point 1 on the horizontal axis, producing this short secant. And now extract this diagram involving two triangles and a wedge or sector from the unit circle sandwiched in between. If we shade in pink the smaller triangle, with base length 1 and height sin x, then we get an area of sin x on 2. If we shade in green the wedge or sector of the circle subtended by the angle x, then the area is the proportion, x over 2 pi, of the area of the whole unit circle, which is pi, giving an area of x on 2. If we shade in blue the area of the larger triangle that engulfs everything with base length 1 and height tan x, then we get an area of tan x on 2. If we compare the three areas, we get that the pink area is less than or equal to the green area, which is less than or equal to the blue area. Thus we get a sequence of inequalities. Sin x on 2 is less than or equal to x on 2, which is less than or equal to tan x on 2. So take this inequality and multiply through by 2 and rewrite tan x as sin x over cos x. Then divide everything through by sin x, retaining the inequalities because sin x is positive in our diagram. And then reciprocate everything, which reverses the inequalities, noting that everything is positive. Notice that sin x on x is squeezed or sandwiched in between 1 on the left and cos x on the right. But these values on the left and right both tend towards the same limit, 1, as x tends towards 0. This is obvious for 1 on the left, which is constant. For cos x on the right, you can perhaps visualize in your mind's eye the curve for cos x. And imagine as x moves towards 0, the value of cos x tends towards 1, producing a limiting value of 1. But sin x on x is sandwiched in the middle. So, by the squeeze law, has nowhere else to move but forced also to go to 1. This demonstrates that the limit of sin x on x as x approaches 0 is indeed 1 as we suspected. Note that this argument used angles in the first quadrant of the unit circle, so that x was approaching 0 from above. But the same argument can be adjusted to give the same result also if the angle is negative, that is, if x is approaching 0 from below. Let's do another example that looks similar using tan x instead over x. We don't need to go through an argument using the squeeze law again, but can just utilise the result for sin x over x. First write tan x as sin x over cos x, and then split the expression up into two factors, sin x on x multiplied by 1 on cos x, and then use the product and quotient limit laws to express this as the limit of the first factor, sin x on x, by the limit of the second factor, which in turn is 1 over the limit of cos x. But both of these limits are 1, so the expression quickly evaluates to 1. Let's do another example, making things slightly harder still, asking for the limit of tan 2x over x as x tends to 0. Observe that we can rewrite the fraction by multiplying the top and the bottom by 2, and then bringing the constant 2 in the numerator out the front. So this becomes 2 times the limit of tan x over 2x, which we can rewrite as tan y over y, by putting y equal to 2x. And notice that y tends to 0 as x tends to 0. But the limit of tan y on y, as y goes to 0, is just 1, our previous result, but using y instead of x. So we get 2 times 1, which is 2. We've made significant progress utilising limit laws to deal with some quite difficult and tricky limits. We discussed and illustrated how limits respect arithmetic operations, so that limits can be brought inside sums, differences, products and quotients, and how we can force certain limits using the squeeze limit law when some possibly wild expression is sandwiched in between two expressions that we can control and already know in advance converge to the same limit. We applied the squeeze limit law to deduce that sin x over x tends to 1 as x tends to 0, and used this to evaluate some limits involving the tan function. Please read the notes, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. In this video, we'll discuss and illustrate the important notion of continuity of a function. What can go wrong when discontinuities occur and how we handle them, including examples when we can fix things using removable discontinuities. A function is said to be continuous if the graph can be drawn, at least in principle, without lifting your pen off the paper. For example, the straight line y equals x in this diagram was drawn without lifting the pen. The line, of course, goes on forever, so one has to imagine, in principle, being able to draw as much as we like, back and forth, as far as we like, without ever needing to lift the pen. In fact, this works for any graph of a linear function. Here's the horizontal line, which is the graph of y equals k for some constant k, which again we can imagine drawing without lifting our pen off the paper. Here's the parabola y equals x squared, also continuous, and y equals sin x, which wriggles back and forth, forever, but continuously. And y equals e to the x, and y equal to the natural logarithm of x, all continuous functions. When we imagine drawing without lifting our pen, there are no holes or gaps, and the limiting values precisely fill in where your pen is supposed to move to, captured by the statement, the limit of f of x as x approaches a is the value of the function at a, namely f of a. And this has to work for every input x equal to a in the domain of the function. There are no surprise jumps or leaps, and you can think of any limiting behaviour of the function as coinciding with the actual value of the function. There are two main obstructions to continuity in practice. Firstly, we must consider denominators of fractions. We're not allowed to divide by 0, and so have to avoid values that cause the denominator of a fraction to be 0. The second main problem is when a function is defined piecewise, which means that there are two or more pieces in the description of the rule for the function, leading to two or more pieces of the curve, which have to match and join up at the endpoints, if we're to imagine drawing the combined curve without lifting our pen off the paper. Here's an example of a piecewise function that happens to be continuous. Consider the usual magnitude function, f of x equals the magnitude or absolute value of x, in fact defined in two pieces, as x if x is greater than or equal to 0, and minus x if x is less than 0. The graph is in a V-shape, formed by taking the line y equals x in the first quadrant of the plane and combining it with y equals minus x in the second quadrant. The two pieces of the curve join up, matching perfectly at the origin, and you can imagine drawing the V-shape without lifting your pen off the paper. By contrast, consider the following example, which turns out to be discontinuous, by which we mean that we'll be unable to draw the graph without lifting our pen off the paper. For this, we modify the previous example and consider the function with rule f of x equals x divided by the magnitude of x, which again can be described in pieces. When x is positive, the magnitude of x is x itself, so dividing x by x gives the value 1. When x is negative, the magnitude of x is minus x, so dividing x by minus x gives the value minus 1. The rule is undefined for x equals 0. Here's the graph of y equals f of x, which consists of two horizontal lines, one at height y equals 1 for x greater than 0, and another at height y equals minus 1 for x less than 0. Note that these two lines get arbitrarily close to the y-axis, but don't actually meet it. You can think of there being two holes on the y-axis, at y equals 1 and y equals minus 1. It won't make the overall curve continuous by filling in either of these holes. For x approaching 0 from above, from the positive right-hand side, the y values are stuck at plus 1, so the limit from the right is plus 1. By contrast, for x approaching 0 from below, from the negative left-hand side, the y values are stuck at minus 1, so the limit from the left is minus 1. We have these contrasting, one-sided limiting behaviours for x over the magnitude of x. We have a limit existing from the right as x tends to 0 from above, namely plus 1, and a limit existing from the left as x tends to 0 from below, namely minus 1. The overall two-sided limit does not exist if we allow x to approach 0 from both sides. There's no hope of filling in the holes to make the curve continuous so that you can draw it without lifting your pen off the paper. Recall that rational functions are ratios of polynomials of the general form y equals f of x equals p of x divided by q of x, where p of x and q of x are polynomials. Problematic behaviour occurs when denominators become 0, often, but not always, leading to asymptotes. Recall two contrasting examples from an earlier video, f of x equals x squared minus 1 divided by x minus 1, and g of x equals x squared minus 2 divided by x minus 1, both of which would have 0 denominator if x equals 1, so that the input x equals 1 is problematic, but in quite different ways. Recall we produced the graph of f, which turns out to be a line with a hole at the point 1, 2. And the graph of g, which turns out to have an oblique asymptote and a vertical asymptote passing through the x-axis at x equals 1. In the case of the function f, the rule becomes f of x equals x plus 1 for x not equal to 1, producing a line with just one point missing. If we fill in the hole, then we get a full continuous curve. We say that the discontinuity is removable. By contrast, if we look at the graph of g, no matter where we travel on the vertical asymptote corresponding to x equals 1, we cannot find an input that will join up the two branches of the curve. They always remain separated. We say that the discontinuity is not removable. I'd like to finish by describing one of the most famous and important examples of all that has a removable discontinuity. Recall that last time we carefully demonstrated using the squeeze limit law that the limit of sin x over x is equal to 1 as x tends to 0. Let's consider the function f of x equal to sin x over x, with domain the set of all non-zero real numbers. The rule is not defined for x equals 0 because of x in the denominator, but it's defined for all other real numbers x. Here is the graph of f. Note that there is a hole for x equals 0 because a rule is undefined there. Because of the wavy, periodic behaviour of sin x, we expect the curve to undulate forever to the right and left. However, the amplitudes of the undulations decrease the further we're away from the origin as the denominator x gets larger and larger. Multiplying by 1 on x has some kind of dampening effect on sin x. The graph also has perfect reflectional symmetry about the y-axis. It's an example of an even function, a concept that we'll talk about and use later in the course. As x approaches 0 from either side, y equal to sin x over x approaches 1. Because the limit exists as x approaches 0, we can fill in the hole and then adjust the rule for the function, which remains sin x over x for non-zero x, but now takes the value 1 in the special case when the input x is equal to 0. The discontinuity turns out to be removable, and we produce this beautiful, continuous, smooth curve. It's a famous curve that has many applications in areas of physics and engineering, such as signal analysis, acoustics, optics, and spectroscopy. Today we moved along at a very fast rate and included quite an advanced discussion about limits in the context now of continuity. We discussed the notion of a continuous function, whose graph we may think of as being drawn without lifting the pen off the paper. A property that can be defined in terms of limits, namely, that the limiting behaviour of the curve at any particular point actually takes the limiting value. We gave contrasting examples, some with a removable discontinuity at a particular point, where the limit exists, including the famous sin x on x curve, and cases where it's not possible to remove the discontinuity, including examples such as where the left and right limits exist but are not equal, and where there's a vertical asymptote for a rational function. Please read the notes, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. In this video, we formally define the derivative as a limit in two different but equivalent ways, and practice these definitions on the cubing function that takes x to x cubed. Recall from earlier videos that we looked at the notion of an average rate of change of a function over some interval of inputs, which is just the slope of the line joining the endpoints of the curve. Recall, for a displacement function, as a function of time, this produces the average velocity for the trip. If we imagine the time interval becoming shorter and shorter, in fact vanishingly small, recall that we get the instantaneous velocity, which is the idea behind what you see on your speedometer. And this is represented by the slope of the tangent line to the curve at the point of interest. Recall that we've seen this idea informally in an earlier video by constructing slopes of secants to curves and watching what happens as they get shorter and shorter. As the secants vanish away, the slopes of the secants get closer and closer to the slope of the tangent line. We think of them as reaching the slope of the tangent line in the limit, and we express this in limit notation. We take this now as the definition of the derivative of the function f given by the rule y equals f of x at the input x. The derivative of f at x, denoted by f dashed of x, is the limit, if it exists, as h tends to 0 of the quotient f of x plus h minus f of x divided by h. This represents the slope of the tangent line to the curve y equals f of x at the point with coordinates x, f of x. In the case that f of x equals x squared, the squaring function, recall that we calculated this limit in an earlier video. The derivative is 2x, so that f dashed x is 2 times x. Let's move from squares to cubes and consider the function y equals f of x that takes an input x to x cubed, and think about what the derivative might be. The graph of this function looks like this, with 180-degree rotational symmetry about the origin. It turns out to be an odd function, an important concept we discuss in detail later. Apart from being a lot steeper, this curve has an important distinguishing feature from the parabola that describes a squaring function. If you draw miniature tangent lines to the curve throughout, you'll discover that the tangent to the curve at the origin, which is just the x-axis in this case, crosses the curve. The origin becomes an inflection point for this curve, another important concept we'll discuss in detail in a later video. Already you can see that for that particular tangent line, the slope is 0, since it's just the x-axis, in fact, which is horizontal. But what about slopes of tangent lines in general for f of x equals x cubed? Well, let's work through the definition of the derivative and see what happens. Start off with the definition. F dashed of x is the limit as h goes to 0 of f of x plus h minus f of x over h, which in our case becomes a limit, as h goes to 0, of x plus h cubed minus x cubed over h. And the cube in the numerator expands, you can check, as x cubed plus 3x squared times h plus 3x times h squared plus h cubed minus x cubed. And we notice the x cubed and minus x cubed cancel out. So we get the limit, as h goes to 0, of 3x squared times h plus 3x times h squared plus h cubed all over h. And the numerator factorises as 3x squared plus 3x times h plus h squared times h. And we can cancel the h's in the numerator and denominator. And the whole thing simplifies to the limit, as h goes to 0, of 3x squared plus 3xh plus h squared. And there's no problem simply evaluating this expression for h equals 0, reducing quickly to 3x squared. This solves our original problem. The derivative of f of x equals x cubed is 3x squared. Recapping from an earlier video with this new notation, we've already seen that if f of x is x squared, then the derivative is 2x. And just now, that if f of x is x cubed, then the derivative is 3x squared. You can easily work through the details for f of x equals x to the fourth, though it takes a bit longer, and find that the derivative is 4x cubed. These are all instances of a general pattern. For f of x equals x to the n, for any exponent n, the derivative is n times x to the n minus 1. That is, the exponent falls down to the front, and you get a new exponent by subtracting 1. If you know about something called a binomial expansion, you can verify this directly already for any positive integer n from the definition of the derivative. When we've developed some general techniques for finding derivatives, this result will follow quite easily and works for any real exponent n, which is very nice indeed. There's an alternative limit definition of the derivative that comes about naturally by taking the average rate of change of a function over an interval and seeing what happens in the limit as the interval shrinks to nothing at the left-hand endpoint. Here's our typical curve, y equals f of x, defined at least over an interval from a to b, producing outputs f of a and f of b for the respective endpoints. And then we draw the secant joining the endpoints, which has slope f of b minus f of a over b minus a, and this is just the average rate of change. If we allow b to head towards a, then the secant lines up more and more in the direction of the tangent line to the curve at x equals a, so that its slope, the average rate of change, approaches the slope of the tangent line, which is just the derivative of the function at x equals a, denoted by f dashed of a. Thus we expect an alternative definition of the derivative, namely, f dashed of a equals the limit as b approaches a of f of b minus f of a over b minus a. Now this looks quite different to our original definition, so let's see if we can recover the original definition by rearranging this formula somehow. Put h equal to b minus a, because we want to get h in the denominator. And put x equal to a, because we want x in the game. Observe that b is just a plus h, which is x plus h, since x equals a, and h, the difference between a and b, tends to 0 as b gets closer and closer to a. So the derivative of f at x, which is called f dashed of x, is just f dashed of a, since x equals a, which, feeding in our new alternative definition in the box above, is the limit as b approaches a of f of b minus f of a over b minus a. But b is x plus h, a is x, b minus a is h, and b tends to a as h tends to 0. So we can rewrite this as a limit as h tends to 0 of f of x plus h minus f of x all over h. And we recover our original definition of the derivative that we introduced earlier in this video. So everything is working nicely as expected. Let's revisit the derivative of the cubing function, but using this alternative definition. The definition is in terms of f dashed of a, and says that we take the limit as b approaches a of f of b minus f of a divided by b minus a. But f of b is b cubed, and f of a is a cubed. Now there's a beautiful factorization of the difference of two cubes, which you can check if you've not seen it before. B cubed minus a cubed is b minus a times b squared plus ba plus a squared. So we get cancellation of the factor b minus a in the numerator with the b minus a in the denominator, so that it reduces to finding the limit as b goes to a of b squared plus ba plus a squared, which becomes straightforward evaluation, replacing a by b to get a squared plus a squared plus a squared, which is 3a squared. This shows that f dashed of a equals 3a squared. If we revert to using x instead of a, we get f dashed of x is 3x squared. Exactly what we obtained using the original definition, which is very pleasing. Today we see that many ideas that we've encountered previously are all coming together using the unifying concept of a limit. We define the derivative to be the slope of the tangent line to a curve, which has two quite natural and equivalent formulae in terms of limits. We use both of these formulae to find the derivative of the function that takes x to x cubed, and the answer turns out to be 3x squared. In later videos, we'll apply these limit formulae for the derivative to other important functions, and then in the next module, develop some general techniques and principles that enable one to find swathes of derivatives easily and quickly in a variety of different settings. Please read the notes, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. In this video, we use the limit definition to rapidly expand our repertoire of derivatives. The process of taking derivatives of functions is called differentiation. We discuss the additivity of the derivative and how that applies in particular to provide simple rules for differentiating polynomials. We explain why the natural exponential function replicates itself under differentiation, and sketch a proof that the derivative of the sine function is the cosine function. We gave a definition of the derivative in terms of limits last time. Let y equal f of x be the rule for a function f. Remember, we defined the derivative of f at x, denoted by f dashed of x, to be the limit as h tends to 0 of f of x plus h minus f of x divided by h. Recall, this limit formula captures precisely the value of the slope of the tangent line to the curve at the point of interest. And by now you're probably starting to picture this phenomenon in your mind's eye, and the idea of the limiting slope of secants. We've already applied this formula to discover that if f of x is x squared, then the derivative is 2x, and if f of x is x cubed, then the derivative is 3x squared. More generally, if f of x is x to the n, then the derivative is nx to the n minus 1. The simplest functions to differentiate quickly are the linear functions, with rules of the form f of x equals ax plus b, where a and b are constants, whose graphs are just straight lines. If you reflect for a moment, the only reasonable way for a given straight line to be approximated by a tangent line is to take the line itself, and the approximation is so good they match perfectly. In other words, a straight line coincides with its tangent line at every point, and has slope a, so that the derivative must be just a. You can check yourself this follows also quickly from the limit definition. So f of x equals ax plus b implies that f dash of x equals a. In particular, if a is equal to 0, so that f of x equals b is a constant function, then the derivative is 0. And if f of x equals x, then the derivative is 1. The derivative is additive, by which we mean that if f of x is the sum of two rules, u of x and v of x, then the derivative of f is the sum of the derivatives of u and v. And constants come out the front, in the sense that if f of x is k times g of x, where k is a constant, then the derivative of f is just k times the derivative of g. These follow easily from the corresponding properties of limits, and details are given in the notes. It's now straightforward to differentiate any polynomial. You differentiate any power of x you see, multiply through by any constants you see, and add everything up. For example, let f of x be this polynomial of degree 4. Then the derivative is formed first by differentiating x to the fourth, which is 4x cubed. Then move on to the next term involving x cubed, so you subtract 2 times 3x squared. Then move on to the next term involving x squared, so you add 5 times 2x. Then move on to the next term involving x, so you subtract 3 times 1. And finally move on to the constant term, whose derivative is 0, and add everything up to get this cubic. And with some practice, you'll go immediately to this last step. Notice that differentiating a polynomial decreases its degree by 1, so we can always make a polynomial disappear if we differentiate it often enough. For example, suppose f of x is this quadratic, then the derivative is this linear function. If we differentiate again, we get what's called the second derivative, which in this case is the constant 6. If we differentiate yet again, we get what is called the third derivative, which in this case is 0. Differentiating 3 times makes this quadratic disappear, and that's true for any quadratic. If you take a polynomial of degree n and differentiate it n plus 1 times, then it disappears. Next, we'll look at a function that turns out to be indestructible with respect to differentiation. Consider the function y equals e to the x. Recall from an earlier video that the tangent line to its curve at the y-intercept has slope 1. The base is Euler's number e, and it's chosen deliberately so that this property holds. We want to transform this fact into a very specific limit. Let's have a look at the curve for x close to 0. If we input x equals h, some small positive real number, and move up to the curve, then we have the value e to the h on the y-axis. Now draw a secant that joins the curve's y-intercept to this point on the curve. The slope of this secant is the vertical rise e to the h minus 1 over the horizontal run h. As h tends to 0, this slope tends to the slope of the tangent line, which is 1. Thus, the limit, as h tends to 0, of e to the h minus 1 over h is just 1. This innocuous-looking limit is very special, and in fact, the foundation for the central role Euler's number e plays in mathematics. Now let's prove the following. That f of x equal to e to the x, we claim that the derivative is just e to the x. Here's the proof. First write f dashed x using the limit definition. The numerator inside the limit then becomes e to the x plus h minus e to the x. But e to the x plus h can be rewritten as e to the x times e to the h by applying an exponential law. And then this new numerator factorizes as e to the x outside e to the h minus 1. But e to the x doesn't involve h at all, so it's like a constant that can come out the front of the limit. So we get e to the x times the limit as h tends to 0 of e to the h minus 1 over h. But this is the special limit we identified before, which evaluates to 1. So the whole expression becomes e to the x times 1, which is just e to the x. And the claim is proved. This is an amazing fact. This function reproduces itself upon differentiation. No matter how many times you differentiate it, the function remains perfectly and obstinately intact. The circular functions, y equals sine x and y equals cos x, form a pair of indestructible functions from the point of view of differentiation in an interesting, roundabout way, as you'll soon see. We claim that the derivative of sine x is cos x. I'm going to sketch a proof. This will be quite an advanced mathematical argument. If you don't follow all the detail, don't worry. I'll first try to convince you visually that the claim seems plausible. Here's a graph of y equals sine x, and directly beneath it we've drawn the graph of y equals cos x. Here are points on the sine curve where the tangent lines are horizontal, having slope equal to 0. And notice that cos x takes the value 0 for exactly the same inputs. Let's also focus on points where the tangent lines of y equals sine x have slope plus 1. And notice that cos x takes the value plus 1 for exactly the same inputs. Finally, focus on points where the tangent lines of y equals sine x have slope negative 1. And notice that cos x takes the value negative 1 for exactly the same inputs. So our claim is looking plausible based on these samples of points. Now we're going to sketch a proof of this claim, and there's more detail in the notes. As preparation for the proof, let's first look more carefully at the tangent to the sine curve at the origin and ask for its slope, which looks like it should be 1. Take a point on the curve and form the secant that joins the origin to this point. The horizontal run is some number h, say, whilst the vertical rise becomes sine of h. So the slope of this secant is sine h over h. So the slope of the tangent line is just the limit of this expression as h tends to 0. But we calculated this limit in an earlier video using the squeeze theorem, with x used instead of h, and the answer is 1. This confirms that the slope of the tangent to the sine curve at the origin is 1. Let's also look at the tangent to the cosine curve at x equals 0. Because the cosine curve turns around at that point, the tangent is horizontal, so must have slope 0. Let's interpret this as a limit. Join the point at the apex on the y-axis at y equals 1 to some other point on the curve, forming a secant. The new point has coordinates h, say, on the x-axis and cos h on the y-axis. The secant is sloping downwards. In moving along this secant, the horizontal run is h, whilst the vertical rise is actually a decline of 1 minus cos h units. So cos h minus 1 is negative, and if we divide it by h, we get the negative slope of the secant. We have 0 being the slope of the tangent line, which is also the limit as h goes to 0 of the slopes of the secants. We have that the limit as h goes to 0 of cos of h minus 1 over h is 0. Thus we have two particular limit formulae, one involving sine and the other involving cosine. There's also an identity from advanced trigonometry that we want to use. A derivation is given in the notes if you want to read about it later. It says, to take the sine of a sum of angles alpha and beta, you multiply sine of alpha by cos of beta and add cos of alpha times sine of beta. We now sketch a proof that the derivative of sine x is cos x. Start off with the definition of the derivative, and this becomes the limit as h tends to 0 of sine x plus h minus sine x all over h. At this point, we rewrite the numerator using the advanced trigger density we mentioned a moment ago, with angles x and h taking the place of alpha and beta. We now strategically reorganize the components of the numerator and then use the fact that the limit of a sum is the sum of the limits to split this into two pieces. In the numerator of the first limit, we take out a common factor of sine x, and in the second limit, we have a factor of cos x, which behaves like a constant, so it can come out the front. But now, in the first piece, sin x is behaving like a constant, so it can come out the front. The first piece is just sin x times 0, and the second piece is just cos x times 1, using the two limits from before, and the whole thing simplifies to cos x, which finally proves our claim. What's the derivative of cos x? The answer turns out to be negative sin x. You can convince yourself by looking at graphs, thinking about tangents to the cosine curve, and checking against corresponding points on the negative sine curve. A rigorous derivation using the limit definition appears in the notes. You're probably curious to know about the derivative of tan x. You're not likely to guess the answer. It's in fact the reciprocal of the square of cos x. You'll have to wait for a future video to see why. We showed before that the derivative of e to the x is e to the x. We've just shown that the derivative of sin x is cos x, and mentioned that the derivative of cos x is minus sin x. This means that the circular functions are indestructible in the following sense. If f of x is sin x, then the derivative is cos x. So its derivative, the second derivative, is negative sin x. So its derivative, the third derivative, is negative cos x. So its derivative, the fourth derivative, quickly becomes sin x, and we're back to where we started. Differentiating ad infinitum just reproduces the same cycle of functions over and over again, forever. Recall in an earlier video we mentioned simple harmonic motion as an example of a displacement function which happens to be the sine curve. Its derivative, the velocity, is the cosine curve. Its second derivative, the acceleration, is the negative sine curve. Its third derivative, the jerk, is the negative cosine curve. Its fourth derivative, the snap, is the original sine curve, and the process goes on forever, reproducing these four curves by differentiation. Today we've really come a long way using the limit definition to rapidly expand our repertoire. We discussed and illustrated simple rules for differentiating polynomials, and noted that by differentiating often enough we can make a polynomial disappear in the sense of going to zero. We explained why the natural exponential function reproduces a perfect copy of itself under differentiation, so is in a certain sense indestructible. Sketched a proof that the derivative of sine is cosine, and mentioned that the derivative of cosine is negative sine, leading to an indestructible sequence of functions, sine, cosine, negative sine and negative cosine, that reproduces itself forever under differentiation. Please read the notes, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. In earlier videos, we've introduced and developed the limit definition of the derivative, formally expressed in the notation of functions, so that if f is a function, then the derivative of f of x with respect to x is denoted by f dash of x, with a dash as a superscript. In today's video, we introduce and apply a very commonly used notation of the derivative called dy dx that looks like a fraction and is known as Leibniz notation. In fact, dy dx is still, formally speaking, a limit, but the idea of thinking of the derivative as a fraction and deliberately using notation as a fraction goes back to the pioneering work of Gottfried Leibniz, one of the founders, in parallel to Isaac Newton, of calculus in the 17th century, and after whom this notation is named. Leibniz thought in terms of very powerful underlying heuristics. He considered the derivative to be a fraction involving infinitesimals, which are idealized, infinitely small numbers that interact using an arithmetic that extends that of the real number system. His notation was so carefully chosen that it has survived intact for hundreds of years. It's interesting that Leibniz's number system wasn't placed on a formal, rigorous footing until the 1960s, which is not so long ago. If you want to read more about this fascinating topic, you can look up terms on the internet such as non-standard analysis or the hyperreal number system. We begin by revisiting a familiar diagram intended to represent a general curve y equals f of x and a point of interest with coordinates x, f of x, and a tangent line to the curve at that point, and a nearby point with coordinates x plus h, f of x plus h. We connect the 2 points with a straight line segment called a secant. The horizontal run is h, and the vertical rise is f of x plus h minus f of x. We think of adding h to x as a slight variation or perturbation of the input, and we introduce some new notation and give h the name delta x. Delta being the Greek capital letter corresponding to the Latin d, and think of delta for difference. So delta x equal to h is the difference in the x-coordinate, and we may simply say difference in x or change in x. As we perturb the x-coordinate, this induces a perturbation in the y-coordinate, and the change in effect in the vertical direction, f of x plus h minus f of x, we may now rename delta y, and simply say difference in y or change in y. The slope of the secant that we recognised before as f of x plus h minus f of x over h now becomes, using this notation, delta y over delta x, the change in y over the change in x. The slope of the tangent line that we recognised as the limiting slope of the secant can now be expressed using this new notation as the limit as delta x goes to 0 of delta y divided by delta x. We can now rewrite the limit definition of the derivative of y equals f of x, equivalently as the limit as delta x goes to 0 of delta y divided by delta x. And this has a very beautiful notational abbreviation, dy over dx, just spoken dy dx, and called Leibniz notation, in honour of Gottfried Leibniz. Informally, in the limit, you can think of the Greek delta x turning into the Latin lowercase dx, and the Greek delta y turning into the Latin lowercase dy. Leibniz thought of dx and dy as idealized mathematical objects, representing some kind of infinitely small numbers that had their own arithmetic that paralleled the arithmetic of the real numbers. In modern terminology, dx and dy are called differentials. They become very useful heuristic devices, both in applications and also later in the final module when we manipulate integrals. Let's revisit some earlier examples, but interpreted or expressed using Leibniz notation. First, if y equals k is a constant function, then the graph is a horizontal line with no change in the y value, giving slope 0 everywhere. So dy dx is 0. Next, if y equals mx plus k is a linear function, where m is the slope and k is the y-intercept, then y changes m units uniformly for each unit that x changes. So dy dx is the constant m. We've noted previously that the derivative is additive, which means that the derivative of a sum is the sum of the derivatives. For example, if y is a quadratic function in x, say ax squared plus bx plus c, where a, b and c are constants, then dy dx is the sum of the derivatives of each of the pieces, which can be expressed in this way. So the derivative of ax squared, regarded as the rule for the function that takes x to ax squared, can be rewritten as d dx of ax squared, which is 2ax. The derivative of bx can be written as d dx of bx, which is b, and the derivative of the constant function c can be rewritten as d dx of c, which is 0. And the entire derivative simplifies to 2ax plus b. We mentioned in general that the derivative of x to the n is n x to the n minus 1 for any fixed exponent n. We carefully proved that the derivative of e to the x is e to the x, reproducing itself exactly under differentiation. Notice that the variable x is the exponent. It's a common error by students to confuse the exponential rule for differentiation with the previous rule and guess that the answer for the derivative of e to the x should be the result of bringing the exponent x down to the front and then creating a new exponent by subtracting 1, which is completely wrong and off track. This is a subtle error and the result of confusing the contrasting roles of the variable x used in building power functions, where x is a base, and exponential functions, where x is an exponent. We sketched a proof that the derivative of sin x is cos x, and mentioned that the derivative of cos x is minus sin x. Good notation can be amazingly transformative. You might recall we developed the quadratic formula, really from scratch, and though the derivation at the time took quite a few lines and some tricks, it was relatively painless using algebraic notation. Imagine as a medieval mathematician, without our notation, trying to express everything in mixtures of words and hybrids of symbols, and trying to avoid any heresies associated with using negative numbers. Leibniz notation, dy dx, is truly a miracle of inventiveness, so simple yet so powerful. It places emphasis on the roles of the variables x and y, where the differential associated with x appears in the denominator as some kind of fraction and the differential dy in the numerator. These distinctions are invisible or opaque in the function notation f-x for the derivative. If one wants to reverse the roles of the variables x and y, it makes perfectly good sense using Leibniz notation to tip dy dx upside down. That is, form dx dy, interchanging the differentials in the numerator and the denominator. And if these were ordinary fractions, the effect would be to form the reciprocal. This equation, dx dy equals the reciprocal of dy dx, is an irresistible deduction from the notation and intuition of Leibniz, and turns out to be a theorem about derivatives of inverse functions. Interchanging the roles of x and y, of input and output, has the effect of inverting the original function. So this formula tells us how to differentiate the inverse function. It becomes a non-trivial and useful theorem about derivatives. Why is it useful? Let's use this idea to find the derivative of the natural logarithm function, knowing that it's the inverse of the natural exponential function. Start off with y equals e to the x, for which we already know the derivative, which is e to the x. We want information about the inverse function, so tip the derivative upside down, which both reverses the roles of x and y and also reciprocates the derivative dy dx of the original exponential function. But this is just 1 over e to the x, which is 1 over y. But y is e to the x, so undoing this gives x equals the natural logarithm of y. So saying that dx dy equals 1 over y is the same as saying d dy of log of y is 1 over y. We now revert back to using x as the symbol for the input. And we get that the derivative of log of x with respect to x is the reciprocal of x. Amazing, such a simple and elegant answer. The formula makes sense visually. Here are the familiar natural logarithm and exponential functions on the same diagram, and we get from one to the other by reflecting in the line y equals x. Euler's number e was chosen so that the slope of the tangent to the curve y equals e to the x of the y-intercept is 1. So this tangent is parallel to the line y equals x. When you do the reflected tangent line, now touching the curve y equals log x at the x-intercept, retains the same slope. Both of these tangent lines have slope 1. Of course, 1 is 1 over 1, so this matches the formula for the derivative of log of x. You can visualize the tangent to the curve at x equals 2, and if your diagram is accurate, you will see that it has a slope of 1/2, also matching the formula for the derivative. We can do the same thing for x equals 3 and get a slope of 1/3, and anywhere on the x-axis you'll find the slope of the tangent to the curve is the reciprocal of x. Let's try this idea, tipping the Leibniz derivative upside down, to differentiate the square root function. Start off with the squaring function y equals x squared and focus on x greater than or equal to 0 so that x is just the square root of y. We know the derivative of y with respect to x is just 2x, and this is 2 times the square root of y. We now form dx dy, which is the reciprocal of dy dx, which becomes 1 over 2 times the square root of y. But dx dy is just d dy of the square root of y, so we can express everything in terms of y. We now revert to using the symbol x as a typical input, so that d dx of the square root of x is 1 over 2 times the square root of x. And so we discover that to differentiate the square root of x, you just double it and reciprocate. Not something you're ever likely to guess. We can relate this to fractional powers because the square root of x is just x to the power of 1/2. This rule for differentiation then becomes d dx of x to the power of 1/2 is 1 over 2 times x to the power of 1/2. But note that this can be rewritten as 1/2 of x to the power of minus 1/2. And so we get this nice formula. Note that this matches precisely the formula that we've mentioned before for the derivative of x to the n, where n equals 1/2. Let's finish by differentiating the cube root function using this inversion trick. Put y equals x cubed, so x becomes the cube root of y. But we proved a while ago that dy dx is 3x squared, which becomes 3 times the square of y to the third, which is 3 times y to the 2/3. So, flipping the derivative over, we get dx dy is 1 over 3 times y to the 2/3, which can be rewritten as 1/3 of y to the minus 2/3. At the same time, dx dy is just dy of y to the 1/3. Reverting to x as a typical input, we get d dx of x to the 1/3 is 1/3 of x to the minus 2/3. Happily, this is consistent with the formula for the derivative of x to the n when n equals 1/3, so everything is working nicely. In today's video, we introduced and practiced the Leibniz notation for the derivative called dy dx, which appears as a fraction involving the differentials dx and dy. Even though the derivative is formally defined as a limit of fractions, thinking of it as behaving like a fraction in its own right turns out to be very useful, especially for applications and for making heuristic leaps of the imagination. One such leap is to invert dy dx to get dx dy, which then can be used to get information about the derivative of the associated inverse function. We exploited this trick to discover that the derivative of the natural logarithm function is the reciprocal function, and also to differentiate the square root and cube root functions. Please read the notes, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. In the previous video, we introduced Leibniz notation, which expresses the derivative in the form of a ratio of differentials. In this video, we discussed some contrasting applications by interpreting differentials as small changes in the respective variables. This is closely related to the tangent line approximation of the curve near any particular point of interest. In our first example, we take a square and consider the increase in area as we change the width slightly. Here we've drawn a square of width 100 metres and coloured in the area in blue. Let A denote the area of a square of side length x, so A equals x squared. The value of A when x equals 100 is 10,000, so this square has area 10,000 square metres. How does the area change if we increase the width by, say, 10 metres, or 5 metres, or 1 metre, or 1 centimetre? In the first case, we expand the width by 10 metres to become 110 metres. We've shaded in pink the new extra area, which is the area of the larger square minus the area of the original square. And you can check this is exactly 2,100 square metres. In the second case, we expand the width now only by 5 metres to become 105 metres. And we can calculate this extra pink area to be exactly 1,025 square metres. In the third case, we expand the width by just 1 metre to become 101 metres, and the extra area becomes exactly 201 square metres. In the fourth case, we expand the width by a minuscule 1 centimetre, that is 0.01 metres, and the extra area turns out to be 2.0001 square metres. Though the exact calculations are not difficult in this example, I want to show you how you can exploit Leibniz notation for the derivative to get fast and perhaps surprisingly accurate estimates for these extra areas. We have this function a equals x squared. The derivative of a with respect to x is just 2x. The trick is to treat the differentials dA and dx like numbers, and dA dx like an ordinary fraction. so that multiplying through by dx, we get dA equals 2x dx, which we think of as an equation involving differentials. This is an idealized form of an approximation, namely, delta A is approximately equal to 2x delta x. This gives us a good approximation formula for the change in area, delta A, in terms of x, and delta x, the change in the width x. This says that the change in the area of a square is approximately 2 times the width times the change in the width. In our example with the blue square, x equals 100 metres. In case 1, the change in x is 10 metres, so the formula for the change in area gives approximately 2,000 square metres. In case 2, the change in x is 5 metres, and the formula gives change in area approximately 1,000 square metres. In case 3, delta x is 1, and delta A is approximately 200 square metres. In case 4, delta x is 0.01, and delta A is approximately 2 square metres. We can compare these estimates with the true increases in area in each of the 4 cases. And one can see that the estimates are quite close to the true increases. And in fact, the quality of the estimates improves as the change in x gets smaller and smaller. The changes in area themselves get smaller, but the proportional error in the estimates gets vanishingly small as delta x tends towards 0. This is related to the underlying idea of tangent lines used to approximate curves, which motivates the definition of the derivative. In this particular example, there's also a clear visual explanation of why the estimate should be so good. Take a general square of side length x and add a small change in x to the width, to form a slightly larger square of width x plus delta x. Colour the original square blue and the oblong areas pink. There is a new, much smaller square, coloured beige in the diagram, that makes up the corner. The area of the larger square is x plus delta x, all squared, which we can expand out. The part of this expansion, 2x times delta x, is in fact the formula for the estimate of increase that we obtained by considering differentials before, which is the result of combining the 2 pink-coloured areas. The last part of the expansion, delta x all squared, is the area of the tiny beige square, and it's exactly the error in our estimates. As delta x tends towards 0, this beige square vanishes out of sight, becoming insignificant compared to the pink areas, and the quality of the approximation improves towards perfect agreement. The next example is an application of differentials to estimate changes in volume of a sphere. Suppose you manufacture metal ball bearings in the shape of hopefully close to perfect spheres of radius 5 millimeters. However, your manufacturing process is not perfect, and you expect up to about 2% error in the true radius of any particular ball bearing. Our problem is to estimate the percentage error in the volume of metal required to manufacture these ball bearings. Let V be the volume of a sphere of radius r. It's a fact, and also follows from methods we learn in the final module on integral calculus, that V is 4/3 pi r cubed. Let's differentiate V regarded as a function of r. The 4/3 pi is a constant that can come out the front of the derivative of r cubed. Remember, the derivative of x cubed with respect to x is 3x squared. So using r instead of x, the derivative of r cubed with respect to r is 3r squared. Hence dv dr simplifies quickly to 4 pi r squared. Multiplying through by the differential dr gives dv equals 4 pi r squared dr, which we can interpret as an equation involving differentials, which is really an idealization of an approximation involving changes in v and r. Delta v is approximately 4 pi r squared delta r, where delta v is the change in v propagated by delta r, a small change in r. In our application, V represents the volume of a ball bearing of radius r equals 5 millimeters, and we're told to expect up to 2% error in the radius. Here's all the information so far. Delta r may be positive or negative, depending on whether the actual radius is a bit more or a bit less than 5 millimeters. We can ignore the sign by taking the absolute value, and then the information about the percentage error is really saying that the proportion, the magnitude of delta r divided by r, is less than or equal to 0.02. we're working towards estimating the percentage error in the volume. So we really want the proportion of the volume V represented by the magnitude of the change in volume, delta V. Thus we want to estimate the fraction, the magnitude of delta V, divided by V. Here's a summary of what we now have and what we're looking for. We just have to put the pieces together. The magnitude of delta V over V is approximately this expression, and the numerator can be rewritten as 4 pi r squared outside of the magnitude of delta R, because r squared is positive. And then there are some cancellations, and everything simplifies to 3 times the magnitude of delta R over R, which must be less than or equal to 3 times 0.02, which is 0.06. Thus we have the fraction, the magnitude of delta V over V, is approximately less than or equal to 0.06. And we therefore expect up to about 6% variation in the volume of the ball bearings. It's worth noting that the mathematics shows that this estimate is independent of the size of the ball bearings. This method only makes an approximate prediction when translating differentials into actual changes in the variables. Because the percentage error, 2%, was small, we expect the approximation to be quite good. In the next example, we apply differentials to estimate cube roots and also interpret our answers in terms of a tangent line to the cube root curve. Let's estimate some cube roots close to the cube root of 64, which is 4, say the cube roots of 70, 65 and 63. These numbers are all in the vicinity of 64, whose cube root is exactly 4, so expect to get cube roots in the vicinity of 4. Note that cube roots are fractional powers with exponent 1/3, so we consider the function y equals f of x equals x to the third. Then the derivative we saw last time is a third x to the minus 2/3. Multiplying through by dx, this becomes an equation involving differentials, which may be interpreted as the following approximation involving changes in y and x. Delta y is approximately equal to a third x to the minus 2/3 times delta x. In our particular problem, all the values of x are in the vicinity of 64. So in forming this approximation, we take x equal to 64, so that y equals its cube root, which is 4. And the approximation for delta y simplifies in a few steps to delta x divided by 48. Now 48 is close to 50, so we can approximate delta y even more coarsely by delta x over 50 if we want to. Of course, delta over 48 is more accurate, but delta x on 50 might produce simpler, rounder numbers if we're only looking for rough approximations. We have all the information we need to start making approximations. Let's estimate the cube root of 70. To move from 64 to 70, delta x, the change in x, is 6. So delta y should be approximately 6 divided by 50, which is equal to 0.12. The cube root of 70, which is y, plus a change in y, delta y, will be approximately 4 plus 0.12, which is 4.12. The cube root of 70, in fact, has this decimal expansion, so our rough and ready approximation is correct to 2 decimal places. We estimate the cube root of 65 using the same manipulations, but delta x now becomes 1, and delta y is approximately 1 divided by 50, which is equal to 0.02. So the cube root of 65, which is y plus delta y, now becomes 4 plus 0.02, which is 4.02. The true value again agrees with the approximation to 2 decimal places. If we use the more accurate estimate for delta y, that is delta x over 48, then our approximation for the cube root of 65 becomes more refined, which astonishingly agrees to the true value to almost 4 decimal places. Finally, estimating the cube root of 63, this time delta x is negative 1, because to change from 64 to 63, we must take away 1 unit, and now delta y is approximately negative 1 over 50, which is negative 0.02. So the cube root of 63 is approximately 4 minus 0.02, which is 3.98. Again agreeing to the true value to 2 decimal places. Using the more accurate approximation with 48 instead of 50 in the denominator, we get a more refined estimate, which again agrees to the true value to 4 decimal places. To interpret what's happening visually, here's the graph of y equals x to the third. We're focusing on behaviour near x equals 64, giving this point on the graph with y equals 4. The underlying idea is to take the tangent line to the curve at this point, which is a very good approximation to the curve nearby. The value of the derivative at x equals 4 is in fact 1 over 48, following from our earlier calculations. And it's not hard to find the equation of the tangent line, which is y equals x on 48 plus 8 over 3. And we can use this equation to estimate y values on the actual curve. If you plug in x equals 65 and x equals 63, the equation of the line produces the same approximations we found earlier, correct to 4 decimal places, implied by the differentials. In fact, using differentials and tangent lines to approximate points on the curve are entirely equivalent processes, just expressed with different notation. In this final example, we look at a rule of thumb used by bankers and investors to estimate how many years it takes for a sum of money, the principal, to double in value when invested with a given compounding annual interest rate. This is called the rule of 70. It estimates that the number of years for the principal to double is 70 divided by the interest rate. For example, if the interest rate is 1%, then you expect to take 70 divided by 1, which is 70 years for the principal to double. If the interest rate is 2%, then you expect to take 70 divided by 2, which is 35 years to double. If the interest rate is 7%, then you expect to take 70 over 7, which is 10 years to double, and so on. The rule of 70 is only a good estimate for small interest rates. Now, why does it work? Though the rule itself is very simple, the underlying reason why it works is profound and relies ultimately on a property of Euler's number E. Recall that the importance of E stems from the fact that the slope of the tangent line to the curve y equals e to the x at the y-intercept is 1, so that when we reflect in the line y equals x to form the inverse function, this tangent then becomes a tangent line to the curve y equals log of x at its x-intercept, also of slope 1. The equation of this tangent line to the curve of the natural logarithm, you can check quickly, is y equals x minus 1, and it's a very good approximation for the curve near x equals 1. Thus, ln of x is approximately equal to x minus 1 for x close to 1. Recall that the derivative of ln of x is 1 over x, so when x equals 1, the value of the derivative is exactly 1, the slope of the tangent line. In terms of differentials, if we multiply through by dx, we get d of ln x equals dx. And this becomes an approximation. Delta of ln of x is approximately equal to delta x, which we expect to be a good estimate when x is close to 1. Making room to continue, delta ln of x, the change in ln of x, is log of 1 plus the change in x, take away the log of 1, which is just ln of 1 plus delta x, because log of 1 is 0. Combined with the above, this gives ln of 1 plus delta x is approximately equal to delta x. As a simpler abstract statement, this just says that ln of 1 plus delta is approximately equal to delta for any small numbers delta. If we want to estimate ln of 1 plus delta when delta is small, we can just replace this expression by delta itself. What on earth has this got to do with the rule of 70? Let P denote the initial principal being invested, and I denote the interest rate. Let y equals y of x be the value of the investment after x years. So P is the value of the investment when x equals 0, so that y of 0 equals P, and the general formula is y equals P times 1 plus I divided by 100 to the power x, which uses an exponential growth model as the investment uses compound interest. We want the number of years x after which the original principal P has doubled to 2P. So by the formula for y of x, we get this expression for P. We can divide through by P and then take natural logs of both sides. But remember, Taking logs brings the exponent down to the front, so the right-hand side becomes x times ln of 1 plus I divided by 100. And then dividing through, x becomes this complicated-looking fraction. Now comes the magic. Recall, log of 1 plus delta is approximately equal to delta for small delta. Here, take delta to be I on 100, which is a small number, and then we can replace ln of 1 plus I on 100 simply by I on 100, up to an approximation. Thus x becomes approximately the simpler fraction ln of 2 over I divided by 100, which is 100 ln of 2 divided by I. The upshot is that to estimate the number of years, we just divide 100 ln of 2 by the interest rate. But 100 ln of 2 is 69.3 to 1 decimal place, which is close to 70. So the number of years is approximately 70 divided by the interest rate, which explains the rule of 70. Now 100 ln of 2 in fact rounds down to 69. So the number of years is also approximately 69 divided by the interest rate, known as the rule of 69, which is slightly more accurate than the rule of 70. And 69 is also not too far off 72, which is a nice number, and we get the so-called rule of 72, which is less accurate, but often used as a rule of thumb if the interest rate is an integer that divides 72 exactly. For example, if the interest rate is 6%, then 72 divided by 6 is 12, so expect about 12 years for the principal to double. It's slightly awkward to divide 6 into 70 or into 69, and in any case, both answers round up to 12. This is the final video for Module 3, and we've come so far, so quickly in transition from pre-calculus. We're well set up now to launch into the main techniques and applications of differential calculus in Module 4 and integral calculus in Module 5. We began this module by discussing average rates of change, and especially focused on interpretations as average speed or velocity in the context of distance or displacement functions. What you see on the speedometer of a car is a physical representation of what we think of as instantaneous velocity, which in mathematical terms is the limiting behaviour of average velocity when the time intervals become vanishingly small. All of this has a general interpretation in terms of slopes of tangent lines to curves, which we saw were described as limits of slopes of secants. The slope of the tangent line is called the derivative. This leads naturally into limit definitions of the derivative, with several natural equivalent formulations, including Leibniz notation, which expresses the derivative in terms of differentials. We discussed a variety of possible behaviours of curves of functions, captured succinctly using variations of limit notation, including examples of asymptotic behaviour. We also discussed the important notion of continuity. Now today, we exploited the notation of Leibniz for the derivative to see how to translate idealised equations involving differentials into approximations involving small changes in the variables expressed by delta notation. This has some surprising applications, such as explaining the rule of 70. Please read the notes, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you in Module 4. You've just completed the third module introducing the derivative and Leibniz notation. This next module continues the development of differential calculus by introducing you to a myriad of techniques and ways of exploiting the first and second derivatives of a function. You'll learn how to recognize when a function is increasing or decreasing by looking at the sign diagram of the first derivative, indicating turning points associated with local and global maxima and minima, and how to recognize when a curve is concave up or concave down by looking at the sign diagram of the second derivative, indicating points of inflection. You'll develop a systematic protocol for curve sketching, including information gleaned from the sign diagrams for the first and second derivatives, as well as information about x and y intercepts and any asymptotic behaviour, which tells us what happens when quantities get very large in magnitude. You'll learn rules for finding derivatives of complicated functions built from simpler functions using the chain rule, the product rule, and the quotient rule, and you'll be able to exploit information about the derivative to solve difficult optimization problems. Again, we hope that you'll find the material interesting and stimulating, that you'll find the videos helpful and the practice and challenges provided by the many exercises beneficial. I look forward very much to your continued attention and participation. In today's video, we discuss what it means for a function to be increasing or decreasing, provide some contrasting examples, and relate these ideas to the sign of the derivative, that is, whether the derivative is positive or negative over a given interval. We say that a function f given by a rule y equals f of x is increasing if the outputs y get bigger as the inputs x get bigger. By getting bigger, we mean moving in the positive direction, to the right along the x-axis and upwards along the y-axis. The simplest example would be the function y equals x, whose curve is a straight line sloping upwards. Naturally, as x gets bigger, y equal to x also gets bigger. A more precise definition involves the less than relation. If a and b are two numbers, and a is less than b, then b is bigger than a. Thus, y equals f of x is the rule for an increasing function if a less than b implies f of a less than f of b for inputs a and b. This makes precise the idea that as x gets bigger, going from a to b, then f of x also gets bigger, going from f of a to f of b. Often the context in which the rule of the function is being used restricts the inputs. Typically, a and b will come from some interval of the real line that is of particular relevance for a given problem. This will become important later when we interpret sign diagrams and sketch curves. We say that a function f given by the rule y equals f of x is decreasing if the outputs y get smaller as the inputs x get bigger. By getting smaller, we mean moving in the negative direction, to the left along the x-axis and downwards along the y-axis. A simple example would be the function y equals minus x, whose curve is a straight line sloping downwards. As x gets bigger, in the sense of moving in the positive direction, y equal to minus x gets smaller in the sense of moving in the negative direction. More precisely, y equals f of x is the rule for a decreasing function if a less than b implies f of a is greater than f of b for inputs a and b. Note how the inequality less than for inputs turns around into greater than for outputs. Functions whose graphs are lines fall into three classes. They're increasing if the slope of the line is positive, decreasing if the slope is negative, or neither increasing nor decreasing if the slope is zero, that is, if the function is constant. Consider the simplest quadratic y equals x squared, whose graph is a parabola with lowest point at the origin. The function is increasing if inputs are restricted to being greater than or equal to 0, but decreasing if inputs are restricted to being less than or equal to 0. If inputs are allowed to be taken from anywhere on the real line, then the function is neither increasing nor decreasing. Consider the simplest cubic polynomial function, y equals x cubed, whose graph looks like this, with an inflection at the origin, where the tangent line passes through the curve. This function is increasing on all of the real line, even though it seems to flatten out momentarily at the origin. It's always the case that if a is less than b, then a cubed is less than b cubed. Here are the graphs of the natural logarithm and exponential functions on the same diagram. They form a natural pair of increasing functions, obtained from each other by reflecting in the line y equals x. The exponential function is increasing on all of the real line without any restriction on inputs. The natural logarithm function, however, is increasing only over the positive reals. Remember, you aren't allowed to take the logarithm of 0 or of a negative number. The fact that both are increasing on their respective domains is not an accident. It's a nice fact, elaborated on a bit later, that if f is increasing, then the inverse function f to the minus 1 is also increasing. The function associated with exponential decay, y equals e to the minus x, is, by contrast, decreasing on all of the real line. This is to be expected because it's the result of reflecting the graph of the increasing function y equals e to the x in the y-axis. Reflecting graphs in the y-axis interchanges increasing and decreasing functions. The circular functions y equals sin x and y equals cos x undulate forever backwards and forwards, so are neither increasing nor decreasing over the real line. If we restrict the domain of the sine curve to the interval from minus pi on 2 to pi on 2, we get a fragment of the curve, which now represents an increasing function. This is the standard restriction that's used to invert the sine function. If we restrict the domain of the cosine curve to the interval from 0 to pi, we get a fragment of the curve, which now represents a decreasing function. This is the standard restriction used to invert the cosine function. It's a general fact that increasing and decreasing functions are invertible because they satisfy the horizontal line test. And these restrictions of the sine and cosine functions are two such examples. The natural, exponential and logarithm functions are also examples that we remarked upon earlier. It's a general fact, explained in the notes, that the inverse of an increasing function is increasing and the inverse of a decreasing function is decreasing. You can see how this works geometrically with these restrictions of sine and cosine. For example, take the restriction of the sine curve, which is increasing, and the line y equals x, reflect, and you produce the inverse sine function, which is also increasing. If you take the restriction of the cosine curve, which is decreasing, and the line y equals x, make a bit more room in the vertical direction, reflect, and you produce the inverse cosine function, which is also decreasing. Here's the graph of the tan function, which is neither increasing nor decreasing over its entire domain, though it's comprised of these infinitely repeating pieces, sandwiched between and separated by vertical asymptotes, and each of these pieces represents an increasing function. And we've highlighted one of them here. The result of restricting the tan function to the interval strictly between negative pi on 2 and pi on 2. This is the standard restriction to make the tan function invertible, and the result is an increasing function. Here's the graph of the inverse tan function, which is also increasing. What about a physical example drawn from real life? Here's a curve we looked at in an earlier video that describes the distance function of a car trip from Sydney to Melbourne. Whilst it's generally sloped upwards as you move from left to right, there are two places where the curve is flat, corresponding to rest periods in the trip where the car isn't moving. So overall, the function is not increasing over the entire time interval. But there are many intervals of time on that trip when the car is moving all of the time, such as this section from Kulak to North Gundagai, and over that time period, the function is increasing. If you're inside the car but not looking outside, you could be sure the car was actually moving because you could always see a positive velocity on the speedometer, even though it may be fluctuating from moment to moment. These positive velocities correspond to slopes of tangent lines to the curve, which are the derivatives of the function. It's clear then that if all the derivatives are positive, then the car is moving at positive velocities, moving closer to North Gundagai from Kulak, which just means, in our mathematics parlance, that the associated function is increasing. This is a physical demonstration of the following mathematical fact. If the derivative is positive on an interval, then the function is increasing. We have, correspondingly, if the derivative is negative on an interval, then the function is decreasing. And you can think of this physically in terms of a car moving backwards in the reverse direction with negative velocities. Consider the function with rule f of x equals x cubed minus x. Then the derivative is 3x squared minus 1. Observe that if 3x squared is greater than 1, then the derivative is positive. And this occurs when x squared is greater than a third, which is precisely when x is greater than 1 over the square root of 3, or less than negative 1 over the square root of 3. Thus the curve for this rule will be increasing on the intervals from 1 over root 3 to infinity and from negative infinity to negative 1 over root 3. Observe also that if 3x squared is less than 1, then the derivative is negative, and this occurs when x lies between negative and positive 1 over root 3. Thus, the curve will be decreasing over this interval. Notice that the rule for f factorises as x times x plus 1 times x minus 1, which tells us that the curve for this rule must cross the x-axis at 0, minus 1 and 1. We're also aware of the importance of plus and minus 1 over root 3. So here's the curve crossing the x-axis at those points we noted before, increasing for x less than negative 1 over root 3 and for x greater than 1 over root 3, and decreasing for x in between. What we've just completed, in fact, are some of the main steps in the technique of curve sketching, which is the topic of a future video. Notice the importance of the sign of the derivative, whether it's positive or negative, and that can be captured in something called a sign diagram for the derivative, in the form of a table, where the horizontal line represents the real line, and we note the important points plus and minus 1 over root 3, where the derivative is 0, and the changing signs of the derivative from positive to positive, which correspond to the curve being increasing, decreasing, and then increasing again. That's a good point to close the discussion for today, leading into more general discussion about sign diagrams in the next video. In today's video, we discussed what it means for a function to be increasing or decreasing, and saw many familiar examples interpreted with this new terminology, and noted that if the derivative is positive on an interval, then the function is increasing, whilst if the derivative is negative, then the function is decreasing. Please read the notes, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. In today's video, we introduce general sign diagrams for rules of functions and provide contrasting examples illustrating how they clarify and inform our understanding of graphs of functions. A sign diagram is a special type of table with two rows. The first row for indicating values of a variable, x say, and the second row for some expression involving the variable, for example x squared minus x, which we factorise if possible. The line separating the rows is a copy of the real number line, and on that line we indicate important points relevant to the behaviour of the expression, such as when it becomes 0 or undefined. For example, x squared minus x becomes 0 for x equals 0 and 1. So we mark off 2 points on the line and label them with 0 and 1. Below this line we indicate the way the expression behaves, whether 0 or undefined at the indicated points, and whether positive or negative between these points and on either side to the right and left. So for this particular expression, the value is positive for x less than 0 or greater than 1, and negative only for x between 0 and 1. Later we'll give an example where the expression is undefined at a particular point. This completes the sign diagram. This particular expression is a quadratic, so the associated curve is a parabola, bowl-shaped up because the coefficient of x squared is positive and passing through the x-axis at 0 and 1. The parabola sits above the x-axis for x less than 0 and x greater than 1, corresponding to the plus signs in the sign diagram, and below the x-axis for x between 0 and 1, corresponding to the minus sign. The sign of the derivative gives us information about where a function might be increasing or decreasing. So let's investigate the derivative of y, denoted by y dash, which in this case is 2x minus 1. Observe that this derivative is 0 precisely when x equals 1/2. And so we can draw a sign diagram, marking off the point half x, 0 directly beneath, and then plus to the right, where 2x minus 1 will be positive, and minus to the left, where it will be negative. The signs tell us that the curve is increasing for x greater than 1/2 and decreasing for x less than 1/2. And both of these exactly match what we see on the curve. This also confirms that the point with coordinates 1/2, -1/4 is the lowest point on the parabola. We informally draw a small line sloping downwards beneath any minus sign to indicate decreasing, and informally a line sloping upwards beneath any plus sign to indicate increasing. Now what about the derivative of y dash, called the second derivative, denoted by y double dash? The derivative of 2x minus 1 is just the constant 2, and the sign diagram is particularly simple. There are no x values where the second derivative is 0 or undefined, and the second derivative is positive everywhere, indicated by a plus sign. We have an informal notation, which is a bowl shape up symbol, which has a technical term, concave up. When we see a plus sign for the second derivative, then we know the curve has some kind of bowl shape up behaviour over the relevant interval. We'll say more about the technical meaning of concavity in a later video. In the case of this parabola, you can imagine the tangent lines to the curve as you pass from left to right, having increasing slope, in the sense of becoming more and more positive as you move from left to right. This is exactly what the sign diagram for the second derivative is telling us, causing the curve to have the shape of a bowl, facing upwards. This upright parabola is concave up, though if we tipped it over, it will become what we call concave down, and then there will be a negative sign instead of a plus sign, and an inverted bowl-shaped down or sad face symbol in the sign diagram, and we'll illustrate that in a moment. We revisit an example discussed towards the end of the previous video. Consider y equal to x cubed minus x, which factorises as x times x plus 1 times x minus 1, so that y equals 0 when x equals minus 1, 0 and 1. We can draw a sign diagram for y, noting these important values for x that cause y to be 0, and then noting an alternating pattern of plus and minus symbols as you move right to left past the points that we've marked on the x-axis. This tells us when the curve sits above and below the x-axis. To find out whether the curve is increasing or decreasing, we form a sign diagram for the derivative, which in this case is 3x squared minus 1, so that y dashed is 0 when x equals plus or minus 1 over root 3. And we get the sign diagram that we mentioned at the end of the last video. We now add our up or down notation to indicate visually when the curve is increasing or decreasing, according to whether the sign of the derivative is positive or negative. Now we can be sure how the curve should undulate, in this case up, down and then up again as we move from left to right. What about the second derivative? Can this give us any useful information? The first derivative is 3x squared minus 1, so the second derivative, y double dash, is 6x, and this is 0 when x is 0. We can draw the sign diagram for y double dash, indicating that it's 0 when x equals 0, and that it has the same sign as x, positive when x is positive, and negative when x is negative. You might remember in the last example we used a bowl shape up or happy face symbol when the second derivative was positive. So we use that again here for x greater than 0. But when the second derivative is negative, we use a bowl shape down or sad face symbol. We now have three sign diagrams that give us a fairly complete description of how the curve should behave, where it sits above or below the x-axis, where it's increasing or decreasing, and where it's bowl-shaped up or down. The important points marked off on the sign diagrams then correspond to important features of the graph, so we note them on the x-axis, and they fit in the curve to match the information about the signs of y, y dashed and y double dash. Of note are the points where the curve is turning around, a peak at minus 1 over root 3 and a trough at plus 1 over root 3. Then this sad face shape for negative x and this happy face shape for positive x. The point where the curve changes from sad to happy is called an inflection. The tangent line actually passes through the curve at a point of inflection. It's worth noticing, and relates to something we call the second derivative test that we'll talk about in a future video, that the point on the curve for x equals negative 1 on root 3, that looks like the top of a hill, correlates with the imagery suggested by the sign diagrams for both the first and second derivatives. And similarly for the point on the curve for x equals 1 on root 3, that looks like the bottom of a valley. The next example also was discussed in an earlier video and is quite difficult. Let g be the rational function with rule x squared minus 2 divided by x minus 1, which can be rewritten as x plus 1 minus 1 over x minus 1. Here's the graph of G with vertical and oblique asymptotes. We now explore the use of sign diagrams to gain a better understanding of the graph. First of all, g of x is 0 precisely when the numerator of the rational expression is 0, which occurs when x equals plus or minus root 2. We can form the sign diagram for g of x by first noting plus or minus root 2 and that g of x is 0 at those points. We also leave room to insert the point 1, because this is the input for which the rule for g does not make sense, and we write u beneath, an abbreviation for undefined. Then we note an alternating pattern of signs for g of x as we move from right to left past these important points on the x-axis. Each part of the sign diagram corresponds to some feature of the graph, sitting above or below the x-axis, being 0 or being undefined. What about a sign diagram for the derivative? As we've noted, the rule for g can be rewritten as x plus 1 take away 1 over x minus 1. Put h of x equal to 1 over x minus 1, and then the derivative g dashed of x becomes 1 minus h dashed of x. But what's h dashed of x? The answer turns out to be negative 1 over x minus 1 squared, and I'll try to give an explanation, which also serves as good revision of one of the limit definitions of the derivative. We have the rule for h. Then for any a, h dashed of a is the limit as b approaches a of h of b minus h of a over b minus a, which becomes the limit of this fraction after subbing in the rule for h. And we can rewrite this, simplify the numerator, and do some cancellation so that the fraction simplifies further. As b approaches a, this fraction approaches negative 1 over a minus 1 squared. Replacing a by x gives the formula that we mentioned earlier. So we can now complete the calculation for the derivative of g, which becomes 1 plus 1 over x minus 1 squared. But all parts of this expression are positive, so g dashed of x is positive always, provided x is not equal to 1. Now we can provide a sign diagram for the derivative of g. We note that g dashed of x is undefined for x equals 1 and positive everywhere to the left and right of 1. So we add an upward sloping symbol in each case to indicate that the function is increasing on both intervals. This behaviour, predicted by the sign diagram, is exactly matched on the curve, both for the branch of the curve to the left of the vertical asymptote and for the branch to the right. There's more that we can say by considering the sign diagram for the second derivative, but we'll save that up for a later video. Today we discussed sign diagrams in general for rules of functions and interpreted a positive or negative sign for the derivative as indicating that the function is increasing or decreasing respectively. A positive sign for the second derivative as indicating that the graph of the function has a bowl shape up or smiley face appearance, and a negative sign for the second derivative as indicating that the graph has a bowl shape down or sad face appearance. Please read the notes, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. In today's video, we discuss local and global maxima and minima, collectively called extrema, for rules of functions, which are related to turning points of curves. We provide some contrasting examples and illustrate how to search for extrema by looking for the changing sign of the derivative to see where a function changes from being increasing to decreasing or from decreasing to increasing. We finish with a discussion of the closed interval method. Consider the rule y equals f of x for a given function f. We say that f of a for some input x equals a is a local maximum if f of a is greater than or equal to f of x for all x near a. We say that f of a is a local minimum if f of a is less than or equal to f of x for all x nearby. We may refer to either a maximum or a minimum as an extremum. And if the previous properties hold for all x in the domain of the function, then the extremum is said to be global. Just think of a global property as one that holds everywhere. To be near A on the real number line means ranging over some interval surrounding A. And that interval, which could be quite small, is often called a neighbourhood of A by mathematicians. Extrema may not exist, even for the simplest of functions. For example, any linear function, where the slope is non-zero, increases and decreases smoothly and uniformly without bound. There's no opportunity for any value of such a function to be the greatest or the least in any neighbourhood of its input. However, by contrast, any linear function with zero slope, that is a constant function y equals k, has only one value. So that constant k becomes simultaneously both the global maximum and minimum value of the function. Consider now a function f whose rule f of x is a quadratic. The graph is a parabola, opening upwards if the coefficient of x squared is positive, or downwards if it's negative. In the upwards facing case, the apex, also called the vertex of the parabola, is the lowest point. When the parabola is situated somewhere in the xy plane and one moves across to the vertical axis, we produce a y value which is less than or equal to all y values produced by the parabola. So it becomes the global minimum. In this diagram, the apex is in the fourth quadrant, but it could be located in any quadrant. Wherever it is, when we move across to the y-axis, we always produce the global minimum. In the downwards facing case, the apex now is at the highest point. So wherever the parabola is situated in the plane, when we move across to the y-axis, we produce the global maximum. And so we have complete information in the two cases of quadratic functions. The apex in either case is also called a turning point. And in both cases, the tangent line to the curve at the apex is horizontal, so has zero slope. These are special cases of a general phenomenon. A turning point for a general curve is a place where the curve changes from increasing to decreasing or from decreasing to increasing. If any given turning point has a tangent line, which is usually the case as most of the time our curves are smooth, then the slope is zero. But the slope of the tangent line is the derivative of the function. So if we want to find turning points, the natural place to look will be where the derivative is zero. Let's apply the derivative to quickly find the turning point and global minimum of this particular quadratic. To solve this, observe that the derivative is 2x minus 2, which is 0 when x equals 1. So the turning point must occur when x equals 1, in which case y equals minus 2. So the turning point has coordinates 1, minus 2, and the global minimum is the y-coordinate, which is minus 2. All of this is confirmed by drawing the associated parabola. Notice that if we draw the sign diagram for the derivative, we see that the derivative is negative to the left of x equals 1 and positive to the right, confirming that the function is decreasing from the left and increasing to the right of the apex. The next example involves a cubic polynomial, and the problem is to find all local and global extrema, firstly over the whole real line, and secondly over the restricted interval between 0 and 5. To solve the first part of the problem, we find the derivative, which is a quadratic, and which turns out to factorise as 3 times x minus 1 times x minus 3, so that the derivative is 0 when x equals 1 and 3. Very quickly, we've narrowed down the possibilities for extrema to just these two inputs. By drawing the sign diagram for the derivative, we should be able to tell what kind of extrema occur and where. We see from the factorisation of y dashed that if x is bigger than 3 or less than 1, then y dashed is positive, and if x is between 1 and 3, then y dashed is negative. So we get an up, down, up pattern of behaviour of the curve, with turning points at x equals 1, where there's a local maximum, and x equals 3, where there's a local minimum. The local maximum is the value of the function at x equals 1, which is 5, and the local minimum is the value at x equals 3, which is 1. Neither of these local extrema can be global because with an unrestricted domain, the cubic can take arbitrarily large positive and negative values. Here's the graph of the function with its turning points and the local extrema appearing on the y-axis. In the second part of this problem, we need to find all extrema when the domain is now restricted to the interval from 0 to 5. The local maximum and minimum from the previous calculation are important because the inputs x equals 1 and 3 fall within this domain. The question is really how far the curve falls away to the left and how much it climbs to the right. So we evaluate the function at the left-hand endpoint of the interval, x equals 0, and get the value 1, and at the right-hand endpoint, x equals 5, and get the value 21. We can now compare the four values, 5, 1, 1, and 21. The global maximum is just the largest of these, which is 21, and the global minimum is the smallest, which is 1. And this solves the second part of our problem. The graph is actually quite steep near x equals 5, so to see what's going on we need to adjust the scale of the axis. And then you can see how easily the local maximum of 5 is surpassed by the global maximum of 21. The global minimum, in fact, is achieved exactly twice, both at the left-hand endpoint of the interval and at x equals 3 inside the interval. The technique that we just used applies generally to curves and is called the closed interval method. Consider a continuous function f defined for inputs x between a and b, including a and b. The interval a, b of inputs with square brackets is referred to as closed because it contains both of the endpoints. Being continuous, you can imagine drawing the graph of f without lifting your pen off the paper. To find the global maximum and minimum values, it suffices to find the largest and smallest values of the function when evaluated at the endpoints of the interval a and b and at inputs where the derivative turns out to be 0, so the tangent line is horizontal, or where the derivative is undefined. In the last example, the derivative was defined everywhere. This is a very powerful result because for most functions there are an infinite number of possible inputs. And this is saying that you only have to restrict attention, typically, to just a finite handful of points. In the last example, which was quite a sophisticated cubic, we only needed to evaluate the function at 4 points. We finish with an example where the derivative is not defined everywhere. The function f has the rule f of x equals the magnitude of x minus 1 plus 3 restricted to x between minus 2 and 5. If x is greater than or equal to 1, then the magnitude sign can simply disappear and the rule quickly becomes x plus 2. If x is less than 1, then the magnitude sign can be removed by replacing x minus 1 by 1 minus x, and the rule quickly becomes 4 minus x. These are two linear pieces with derivative 1 for x greater than 1 and minus 1 for x less than 1. Note that the values 1 and minus 1 are both non-zero. In fact, there can be no derivative at x equals 1 because there's a sharp point on the curve, so the tangent line becomes ambiguous and there's no well-defined slope. Here's the graph trimmed to only include inputs x between minus 2 and 5. We can solve the problem completely by inspecting the graph, but let's see what the closed interval method predicts. The method tells us we only need to check endpoints and x equals 1, since the derivative is never 0 and is undefined at x equals 1. So we check f of minus 2, which evaluates to 6, f of 5, which evaluates to 7, and f of 1, which evaluates to 3, of which 7 is the largest and 3 is the smallest. And these correspond on the graph to the global maximum and global minimum of the function, respectively. Note that the value 6, which occurs at the left-hand endpoint of the domain, is a local but not global maximum. This then solves our problem. Note that though we looked at the graph, The closed interval method can be followed blindly and mechanically without any visual assistance. It's important to have such methods to deal with functions whose graphs are so complicated that it may be too difficult to draw them or even imagine what they look like. In today's video, we discussed local and global maxima and minima, collectively called extrema, for rules of functions, considered associated turning points where the curve changes from increasing to decreasing or decreasing to increasing, and found them by exploiting the derivative and the fact that the tangent line to a curve at a turning point must be horizontal and have zero slope. We finished with discussion and illustrations of the closed interval method, which locates global extrema by narrowing attention to endpoints of the domain and points where the derivative is zero or undefined. Please read the notes, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. In today's video, we formally discuss concavity, which is a property of curves where the slopes of tangent lines are either increasing or decreasing, leading to notions of concave up and concave down, and points of inflection where concavity changes, either from concave up to down or from concave down to up, which are also points with the property that the tangent lines pass through the curve. We begin by discussing concavity. Think of the property concave up of a curve as corresponding to the curve being in a bowl-shape up configuration. If you look at miniature tangent lines to the curve as you pass from left to right, you'll notice that the slopes change from being very steep and negative to shallow and negative, to being zero as you move through the turning point, to being shallow and positive, to being steep and positive. The slopes of the tangent lines are increasing. This corresponds to the derivative of the rule of the original function being itself an increasing function. So its derivative, the second derivative of the original function, denoted by y double dashed, should be positive. Now consider the opposite property, concave down, which corresponds to the curve being in a bowl-shaped down configuration. Now, if you look at miniature tangent lines to the curve as you pass from left to right, you'll notice that the slopes change from being very steep and positive to shallow and positive, to being zero as you move through the turning point, to being shallow and negative, to being steep and negative. The slopes of the tangent lines are decreasing. This corresponds to the derivative of the rule of the original function being itself a decreasing function. So the second derivative of the original function, y double dashed, should be negative. A point of inflection, or we simply say an inflection, is a point where the concavity changes, either from being concave up to being concave down, or from concave down to concave up. We can picture the first case in a couple of ways, transitioning from bowl-shape up to bowl-shape down. And the moments of transition are called inflections. And you can watch the way miniature tangent lines to the curve behave as you pass from left to right, for the first curve displayed here, and for the second curve. And you might notice that the tangent line crosses the curve at the point of inflection. The slope of the tangent line, which is the derivative denoted by y dash, reaches a maximum at that moment of transition, at the inflection point. So its derivative, denoted by y double dashed, must become zero. In summary, for the case where concavity changes from concave up to down, the derivative reaches a maximum and the second derivative is zero. Consider the second type of transition from concave down to concave up. We can picture that in a couple of ways, transitioning from bowl-shape down to bowl-shape up. And note the moments of transition, the inflections. And now watch the way miniature tangent lines behave as you pass from left to right, for the first curve and for the second curve. And again, the tangent line crosses the curve at the point of inflection. This time the derivative y dashed reaches a minimum at that moment of transition at the inflection. And again the second derivative y double dashed must become zero. In summary, for the case where concavity changes from concave down to up, the derivative reaches a minimum and the second derivative is zero. And so we've considered variations in the way concavity can change and the effects these have on the derivative and second derivative. The upshot of this is that changes in concavity may be detected by looking at the changes in the sign of the second derivative, and all of this information will be captured in its sign diagram. To see how this works, let's sketch the curve y equals 9x minus x cubed. We begin by noticing that the rule factorises as x times 3 plus x times 3 minus x, which will be useful in a moment for detecting x-intercepts. The derivative, y dashed equals 9 minus 3x squared, which factorises as 3 times root 3 plus x times root 3 minus x. The second derivative, y double dashed, is simply minus 6x. Putting these together, we can start to build sign diagrams. And we'll do this for the first and second derivatives. In the case of y dashed, we see that the important inputs for x are plus or minus root 3, where the derivative is 0. And we get a pattern of signs, minus, plus, minus, as we move from left to right. So the curve is decreasing, then increasing, then decreasing again. In the case of y double dashed, the important input for x is 0, where the second derivative is also 0, and the pattern of signs is plus, minus, as we move from left to right. So the curve must be concave up to the left of 0, indicated by this smiley face symbol, and concave down to the right of 0, indicated by this sad face symbol. All of this information is noted here to the side, and we can list the main features of the curve. The y-intercept is just 0. The x-intercepts will be 0, 3, and minus 3. From the sign diagram for the derivative, there's a local minimum occurring for x equal to minus root 3, and a local maximum when x equals plus root 3. From the sign diagram for the second derivative, there's an inflection at the origin. Now we can sketch the curve with confidence. Here are the important points on the x-axis, and we fit in a curve which is concave up to the left of 0, concave down to the right, with a local minimum at x equal to negative root 3 and a local maximum at x equal to plus root 3. And the local maximum and minimum values you can quickly work out from the rule for the function, and they become plus or minus 6 times the square root of 3. And the origin is the point of inflection where the concavity changes. This completes the sketch of the curve y equals 9x minus x cubed. We'll finish with an example of a cusp and sketch the curve y equals x to the power of 2/3. We begin by differentiating y, which becomes 2/3 of x to the minus 1/3, remembering the rule that the exponent comes down to the front and you subtract 1 to get the new exponent, which we can rewrite as 2 over 3 times x to the 1/3. The sign diagram for the derivative involves one important point for x, namely x equal to 0, where the derivative is not defined, because otherwise we'd be trying to divide by 0 in the rule for y dashed. The pattern of signs is simply negative, positive, as the sign of y dashed agrees with the sign of x. So the curve is decreasing to the left of 0 and increasing to the right. This means that there's a global minimum at x equals 0, noting that the curve is continuous even though the derivative is undefined at x equals 0. We can say more about the behaviour of the derivative near the origin using limit notation. The limit of y dashed as x approaches 0 from below is the limit of 2 divided by 3 times the cube root of x, which becomes arbitrarily large and negative, and we use the minus infinity notation to capture this. On the other hand, the limit of y dashed as x approaches 0 from above becomes plus infinity, capturing the idea that the derivative gets arbitrarily large and positive. These two limits summarise the behaviour of the slopes and imply that the tangent lines themselves become more and more vertical as x approaches 0 from one side or the other. Let's continue differentiating. The second derivative becomes 2/3 of minus 1/3 times x to the minus 4/3, just using the rule for differentiating a power of x again, which may be rewritten as -2 divided by 9 times the square of x to the 2/3. We're emphasising the square in the denominator, as this tells us that it's always positive, so the entire fraction is always negative, provided x is not equal to 0. We can now build the sign diagram for y double dashed, which again has 0 for an important point for x, and y double dashed is undefined. Now the pattern of signs is just negative, negative. So we have the concave down sad face symbol in both cases. In summary, we have the derivative and second derivative and their respective sign diagrams, and the contrasting unbounded behaviours of the derivative as x approaches 0 from each side. We can now draw the graph that matches all of this information, producing a continuous curve with this sharp point, a cusp at the origin, which also coincides with the global minimum value of y equals 0. This completes the sketch of the curve. In today's video, we discussed notions of concavity of a curve, including the properties of being concave up and concave down, and points of inflection where concavity changes, either from concave up to down or from concave down to up. We illustrated the ideas by working through a couple of contrasting examples, including a cusp and exploited information provided by the sign diagrams of the first and second derivatives. Please read the notes, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. In today's video, we bring together a range of ideas and techniques that we've been discussing over several videos that lead to an ordered and systematic checklist for sketching a curve in the plane. Of central importance are the sign diagram for the derivative, which tells us where the curve is increasing or decreasing, and the sign diagram for the second derivative, which tells us where the curve is concave up or down. We begin by making some general remarks about curve sketching, by which we mean more specifically sketching or drawing the graph of a function y equals f of x in the xy plane. The scales of the x and y axes don't need to be the same, and the axes are positioned on the page depending on where the important features of the graph will appear. Always aim for simplicity and clarity, and focus on the main qualitative features. Extra detail, such as coordinates of points, can be added depending on the requirements of any particular problem. There's a fairly natural list of typical features to look for. Firstly, look for the y-intercept, where the curve crosses the vertical axis, in the case that x equals 0 is in the domain of the function, which is simply found by evaluating f of 0. And then look for the x-intercepts, where the curve crosses the horizontal axis, if they're likely to be straightforward to find or simple to describe, but they may be difficult, as they're the solutions of the equation f of x equals 0. Indeed, a given problem might be to attempt to solve the equation f of x equals 0, typically by using some approximation method from advanced calculus, and the main purpose of the sketch of the curve may be just to get started, with the final aim of knowing roughly where the x-intercepts might be. Then look for asymptotic behaviour, which roughly speaking means seeing what happens when things get large, such as when x gets arbitrarily large and positive, or arbitrarily large and negative, leading to possible horizontal or oblique asymptotes. Or whether there are any vertical asymptotes near which y can get arbitrarily large and positive or negative. Then we look for where the curve might be increasing, where the derivative could be positive, or decreasing where the derivative could be negative, which helps us find turning points where the derivative might be 0. And these could be local or global maxima or minima. This information typically is stored in the sign diagram for the derivative. Then we look for where the curve might be concave up, where the second derivative might be positive, or concave down, where the second derivative might be negative, which helps us find possible points of inflection. Where the second derivative might be 0. This information typically is stored in the sign diagram for the second derivative. Let's work through this list to sketch the following cubic. The y-intercept is -1, the constant term, which results when you evaluate the polynomial at 0. The x-intercepts look tricky, and we can say more about them later and roughly where they might exist. In fact, there's only one x-intercept in this case, but that's not obvious from the rule itself. We now consider asymptotic behaviour. As x gets large and positive, the cubic is dominated by the leading term 2x cubed, and also gets arbitrarily large and positive, indicated by the use of the infinity symbol. As x gets large and negative, now the cubic also gets arbitrarily large and negative, indicated by the use of the negative infinity symbol. There are certainly no horizontal asymptotes, nor are there any oblique asymptotes, though it's not obvious why there are none, and some careful reasoning is given in the notes. The derivative is this quadratic, which quickly factorizes. And we can see it's 0 when x equals 1 or 2. And then build its sign diagram with this pattern plus, minus, plus, corresponding to increasing, decreasing, increasing, with a maximum occurring at x equals 1 and a minimum at x equals 2, with y values 4 and 3 respectively, giving a turning point 1, 4 with local maximum 4, and a turning point 2, 3 with local minimum 3. We get the second derivative, y double dash, by taking the derivative of y dash, and get 12x minus 18, which factorizes as 6 times 2x minus 3. So that y double dash equals 0 when x equals 3 on 2. And we can build its sign diagram with a pattern of negative, positive. So concave down followed by concave up, with change in concavity and inflection when x equals 3 on 2. We can evaluate y for this input, yielding 7 on 2, so the point of inflection has coordinates 3 on 2, 7 on 2. We can now put all of this information together, noting important points on the axes and the position of the y-intercept, the two extrema and the inflection, and then drawing a smooth curve that passes through these points, consistent with the information in the sign diagrams. This completes the sketch of the cubic. And one may, if it's important, highlight the point of inflection and the points where the local maximum and minimum occur. Notice that the sketch tells us that there's only one x-intercept, and the curve crosses the x-axis somewhere between 0 and 1, and quite close to 0. If one were trying to solve the equation for x where this cubic is set equal to 0, then this sketch would tell you, firstly, that there's only one solution, and secondly, where to start looking to find an approximation to this unique solution. Now we'll sketch the graph of a by now familiar rational function g with the rule g of x equals x squared minus 2 over x minus 1. Many of its main features have been explored in earlier videos. Let's go through the checklist systematically. Firstly, the y-intercept is 2, the result of evaluating the rule when x equals 0. The x-intercepts turn out to be straightforward, simply when the numerator x squared minus 2 is 0, which occurs when x is plus or minus the square root of 2. The asymptotic behaviour has been explored thoroughly in an earlier video. The limit as x approaches 1 from above of g of x is minus infinity, which means g of x gets arbitrarily large and negative, and the limit as x approaches 1 from below becomes positive infinity, which means g of x gets arbitrarily large and positive, and x equals 1 is a vertical asymptote. The interesting asymptotic behaviour occurs as x gets large and positive or large and negative. By rewriting the rule for g as x plus 1 minus 1 on x minus 1, we saw that g of x is approximately x plus 1 for large positive or negative x, so that the line y equals x plus 1 becomes an oblique asymptote. The derivative of g we looked at in detail in an earlier video, which is 1 plus 1 on x minus 1 squared, and positive for all x not equal to 1. The sign diagram, you might recall, is particularly simple, with plus, plus on either side of x equals 1, where y dash is undefined, so that the curve is increasing for x less than 1 and increasing again for x greater than 1, so that there are no turning points. We can rewrite the derivative as 1 plus x minus 2 to the negative 2. So the second derivative, y double dashed, becomes 0 plus negative 2 times x minus 1 to the negative 3. I'll just explain briefly where the last part comes from. The derivative of x to the n is n times x to the n minus 1 for any exponent n. So that the derivative of x minus 1 to the n must similarly be n times x minus 1 to the n minus 1, because the curve y equals x minus 1 to the n is obtained from the curve x equals x to the n by shifting the curve to the right horizontally by 1 unit, and slopes of tangent lines are not altered at all by horizontal shifting. This result was then applied with n equal to negative 2. The second derivative then becomes negative 2 divided by x minus 1 cubed, and its sign, positive or negative, must be the opposite of the sign of x minus 1. This produces the following sign diagram, with y double dash undefined at x equals 1, and the pattern plus followed by minus, so that the curve is concave up for x less than 1, followed by concave down for x greater than 1. Now we can gather all of this information and set up the axes for the sketch of the curve, noting the important points 2 on the y-axis and plus and minus root 2 on the x-axis, and the oblique and vertical asymptotes. Then we see this familiar curve in 2 branches, consistent with all of this information. The feature that we didn't discuss previously was concavity, and we see the concave up branch to the left of the vertical asymptote and the concave down branch to the right. Notice that these are not full smiley or sad faces, so to speak. The slope is increasing in the left-hand branch of the graph and decreasing in the right-hand branch, which is consistent with the pattern of plus and minus in the sign diagram for the second derivative. The reason for the oblique asymptote is that the rule for the function splits up into a linear piece, x plus 1, take away this extra piece, 1 over x minus 1. This means that to the right, the curve is approaching the oblique asymptote from below, because we are taking a small positive piece away from the linear piece. But to the left, the curve is approaching the oblique asymptote from above, because we are taking away a small negative piece, which is the same as adding a small positive piece. It's interesting to ask, what happens if we add 1 over x minus 1 in the rule for the function instead of taking it away? So let's work through the checklist for sketching the curve with this variation of the previous example, where we call the function f with the rule y equals f of x equals x plus 1 plus 1 over x minus 1. Observe, after a little bit of algebraic manipulation, that the rule becomes the rational function x squared over x minus 1. The y-intercept is now just 0, and we quickly see that there's exactly one x-intercept, which is also 0. As in the previous example, x equals 1 becomes the vertical asymptote. But notice that the behaviour is different. The limit, as x approaches 1 from above, now turns out to be plus instead of minus infinity. And the limit, as x approaches 1 from below, now turns out to be minus instead of plus infinity. The oblique asymptote again is the line y equals x plus 1. The derivative y dash now becomes 1 minus, instead of plus, 1 over x minus 1 squared, which, after a few steps, you can see becomes the rational function x squared minus 2x over x minus 1 squared. And the numerator factorises as x times x minus 2. So that y dashed equals 0 when x equals 0 and 2. Notice that y dashed is undefined at x equals 1. We can now build the sign diagram for y dashed, which produces the pattern of signs plus, minus, minus again, plus, as we move from left to right past the important points for x. producing the pattern increasing, decreasing, decreasing again, and increasing, with a maximum at x equals 0 and a minimum at x equals 2. Evaluating f at x equals 0 and 2 produces the turning points 0, 0, the origin in fact, with a local maximum of 0, and 2, 4, with a local minimum of 4. To find the second derivative y double dash, first notice that y dash can be rewritten as 1 minus x minus 1 to the minus 2. So the differentiating produces minus negative 2 times x minus 1 to the minus 3 by bringing the exponent down and making a new exponent by subtracting 1, to produce simply 2 over x minus 1 cubed. Then y double dashed is undefined at x equals 1 and otherwise non-zero, in which case it's clear that the sign of y double dash is the same as the sign of x minus 1. And so we can quickly build the sign diagram with the pattern minus plus, sad face followed by smiley face, so that the curve is concave down for x less than 1 and concave up for x greater than 1. Putting this information together, drawing the axes and two asymptotes, we get the curve in two branches, with the first branch concave down, achieving a local maximum corresponding to the origin, and the second branch concave up, achieving a local minimum corresponding to the point 2, 4. Notice how, by contrast with the previous example, the curve gets closer and closer to the oblique asymptote from above as we move to the right, and from below as we move to the left. In today's video, we produced a checklist for sketching curves in the plane and worked through the details in three contrasting examples. The first involved a cubic function, where there were no asymptotes, but there were two turning points and an inflection. Interestingly, the sketch shows there's exactly one x-intercept and indicates roughly where to find it, which would be useful if one wanted to go further and solve an associated cubic equation. The second and third examples involved rational functions, with similar rules but contrasting behaviour. Both of them had two branches and identical vertical and oblique asymptotes, but approached differently. One curve had no turning points, whilst the other curve had two. They both had shifts in concavity as one passes across the vertical asymptote, so to speak, which one may think of as creating some kind of inflection at plus and minus infinity. Please read the notes, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. There are three important techniques or formulae for differentiating more complicated functions in terms of simpler functions, known as the chain rule, the product rule, and the quotient rule. In today's video, we introduce and explain the first of these, the chain rule, which is considered by many to be the simplest to remember, explain, and apply. Let y equal f of u be a function of a variable u, whilst u itself is a function of another variable x, say u equals g of x. Using Leibniz notation, the chain rule says simply dy dx equals dy du times du dx. And you can think of the differential du in the numerator cancelling with du in the denominator as though these were ordinary fractions. There's an equivalent statement using the function dash notation for the derivative. F circle g dashed of x equals f dashed of g of x times g dashed of x. The two statements look quite different, but in fact carry exactly the same information, and I'll come back to the function dash notation version later. For now, let's focus on the version of the chain rule using Leibniz notation and work through some examples. Here y equals negative 3x plus 6 squared, and we want to find the derivative dy dx. We can solve this directly by expanding the brackets to get the quadratic 9x squared minus 36x plus 36, and then differentiating the usual way to get 18x minus 36, which factorises as 18 times x minus 2. We can also solve this indirectly using the chain rule. To do this, we put y equals u squared, where u equals minus 3x plus 6, so that y becomes a particularly simple function of u. The chain rule says dy dx equals dy du times du dx. But the derivative of y with respect to u is just 2u, since y equals u squared, and the derivative of u with respect to x is just minus 3. So this product becomes 2u times minus 3, which is minus 6u. Converting back into an expression involving x, this becomes minus 6 times minus 3x plus 6, which quickly simplifies to 18 times x minus 2, which is the same answer that we obtained by the direct method. It's interesting that we get to the same answer by quite different routes. In this example, there's about the same amount of work using either method. In more elaborate examples, the chain rule can save a lot of time and work. With a little bit of practice, you will develop fluency quickly and find the chain rule effective, powerful, and easy to use. In the next example, we want to find the derivative of y equals e to the minus x. To set up the chain rule, we put y equals e to the u, where u equals minus x. Then again dy dx equals dy du times du dx. But y equals e to the u, so dy du is just e to the u, and du dx is minus 1. So this becomes minus e to the u, which becomes minus e to the minus x, getting an expression in terms of x. This shows that the derivative of e to the minus x is minus e to the minus x. More generally, we can consider y equals e to the kx, where k is a constant, and imitate the previous calculation when k was equal to negative 1. Put u equal to kx so that y equals e to the u. Again, dy dx equals dy du times du dx, which, similar to before, becomes e to the u times k, which is k e to the u, which becomes k e to the kx. This shows that the derivative of e to the kx is k e to the kx. You may be curious to know why the chain rule works, and we now sketch a proof. We take the heuristic idea of cancelling differentials in the numerator and denominator and relate this to the formal definition of the derivative in terms of limits. Using Leibniz notation, the derivative is defined as the limit as delta x tends to 0 of the quotient delta y over delta x, where delta x is a small change in x and delta y is the corresponding small change in y. We also have the variable u, somewhere in between, acting like a stepping stone in the composition of functions, and the change in x causes a change in u, denoted by delta u. We can suppose in this sketch that delta u is non-zero, and then insert delta u both in the numerator and denominator of the fraction, without affecting the overall value of the expression of which we're taking the limit. But the limit of a product is the product of the limits, so we can rewrite this as the limit as delta x approaches 0 of delta y over delta u multiplied by the limit of delta u over delta x. And we can adjust the way we've written the first limit, because we expect delta u to get really, really small as delta x does. That is, delta u goes to 0 as delta x goes to 0. And then recognise the first limit as a definition of dy du and the second limit as a definition of du dx. This completes the sketch of the proof that dy dx equals dy du times du dx. Here's the statement of the chain rule again with both versions. Let's focus now on the version using function dash notation. The explicit connection is that y is a function of u with rule f of u, and u is a function of x with rule g of x. So we're feeding the rule for g into the rule for f, which creates the composite function f circle g. Then f circle g dashed of x is the derivative of y with respect to x, not with respect to u, which we've previously just called y dashed, also called dy dx in Leibniz notation, which is dy du times du dx, by the first form of the chain rule that we've discussed already in detail. But dy du becomes f dashed of u, and u dx becomes g dashed of x in function notation, which is f dashed of g of x times g dashed of x, because u equals g of x, which gives us the required statement of the chain rule using function notation. Let's practice this version of the chain rule on an example. that f and g be functions with rules f of x equals x cubed and g of x equals x squared minus 1. We wish to find the derivatives of the composite functions fog, that is f circle g, and gof, that is g circle f. Certainly the derivative of f is 3x squared, and the derivative of g is 2x. So applying the chain rule using function notation, we get fog dash of x is equal to f dashed of g of x times g dashed of x, which is f dashed of x squared minus 1 times g dashed of x, which is 3 times x squared minus 1 squared times 2x, which becomes 6x times x squared minus 1 all squared. On the other hand, applying the chain rule to these functions but composing in the other order, we have gof dashed of x equals g dashed of f of x times f dashed of x, which becomes g dashed of x cubed times f dashed of x, which is 2x cubed times 3x squared, which simplifies to 6x to the fifth, and this solves the problem. Notice that we didn't need to know the rules for f circle g or g circle f and could follow the formula for the chain rule quite mechanically. Of course, we can solve this problem also without the chain rule, and in the case of f circle g, the rule becomes f of g of x, which becomes f of x squared minus 1 equal to x squared minus 1 cubed, which expands out to become x to the 6th minus 3x to the 4th plus 3x squared minus 1, with derivative 6x to the 5th minus 12x cubed plus 6x, which factorizes as 6x outside of x to the 4th minus 2x squared plus 1, which factorizes further as 6x times x squared minus 1 squared, which happily agrees with the answer we found quickly and indirectly using the chain rule. In the case of g circle f, the rule becomes g of f of x, which becomes g of x cubed, which is x cubed squared minus 1, equal to x to the 6th minus 1, with derivative 6x to the 5th, which again happily agrees with the answer found using the chain rule. In today's video, we introduced the chain rule, using both Leibniz notation and function notation, and applied it to differentiate composite functions in several contrasting examples. Please read the notes, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. In today's video, we demonstrate two contrasting applications of the chain rule. To begin to understand the behaviour of the Gaussian curve y equals e to the minus x squared, related to the normal probability distribution used in statistics, and to predict how long it takes for an ice cube to melt away completely. Our first example is the Gaussian curve y equals e to the minus x squared, which is often described as bell-shaped, in the shape of a bell. It's actually the graph of something called a probability density function for the normal distribution used in statistics, so it's of fundamental importance in applications to science and many other disciplines. The curve is named after Carl Friedrich Gauss, another giant in the development of modern mathematics, who lived and worked from towards the end of the 18th century into the middle of the 19th century. It's a common debating theme: who was the greater mathematician, Euler or Gauss? The description bell-shaped is possibly slightly misleading. There are many curves that you could say are in the shape of a bell, but this is the one most people have in mind when they refer to a bell-shaped curve. We'll meet another important curve in the shape of a bell in a later video known as the Witch of Maria Agnesi, after a famous female 18th century Italian mathematician, Maria Agnesi, but more about that later. I'd like to apply the methods of curve sketching that we've discussed in earlier videos to the function y equals e to the minus x squared. In the course of doing this, you will see an application of the chain rule. We'll first find the y-intercept, which is 1. There are in fact no x-intercepts, because any power of e, in particular e to the minus x squared, for any x is positive. As to asymptotic behaviour, observe that e to the minus x squared, which is the reciprocal of e to the x squared, tends to 0 as x gets arbitrarily large and positive or negative. So the x-axis is a horizontal asymptote. We next look at properties of the derivative, and this is where the chain rule comes in handy. Put y equal to e to the u, where u equals minus x squared, so dy du equals e to the u, and u dx equals minus 2x. Hence the derivative y dash, which is dy dx in Leibniz notation, becomes dy du times du dx by the chain rule, which now becomes e to the u times minus 2x, which is minus 2x times e to the minus x squared. It's important to know when the derivative is 0, and in this case this only happens when x equals 0, noting that the factor e to the minus x squared is never 0. We can then build a simple sign diagram by noting that y dashed is 0 when x is 0, and we have a pattern of plus, minus, indicating that the curve is increasing for x less than 0, decreasing for x greater than 0, and achieving a maximum at x equals 0. We can put this all together so far, drawing the axes and noting the y-intercept, the asymptotic behaviour of the x-axis, both to the far left and far right, and the fact that there's a turning point at the y-intercept when x equals 0. Because the curve is increasing from the left and decreasing to the right, it's natural to fill in the rest of the curve to obtain this bell shape. To create this shape, there appear to be two natural inflections where the curve changes concavity, both to the right and to the left. And the curve has natural symmetry about the vertical axis because e to the minus x squared doesn't change if you replace x by minus x, an instance of an even function. To be sure about the way the curve behaves, and in particular to find these inflections, we need to go further and investigate the second derivative y double dash. But y dashed is quite complicated, and we don't yet have the tools to find y double dash easily. To do so, we employ the so-called product rule, which tells us how to differentiate a product of expressions. But we defer the complete analysis until after next time, when the product rule will be explained and illustrated. The next example involves some quite intricate mathematics, so you might not be able to follow all of the detail at first. I hope you'll nevertheless persevere, maybe using the pause and replay buttons on the video from time to time, because the mathematics describes a very beautiful physical phenomenon with surprising accuracy and involves an elegant and powerful application of the chain rule. In this next example, we've created an ornamental sculpture in the form of a perfect ice cube, which we've suspended from the ceiling in a warm room. 100 litres of water were used to create the original ice cube. We notice, after 3 hours, that 10 litres of water have accumulated in a tray below the dripping ice cube. Our problem is to use mathematics to estimate the number of hours it takes for the ice cube to melt away to nothing. We begin by denoting the side length of the cube by x units. What the units turn out to be is unimportant, and we don't even need to know what the original value of x is, or even to know what exact volume of frozen ice corresponds to, say, 1 litre of water. It's very important, however, to think of the value x as a function that changes with time t, and the units of time will be hours, since the question asks how many hours it takes for the cube to melt away to nothing. You might notice in this example we're using t as the independent variable and x as the dependent variable, similar to the conventions used in describing displacement functions. There are two quantities that turn out to be important in the modelling that precedes the analysis. These are the volume of the cube, denoted by v, which is also a function of time t, and takes the value x cubed, cube units, for whatever value x happens to be at that particular time. And the surface area of the cube, denoted by a, another function of time t, and takes the value 6x squared, since there are 6 faces to the cube, each of area x squared, square units. So we have these 3 quantities associated with the melting ice cube, x, v, and a, all functions of time t. In fact, we want to know when the ice cube disappears, so we want the time t at which all of these will be 0. The key physical fact which starts our mathematical modelling, is that the rate of melting of the volume of the cube is proportional to the surface area of the cube. This makes good intuitive sense, as the surface of the cube is where the cube interfaces directly with the warm air in the room. So the more area there is on the surface of the cube, the more associated substance of the cube, measured by volume, should disintegrate from solid into liquid and drip into the tray below. The rate at which the volume changes with time is the derivative dV dt. And this fact states that dV dt is a constant multiple of the surface area A, say k times A for some constant k. But A equals 6x squared, so dV dt becomes 6k x squared. We're developing a list of important facts. Note also that dV dx, the derivative of x cubed with respect to x, is 3x squared. We'd like information about the width x to the cube and how it changes with time t, so it's natural to ask what the derivative dx dt might be. The link between this and the other derivatives is the chain rule, which in this case says that dV dt equals dV dx times dx dt. But dV dt is 6kx squared and dV dx is 3x squared. So this says that 6kx squared equals 3x squared times dx dt. So dividing through gives dx dt equals 6kx squared divided by 3x squared, which simplifies to 2k. Hence dx dt is simply 2 times the constant k, which is another constant. If the rate of change of x with respect to time t is constant, then the function x must be a linear function of t with slope 2k, so that x must have the form x equals 2kt plus c for some constant c. This is an important step, going backwards from a derivative to a function. It's a fact, and part of a more general theory that we'll explore in the final module, that if a derivative is constant, then the function that it comes from must be a linear function. If you think about this geometrically, if the slopes of all the tangent lines to a curve are constant, then the curve must be a straight line. That's what's happening here, though our variables are t and x, rather than the usual x and y. This is significant progress to see that v is x cubed and x is 2kt plus c, where k and c are some constants. We haven't yet used the given information that 10 litres of water dripped off the cube in the first 3 hours, which represents 10% of the volume, leaving intact 90% or 9/10 of the original volume. So V of 3 equals 9/10 of V of 0. We can use the fact that V equals the cube of x to rewrite this as the cube of x evaluated at 3 is 9/10 of the cube of x evaluated at 0. But we know that x evaluated at 0 is just the constant c. And x evaluated at 3 becomes 6k plus c. So we get a nice equation linking the constants k and c. We can rewrite this as 6k plus c cubed equals 0.9 of c cubed. And now solve for c, first by taking cube roots, to get 6k plus c equals a cube root of 0.9 times c. And some rearrangement gives finally c equals 6k divided by the cube root of 0.1 minus 1. We have an elegant relationship between the constants c and k, and can now ask for the time t at which the cube disappears by melting away, which is when the width x becomes 0, that is, when 2kt plus c equals 0. And we can sub in the formula for c in terms of k. We therefore want t such that this equation holds. Rearranging the information and noticing that k cancels out, we get that t equals 3 divided by 1 minus the cube root of 0.9. which our calculator tells us is approximately 86.9 to one decimal place. Thus, the answer to our original problem is that it takes almost 87 hours for the cube to melt away completely. If you look carefully at the mathematical analysis, you'll see that the final answer depends only on the proportion of the cube that had melted after 3 hours. Clearly, the warmer the temperature, the larger would be this proportion. One could generalize the problem to include this proportion as a variable parameter and deduce a general formula. It's interesting that the model predicts that the cube disappears completely. There is a time at which the width and the volume actually become zero. This is in contrast to exponential decay models, where the amount of the given substance tends towards zero, in fact very rapidly, but never actually reaches zero. In the case of our melting ice cube, the width turns out to be a decreasing linear function of time. In today's video, we discussed two contrasting examples that relied on the chain rule in order to progress towards a solution. The first example looked at the Gaussian bell-shaped curve related to the normal probability distribution used in statistics. The chain rule assisted us in finding the derivative of the associated function. In a future video, we'll go further with this example to find and analyze the second derivative. Though to achieve this, we'll use the product rule, which is introduced in the next video. In the second example, we performed a detailed analysis of a melting ice cube. We used the chain rule to connect together different aspects of the problem expressed in terms of derivatives. We obtained a model in which the main measure, the width of the cube, becomes a decreasing linear function so that the cube disappears completely. This is in contrast to exponential decay models where the value of the function decreases and gets arbitrarily close to zero but does not actually reach zero. Please read the notes, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. In today's video, we introduce, explain, and illustrate the product rule, which enables you to differentiate a product of expressions in terms of the derivatives of the factors. Consider a function y of x, which is a product of u and v, where u and v are themselves functions of x. The product rule states that the derivative of y with respect to x is u times the derivative of v plus v times the derivative of u, expressed this way using Leibniz notation. Equivalently, using function notation and the dash to denote the derivative, the product rule says y dashed equals u v dashed plus v u dashed. For example, let y be this product of a quadratic and a linear polynomial, and we want to find the derivative y dashed. We'll give two solutions. The first solution is direct, without using the product rule. We expand the brackets and gather together the terms to form this cubic polynomial, and then differentiate immediately to get the quadratic 6x squared plus 2x minus 23. The second solution uses the product rule. We write y as the product uv, where u equals the first factor, x squared plus 3x minus 4, and v equals the second factor, 2x minus 5, so that the derivative of u is 2x plus 3, and the derivative of v is 2. By the product rule, y dash equals uv dash plus vu dash, and we just put all the pieces together. Expand and simplify, and we get the quadratic 6x squared plus 2x minus 23, which of course agrees with our first solution. The solutions are the same, though the pathways are quite different. Which pathway you take depends on the problem at hand. Here's another example. Again, y is a product of two expressions involving x, and we want to find the derivative y dash. We can solve this directly by expanding the brackets, simplifying one of the expressions using an exponential law, and then differentiating directly piece by piece, using the fact repeatedly that the derivative of e to the kx is k e to the kx, where k is a constant, which is a result we established in an earlier video using the chain rule. And then tidying this up a little to get negative 3e to the 3x minus 2e to the negative x minus 2e to the 2x. An alternative solution is to apply the product rule, recognizing that y is the product uv. where u is the first factor, 1 plus e to the minus x, and v is the second factor, 2 minus e to the 3x, so that u dash quickly becomes negative e to the negative x, and v dash becomes negative 3e to the 3x. By the product rule, y dashed equals uv dash plus vu dash. We can put all the pieces together, expand, simplify, and gather terms to get finally negative 3e to the 3x minus 2e to the 2x minus 2e to the negative x, which agrees with our first solution. Use of the product rule is often the only natural way to proceed, and of course one tries to avoid going back to the original limit definition of the derivative. Here's such an example. We want to find the derivative y dash when y is the product of x with sine x. We'll present the solution using the product rule and Leibniz notation. The derivative is dy dx, which is d dx of x sine x, which by the product rule is the first factor x times the derivative of the second factor, plus the second factor sine x times the derivative of the first factor. The derivative of sine x is cos x, and the derivative of x is 1, so we get x cos x plus sine x times 1, which is simply x cos x plus sine x. Notice how, just in a few short steps, we're able to painlessly differentiate a sophisticated function. You're very unlikely to guess this answer, and extremely unlikely to navigate through the limit definition of the derivative, which would quickly become a quagmire in an example like this. You can appreciate the power of results like the product rule that provide such succinct and elegant solutions. We've only stated the product rule and used it, and you might be curious to know why it works. Here's a sketch of a proof why it works, and what follows now is quite advanced, tricky and intricate, so you shouldn't worry if you find it difficult to follow all of the details. Let y be a product of u and v where y, u and v are functions of x. A small change in x, called delta x, propagates a small change in y called delta y, where delta y is the difference between y evaluated at x and y evaluated at x plus delta x. That is, delta y equals y of x plus delta x minus y of x. But y is u times v, so this becomes u of x plus delta x times v of x plus delta x minus u of x times v of x. And now comes the magic sleight of hand. We insert minus u of x plus delta x times v of x plus u of x plus delta x times v of x, which altogether is 0, so it doesn't change the overall value of the expression. Now, why would we do such a thing, making it look so much more complicated? Well, it's common in proofs in mathematics to introduce terms to make things look more complex or elaborate, but to facilitate something that gets you past an obstruction, or leads to something ultimately more simple than what you started with. The trick here, using an expansion of 0, expressed as an addition and subtraction of the same thing, has lots of applications in algebra. You might remember we employed a similar trick to complete the square when manipulating quadratics in earlier videos. Observe that in the first two terms of this expression there's a common factor of u of x plus delta x, which we can bring outside of v of x plus delta x minus v of x. And in the second half there's a common factor of v of x, which we can bring outside on the right of u of x plus delta x minus u of x, which is significant progress, because v of x plus delta x minus v of x is just delta v, the change in v, and u of x plus delta x minus u of x is just delta u, the change in u. And now you start to see how everything is starting to simplify. We have delta y equals this combination, and we can divide everything through by delta x, setting up something that looks close to the derivative dy dx. The left-hand side, delta y over delta x, approaches the derivative dy dx as delta x approaches 0. And we can see what happens to each piece on the right-hand side. We have u of x plus delta x approaches u of x as delta x approaches 0. In fact, using a property called continuity. And throughout this discussion, all functions turn out to be continuous as a consequence of assuming that their derivatives exist, which is a subtle point explained in more advanced courses in calculus. And delta v over delta x approaches dv dx, delta u over delta x approaches du dx, and v of x just remains as v of x. We can rewrite the right-hand side as u of x dv dx plus v of x du dx, or in function notation y dashed equals uv dash plus vu dashed, and we've finished the proof of the product rule. In today's video, we introduced and illustrated the product rule, which enables you to differentiate a product of expressions in terms of the derivatives of the factors. We then sketched a proof, which involves some subtle algebraic manipulation and the limit definition of the derivative using Leibniz notation. Please read the notes, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. In today's video, we apply the product rule to further explore the behaviour of the Gaussian curve y equals e to the minus x squared using the second derivative, and to give a proof by mathematical induction of the formula for differentiating a power of x where the exponent is a positive integer. In an earlier video, we used methods of curve sketching to go a long way towards describing the graph of the function y equals e to the minus x squared. We observed that the y-intercept is 1, that there are no x-intercepts, and the x-axis is a horizontal asymptote. We used the chain rule to find the derivative of y dash and built its associated sign diagram. We put this all together, noting the y-intercept, the asymptotic behaviour of the x-axis, both to the far left and far right, and the fact that there's a turning point when x equals 0. Because the curve is increasing to the left and decreasing to the right, it's natural to fill in the rest of the curve to obtain this bell shape. To create this shape, there appear to be two natural inflections where the curve changes concavity. To be sure about the way the concavity changes, we need to go further and investigate the second derivative y double dash. Because the first derivative is quite complicated, we'll use the product rule to work out its derivative. We have y dash is minus 2x times e to the minus x squared, which we can write as u times v, where u is minus 2x and v is e to the minus x squared. Then u dashed is minus 2, and v is our original y, so v dash is in fact the same as y dash. By the product rule, y double dash, which is the derivative of y dash, is u v dash plus v u dash, which is this expression, which becomes, after a couple of steps, 2 times 2x squared minus 1 times e to the minus x squared. And notice that the factor e to the minus x squared is always positive. Hence the second derivative is 0 precisely when 2x squared minus 1 equals 0. That is, when x equals plus or minus 1 over the square root of 2. And we can build the sign diagram, noting the important points for x, where y double dashed is 0, and the pattern of plus, minus, plus, producing a pattern of concave up, concave down, concave up as we pass from left to right. This tells us that there are inflections when x equals plus or minus 1 over root 2. We can update our previous information in sketching the Gaussian curve, confirming what we expected the concavity might be and to locate the points of inflection. This now completes a thorough investigation of the curve. Our second application of the product rule is to provide a proof of the formula for the derivative of x to the n. You'll recall that we carefully proved from the limit definition that the derivative of x squared is 2x and the derivative of x cubed is 3x squared. These are special cases of a general pattern that the derivative of x to the n is n times x to the n minus 1, a result that we used on several occasions without explaining why it's true. The aim of this next application is to carefully prove this formula for all positive integers n, that is, for n equals 1, 2, 3, 4, and so on. The argument that I'm about to give is called, more formally, a proof by mathematical induction, which is a very common and powerful proof technique in mathematics, which you can read about if you wish, though I think you'll be able to follow the main ideas. For many of you, this might be your very first proof by mathematical induction and will serve you well as a prototype example of the technique in case you go on to do more higher mathematics. The claim that we're proving is in fact infinitely many statements as n passes through the set of positive integers. We've already carefully checked this in the cases n equals 1, 2 and 3. The case n equals 1 matches up nicely to the fact that the derivative of x is 1. The cases n equals 2 and 3 match up with facts we already know. The problem for us now is to somehow prove the cases n equals 4, 5, 6 and so on. We don't want to spend a lot of time and effort on each case, and we certainly don't have an infinite amount of time to go through each and every positive integer separately. This is where you might start to see the power of thinking abstractly. What follows is like a thought experiment. Suppose that, by whatever means, we've been able to prove the formula for some particular positive integer n. And let's refer to this formula, only for this particular n, by star. In formal proofs, the statement star is referred to as the inductive hypothesis. Our aim is to prove statement star with n replaced by the next positive integer n plus 1. This new statement will be that the derivative of x to the n plus 1 is n plus 1 times x to the n. We can refer to this as double star. If we can prove that star implies double star, then we get an instantaneous infinite chain reaction from the case n equals 1, and then star must hold for all positive integers. Why are we able to say that? Well, we've verified star for n equals 1, and also for n equals 2 and 3. That's not in fact important. It's enough that we've verified it for n equals 1. Star implying double star means the formula must be true for 1 plus 1 equals 2, and then feeding 2 back in for n for 2 plus 1 equals 3, and then feeding 3 back in for n for 3 plus 1 equals 4, and repeating for 4 plus 1 equals 5, for 5 plus 1 equals 6, and so on forever, racing through all of the positive integers instantaneously. So let's prove double star after supposing that star is true for some particular positive integer n. Notice that x to the n plus 1 is the product of x to the n with x. So we can apply the product rule to conclude that the derivative is x to the n times the derivative of the second factor plus x times the derivative of the first factor, which becomes x to the n times 1 plus x times, and at this point we invoke statement star, n times x to the n minus 1. And then this tidies up in a few steps to become n plus 1 times x to the n. This establishes the statement double star. Hence star implies double star. This implication is called the inductive step in formal proofs by mathematical induction. It shows, by the chain reaction effect that I mentioned earlier, that star holds for all positive integers n. This completes this particular application of the product rule for all positive integers n and for all real numbers x. If we restrict attention to positive real numbers x only, then we can go much further and prove that to differentiate a general power, say x to the alpha, for any real number alpha, you again bring the exponent to the front and make a new exponent by subtracting 1. This very general fact follows from the chain rule and properties of logs and exponentials. To see why, express x to the alpha as e to the alpha times ln of x. And then the derivative of x to the alpha becomes the derivative of e to the u, where u equals alpha times ln of x, which becomes d du of e to the u times du dx by the chain rule, and each piece is then straightforward. The derivative of e to the u with respect to u is just e to the u, and the derivative of u with respect to x is just alpha over x, because the derivative of ln of x is 1 over x. Thus the derivative becomes e to the u times alpha over x, which can be rewritten as x to the alpha times x to the minus 1, which simplifies to alpha times x to the alpha minus 1. And this completes the proof of our formula. In today's video, we applied the product rule, first to complete our curve sketching analysis of the Gaussian curve from an earlier video, in particular to understand the curve's behaviour with respect to concavity and to locate the inflection points. And secondly, to prove that the derivative of x to the n is n times x to the n minus 1 for all real numbers x and all positive integers n. This proof, in fact, is an example of the technique of proof by mathematical induction. We then used the chain rule and properties of logs and exponentials to see how to generalise this formula for arbitrary real exponents. Please read the notes, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. In today's video, we use calculus to solve several contrasting problems in optimization, which means to find the smallest or largest value of some quantity of interest. In this first problem, we're asked to minimize the sum of a real number and its reciprocal. You can experiment with a few numbers to get a feeling for what the answer might be before we actually do the calculus. We want to find the smallest sum that results by adding a number to its reciprocal. You may well guess the answer, but we want to be absolutely sure. To turn this into mathematics, we put y equals f of x equals x plus 1 over x, which can be rewritten as x plus x to the minus 1. The strategy is to use the derivative to find the turning point, which should tell us what the minimum might be. The derivative is y dash equal 1 minus x to the minus 2, which we can rewrite in a couple of steps as x squared minus 1 over x squared. So that y dashed is 0 when x equals plus or minus 1. Note that y dashed is undefined when x equals 0. And so we get the following sign diagram, with the pattern positive, negative, negative again, positive, which indicates the pattern increasing, decreasing, decreasing again, increasing, with a maximum when x equals minus 1 and a minimum when x equals 1. In fact, we only need to focus on positive x and the corresponding part of the sign diagram, highlighted here, producing a global minimum for x greater than 0, occurring when x equals 1, with value f of 1 equals 2. This solves the original problem. The answer is that the minimum sum of the positive real with its reciprocal is 2, and this occurs by adding 1 to its reciprocal. The mathematics tells us it's impossible to do any better than this. Though we don't need to, we can, if we like, graph the curve y equals x plus 1 over x, which splits into two branches, with the y-axis being a vertical asymptote and the line y equals x being an oblique asymptote. The branch of the curve in the first quadrant is directly relevant for our original problem, and the turning point with coordinates 1, 2 corresponds to the solution. In the next optimization problem, we're asked to build a rectangular enclosure using 100 metres of fencing in order to maximise the area. What should we do? For example, if we make a thin rectangle, only 5 metres deep and 45 metres wide, then we use up the 100 metres of fencing and the area becomes 225 square metres. If we try making it 10 metres deep and now 40 metres wide, we get a larger area of 400 square metres. But we can do better. If it's 20 metres deep and 30 metres wide, we increase the area to 600 square metres. We can still do better. If it's 25 metres deep and 25 metres wide, then the area becomes 625 square metres. Notice now that we've produced a perfect square, and it looks like there's no way to make the area any larger. It seems reasonable to guess intuitively that the perfect square should solve the problem. Let's do the maths to see if it confirms our intuition. Here's a diagram representing a general enclosure with side lengths x and y metres. Note that the diagram is just a guide to assist us in creating the mathematics. In fact, we're expecting to get a perfect square in the end, but we're not sure, so just try to imagine any old typical rectangle, but realise this is only to help set up the mathematics. Denote the area of the rectangle by a square metres so that a is the product x, y. The constraint is that we only have 100 metres of fencing, so we add up all the sides of the rectangle, that is x plus y, plus x again, plus y again, to get 100. Then 2x plus 2y equals 100, so that x plus y equals 50. Hence y equals 50 minus x. We can now express a in terms of x only, because a is x times y, which is x times 50 minus x, which expands out into the quadratic 50x minus x squared. The derivative, the 80x, becomes 50 minus 2x, or 2 times 25 minus x. Hence the 80x is 0 when x equals 25. And we can now build its sign diagram with pattern positive, negative, and increasing, then decreasing, with a maximum occurring when x equals 25. It follows that the area A is maximised when x and y are both equal to 25. So indeed, the enclosure turns out to be a perfect square, as we suspected all along, with maximum area 625 square metres. The maths guarantees that there's no chance of doing better than this. The area function A turned out to be a quadratic in x, so of course we can also visualise the solution in terms of the associated parabola. Here's the information we used about the derivative, and it matches perfectly with the actual parabola, which passes through the x-axis at 0 and 50, with apex exactly halfway between, corresponding to the solution. The problem is constrained by having non-negative side lengths, and if x equals 0 or x equals 50, at the boundaries of the actual physical domain, the rectangle becomes infinitely thin with 0 area. Note also that the second derivative is negative 2, which is less than 0, so the curve should be concave down, which indeed corresponds to the fact that the parabola is facing downwards. Our final optimization problem is quite difficult and uses all of the techniques that we've been building up over several videos. We're unlikely to be able to guess the answer, so we rely on producing a carefully developed mathematical solution. We revisit the Statue of Liberty, which you might remember is 46 metres high, standing on a pedestal which is also 46 metres high. The problem is to find the horizontal distance x metres from the base of the pedestal that maximises the angle theta subtended by the statue, and also to find this largest angle. It's useful, especially in developing formulae, to refer to the common height of the statue and pedestal using the symbol h. Though it hasn't been asked for in the problem, we give a name phi to the angle subtended by the pedestal. We then insert into the diagram a vertical length of height 2h, the combined height of the statue and the pedestal, opposite the two angles, that creates this figure involving a large right-angled triangle. Focusing on the smaller right-angled triangle with angle phi, we see that the tan of phi is the opposite over the adjacent, that is h over x. The larger right-angled triangle has angle theta plus phi, and tan of this combined angle is 2h over x. Hence phi becomes inverse tan of h over x, and theta plus phi becomes inverse tan of 2h over x. So that subtracting phi, theta becomes inverse tan of 2h over x minus inverse tan of h over x. So finally we're able to express theta as a function of x. Remember that we want to maximise theta, so it should be useful to look at the derivative d theta dx. Since theta is a difference of two expressions, its derivative will be the difference of the derivatives of the expressions. We apply the chain rule to each piece using the substitutions u equals 2h on x for the first piece and v equals h on x for the second piece. But u can be written as 2h times x to the minus 1, so its derivative with respect to x is minus 2h times x to the minus 2, which can be rewritten as minus 2h over x squared. And similarly, the derivative of v with respect to x becomes minus h on x squared. The other ingredient we need is the fact that the derivative of inverse tan of x is 1 over x squared plus 1. The rule for the function whose graph is the Witch of Maria Agnesi that we discussed in detail in an earlier video. And now we just carefully insert all of these bits and pieces into the expression for d theta dx. to produce this expression involving u, v, h and x, which becomes an expression involving just h and x, which you can check simplifies to this expression. We now put everything over a common denominator and carefully simplify until we finally get the fraction below in terms of x and the constant h. It's a lot of careful algebraic manipulation, probably the most difficult and intricate so far in this course, but it's worth the effort. Though this might look complicated, notice that a large portion of this expression, circled in pink, is always positive. Remember, it's the changing sign of the derivative that gives us information about the turning points. In this case, the sign of the derivative is completely determined by the sign of the expression 2h squared minus x squared, highlighted here in blue. Observe that the derivative is 0 precisely when x squared equals 2h squared. And this occurs when x equals the square root of 2 times h, where h, remember, is the height of both the pedestal and the statue. Note that we're only interested in positive distances for x, so we can ignore the negative square root. We can now build the sign diagram for the derivative, with the important point root 2 times h for x where the derivative is 0, with pattern positive, negative, increasing, then decreasing, with a maximum when x equals root 2 times h. This shows that the angle subtended by the statue is maximised when the distance x is root 2 times h, where h equals 46, which evaluates to about 65 metres. The maximum angle becomes this expression inverse tan of root 2 minus inverse tan of 1 over root 2, which evaluates to about 19.5 degrees. Notice that the final expression does not depend on h, which cancels out in the process of simplifying the answer. The maximum angle is nearly 20 degrees, and this works regardless of the height of the statue and pedestal. By carefully checking the mathematics, you see that we only need that they are of the same height to get this particular maximum angle. Whatever h happens to be, the horizontal distance that achieves this maximum angle will be root 2 times h, which of course does vary with h. In our case, this horizontal distance turns out to be about 65 metres. In today's video, we discussed and solved 3 contrasting optimization problems. All of the solutions relied on determining and understanding the behaviour of the sign of the derivative. The first 2 problems had solutions that one could reasonably guess in advance, either by experimenting or thinking about the problem intuitively. The third problem, however, was very difficult, with a final answer that I think will be impossible to guess. The derivation relied on the derivative of the inverse tan function, the Witch of Maria Agnesi, together with quite intricate algebraic manipulations. I hope you'll be able to follow through and check all of the details. By doing so, you'll develop very strong technique and a thorough understanding of the underlying principles. Please read the notes, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. Welcome back. We've just completed the 3rd and 4th modules introducing and discussing the differential calculus, which is really all about studying slopes of tangent lines to curves. This final module introduces and discusses integral calculus, which is really all about the study of areas under curves. Remarkably, slopes of tangent lines and areas under curves turn out to be intrinsically linked, leading to the fundamental theorem of calculus. This final module begins by illustrating how one can use areas under velocity curves to estimate displacement, using averages of lower and upper rectangular approximations, and replicating thought experiments, originally due to the ancient Greeks, involving limits of approximations, to discover the formula for the area of a circle and the area under a parabola. We then formalize the method of Riemann sums, using rectangular approximations to areas under curves over a given interval, leading to the definite integral, which is defined to be the limit of the Riemann sums and captures precisely areas under a curve. We can calculate the definite integral exactly under certain conditions, using the fundamental theorem of calculus, providing a simple and elegant formula involving taking antiderivatives, which reverses the process of forming derivatives. We introduce indefinite integrals and illustrate the method of integration by substitution, closely related to the chain rule that you learnt about in the previous module. We discussed properties of odd and even functions related to rotational and reflectional symmetry, and the logistic function, which modifies exponential growth by introducing an inhibition factor with important applications to population dynamics. Finally, we come full circle and provide you with some context and insight about how calculus was originally conceived by Newton in the 17th century, by his remarkable estimate of the escape velocity of a rocket. Again, we hope that you'll find the material interesting and stimulating, that you find the videos helpful, and the practice and challenges provided by the many exercises beneficial. I look forward very much to your continued attention and participation. In today's video, we go through an extended example involving data points from the velocity curve of an accelerating vehicle to estimate the displacement or distance travelled. This exemplifies the idea of using the derivative to get information about the original function. As you'll see, the calculation or estimation of areas under curves is the key to moving backwards, so to speak, from the derivative. The underlying reason is that derivatives are related to instantaneous rates, which are limits of fractions. To undo a fraction, you expect multiplication to be involved, and of course multiplication of real numbers is related to and may be defined in terms of areas of rectangles. This is our first foray into integral calculus. Two key words that will become familiar to you are integration and anti-differentiation. In common language, to integrate means to put things together into a coherent whole. The word anti-differentiate is not part of common language and only used by mathematicians, and it means to undo differentiation, in a sense that we can make precise, that is, to go backwards from derivatives to the functions from which they came. For us, putting things together will have a technical meaning of finding areas, which involves multiplication, and converting rates into quantities, which is some kind of process by which we unpack the derivative. The central theme is to use information about the derivative to gain information or insight concerning the original function. Think of all that hard work in the previous two modules where we created derivatives. Now we're going in the reverse direction, developing techniques for undoing the derivative. This leads naturally into setting up and solving differential equations, which are equations in which at least one derivative appears somewhere. The study of differential equations would be for you a natural continuation following on from this introductory course in calculus. Working backwards from the derivative includes, for example, knowing velocity, the instantaneous rate of change of displacement, to get back to or find displacement, or knowing acceleration, the instantaneous rate of change of velocity, to get back to or find velocity, or knowing the rate of absorption of a drug, to determine the amount of the drug that's been absorbed, or knowing the rate of growth of a colony of bacteria to determine or predict the size of the population, or knowing the rate of spread of a disease to estimate or predict the number of people that will become infected. Let's focus now on perhaps the most important motivating example, velocity, denoted by v, the derivative of displacement, denoted by x, both of which are functions of time t. And we can keep in our minds that v is dx dt. If we have enough information about v, and even without a formula for dx dt, then we can find or estimate displacement x by finding areas under the velocity curve. Here's a typical velocity curve, and we're interested in the displacement over a particular interval of time as t passes, say, from a to b. We move up to the curve from t equals a and t equals b to create a region in the plane, coloured here in green, bounded by the curve, the horizontal axis and the vertical lines through a and b. It turns out that this green area represents the change in position, the displacement x of the object over this particular time interval. To try to understand this phenomenon, we first look at the simplest case when the velocity v is constant, say c, so that the velocity curve is a horizontal line passing through c on the vertical axis. We move up to the curve from t equals a and t equals b and obtain a rectangular region, coloured green in this diagram. And to make it more concrete, let's measure the velocity in, say, kilometres per hour and time t in hours. And you could imagine that we're travelling in a car along, say, a straight road. Note that in the diagram, the scales on the horizontal and vertical axes are typically different and can change according to the numbers involved. For example, if c equals 60, a equals 5 and b equals 9, then we'd be travelling at 60 kilometres per hour for 4 hours, so the distance travelled will be 4 times 60 equal to 240 kilometres. Represented exactly by the area of the green rectangle of width 4 units and height 60 units. In general, the width of the rectangle is b minus a and the height is the constant c. So the green area is the product c times b minus a, exactly representing the number of kilometres travelled by multiplying the constant velocity by the number of hours spent travelling. Of course, in practice, the velocity fluctuates. Let's go through a typical example. To estimate the distance travelled by a car that is accelerating over an interval of 10 seconds so that its speed keeps increasing. We'll assume the car is travelling along a straight road in one direction, so we can use the words velocity and speed interchangeably. The velocities were measured every 2 seconds and recorded here in metres per second to keep the units consistent and to simplify the calculation that follows. Note, to put this in context, in case you're used to measuring speeds in kilometres per hour, that 90 kilometres per hour converts to 25 metres per second. You can see from the table that the car must have been going really fast after about 5 or 6 seconds. We can introduce a horizontal axis for time t and a vertical axis for velocity v and plot the points from the table. We can join the points to get what we expect will be a reasonable approximation to the true velocity curve of the car. Now, in the first 2 seconds, the car accelerates from 5 to 14.5 metres per second. So it's always travelling at a speed greater than or equal to 5 metres per second, and most of the time considerably faster than that. Any car moving at a constant speed of 5 metres per second would travel a shorter distance, which is represented by the green rectangular area in the diagram. This green area, sitting beneath the curve, then becomes a lower bound for the distance travelled by the accelerating car over the first 2 seconds. Similarly, we can draw in a rectangle for the period from 2 to 4 seconds, whose area represents the distance travelled by a car moving at the constant speed of 14.5 metres per second. This again is a lower bound for the distance travelled by the accelerating car, which is always moving at a speed greater than or equal to 14.5 metres per second over this interval. We can continue drawing in rectangles beneath the curve for time t equals 4 to 6 seconds, t equals 6 to 8 seconds, and t equals 8 to 10 seconds. We get a lower bound on the actual total displacement of the accelerating car by adding up the areas of all of these green rectangles or columns sitting beneath the curve. All of the columns have width 2 units, so to get each successive shaded area we just multiply the heights by 2. As the car is accelerating, its speed keeps increasing throughout, so we just take the velocities in the table as heights of the rectangles in succession from 5 all the way up to 31. And this sum quickly evaluates to 200. Thus, a lower bound for the distance travelled by the car becomes 200 metres. The previous estimate used rectangles sitting beneath the curve. If we use upper bounds for the velocities on each of these subintervals, then we build rectangles that sit above the curve. In this diagram, we enlarge the green area in each case with a blue area, so that the combined blue and green areas form columns that encompass all of the area under the curve. The area of each larger rectangle or column now represents the distance travelled by moving at a constant speed greater than or equal to the speed of the accelerating car on any particular interval of 2 seconds. By adding up all of the areas, we should get an upper bound for the total distance travelled. Again, the width of each column is 2 units, and the heights now move from 14.5, an upper bound for the first interval, successively through the heights in the table, finishing at 32.5, an upper bound for the last subinterval. These areas all add up to give 255. Hence we estimate an upper bound for the true distance travelled by our car to be 255 metres. Putting this together, we've found a lower bound and an upper bound, and know that the true distance travelled is somewhere in between. The number halfway between these two bounds seems likely to be a reasonable estimate, and that number is just the average, which turns out to be 227.5. Hence, finally, we estimate that the car travelled about 227.5 metres over those 10 seconds. In fact, we expect this average to be a slight underestimate, as you can see from the sketch that the curve appears to be concave down. I'll try to explain the significance of the concavity. Consider any rectangle, split it into two pieces, and colour the lower part of the rectangle green and the upper part blue. Now draw a diagonal across the upper part upwards from left to right, and colour in pink everything below this diagonal. This pink area is the green area plus half of the blue area, which can be expressed as 1/2 of the green area plus the combined green and blue areas. In other words, the pink area is the average of the smaller and larger areas from the previous two diagrams. The shape coloured in pink is an example of a trapezium in geometry. In our example with the accelerating car, over any particular interval of 2 seconds, we had a green rectangle sitting below a fragment of the velocity curve, and a combined green and blue rectangle sitting above the curve. And there's this trapezium shape, which we've coloured in pink. And as I've just explained, the pink area is the average of the areas of the upper and lower rectangles. Let's add to this diagram a curved fragment joining the points of the diagonal that creates the trapezium, and draw it so that it's concave down, as in our physical example. Because of the concavity, there's a tiny piece of area not included by the pink shading, which we've coloured beige. The pink area, the area of the trapezium, therefore becomes a slight underestimate of the area under this curved fragment. Nevertheless, the trapezium becomes an excellent approximation for the area if the curved fragment is almost a straight line. This leads to a technique known as the trapezoidal rule for approximating areas under curves using trapeziums, which you can read about if you wish. In the case of our velocity curve, you can see visually that, though concave down overall, the individual fragments of the curve are close to being straight lines. So we expect this average of the upper and lower bounds, which is the aggregate of the averages of the areas of the lower and upper rectangles, to be a very good, if not excellent, approximation to the true distance travelled by the car. The previous estimate was based on a table with 6 data points. Clearly, if we had more data, then we expect to be able to improve our estimate. Suppose that the velocity was measured every second instead of every 2 seconds. Here's a new table with the original data, but including measurements taken also for each second in between. As before, we can plot all of the points and join them with a smooth curve. Again, we build rectangles that sit beneath the curve, and then shade in their areas in green. We can build rectangles that sit above the curve by extending the lower rectangles, and shade in the additional areas in blue. As before, we can calculate lower and upper bounds for the area under the true velocity curve. Note that the width of each rectangle or column is 1 unit, since the time intervals are now only 1 second each. Adding up the green areas gives a lower bound of 216, whilst combining the green and blue areas gives an upper bound of 243.5. We can again take the average to produce a revised estimate of 229.75 metres for the distance travelled by the car. Because the curve appears to be concave down, we still expect this to be a very slight underestimate. The curve fragments appear to be very close to straight line segments on each of these now very short time intervals, so we expect to have produced an excellent estimate of the distance travelled. In today's video, we began with some general remarks concerning moving backwards, so to speak, from rates to original quantities, or in mathematical language, using the derivative to gain information about the original function. Moving backwards from velocity to displacement becomes a prototype for this phenomenon, and we saw that the connection involves finding areas under curves. We discussed in detail how we could use a table of values for the velocity to estimate the distance travelled by an accelerating car over a given time interval. We used rectangular approximations that sit both below and above the velocity curve to get lower and upper bounds for the distance travelled. By taking the average of these bounds, we appear to get a very good, if not excellent, approximation to the true displacement. Taking averages is in fact related to using trapezoids to estimate the area under a curve. Please read the notes, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. In today's video, we go through two important and quite subtle calculations, both of which were known to the ancient Greeks. We use the perimeter to find a formula for the area of a circle, and calculate precisely a certain area bounded by a parabola in the xy plane. We begin with two very familiar areas. The area of a rectangle, of course, is the base times the height, and in fact this is how one defines multiplication of two positive real numbers in the first place. The area of a triangle, I expect you know, is half the base times the height. Already something interesting is happening, as this enables one in principle to find areas of any geometric figure bounded by straight lines, since such figures can be split up into triangular pieces. To see why this formula holds, one has to relate a typical triangle in some way to rectangles. In this particular figure, one can form an altitude of height h from the apex of the triangle to meet the horizontal base of length b, and then use it to form two rectangles that enclose the triangle. One of width b1 and the other of width b2, say. And notice that the area of the triangle, coloured beige, splits up into two pieces, the first of which is exactly half the area of the rectangle of width b1, and the second of which is exactly half the area of the rectangle of width b2. So putting together the areas of these rectangles, and using the fact that b1 plus b2 equals b, we get that the beige area is 1/2 of b times h. This isn't the most general diagram for a triangle, but you can easily adapt this argument to all triangles. What about areas bounded by curves that are not straight lines? The most classic example would be a circle, say of radius r. I expect you know the formula for the area of a circle, but do you know why it works? We discussed the perimeter in a very early video, which we can call P, and noted the fact that P equals pi times the diameter, or 2 pi times the radius. We're going to engage in a thought experiment used by the ancient Greeks. Imagine dividing a circle into n pieces called sectors, which are like pieces of pizza. And here, for example, n equals 4. And dividing all the pieces in half, we can get n equals 8. And in half again, we can get n equals 16. We can imagine going on dividing the sectors in half indefinitely, and they get thinner and thinner. Suppose we stop halving the segments at some stage, and join up the points on the circle using successive small line segments where all the radii emanating from the centre meet the circle, to form this green polygonal shape that appears to be hugging the perimeter. Suppose we do this so that all of the sectors have exactly the same shape, and here's a picture of one enlarged, including the small green line segment joining up the 2 points on the perimeter. The drawing is not too thin to make it easier to follow the mathematics associated with the diagram. We have the two radii of length r emanating from the centre, which form a triangle together with the green line segment of length b, say. Denote the height or altitude of the triangle by h, say. Notice that h is approximately equal to the radius r, because the altitude emanating from the centre of the circle almost reaches the perimeter. If you imagine making more and more thinner sectors by allowing the number n of sectors to become arbitrarily large, then you can see h getting closer and closer to the radius. We can express this precisely using limit notation. The limit as n goes to infinity of h is r. What about the area of the sector? It falls naturally into two pieces: the area of the triangle, coloured green, bounded by the two radii and the line segment, and a little bit left over between the line segment and the perimeter, coloured beige. The area of the sector is approximately the area of the triangle, which is half the base b times the height h. Here's our circle again, split up into n sectors of the same size and shape, each with area half the base b times the height h, and the limit as n goes to infinity of h is the radius r. Observe that if we circumnavigate the circle using the green line segments of length b, we get n lots of b, approximating the perimeter p. The more we subdivide the circle into thinner and thinner sectors, the closer n times b will be to the actual perimeter p. In fact, the limit as n goes to infinity of n times b is p. How does all of this information relate to the area of the circle? Here, all the triangles approximating the sectors have been coloured in green. There's only a tiny bit of area of the circle not included, which you can hardly see between the green line segments and the perimeter. So the area of the circle is approximately the sum of the areas of the triangles, which is n times a half bh, which we can rewrite as a half of nb in brackets times h. The approximation gets better and better as n gets larger, and in fact the area is precisely the limit of this expression as n tends to infinity. But we have enough information to evaluate this limit. The constant half comes out the front, and the limit of a product is the product of the limits. The limit of nb is just the perimeter p, and the limit of h is the radius r. But the perimeter is 2 pi times r, so the expression a half pr becomes a half of 2 pi r times r, which simplifies quickly to pi r squared. Thus we answer our earlier question. The formula for the area of a circle is A equals pi r squared. Look carefully at this in light of our knowledge of the derivative. The area A is pi r squared, and the perimeter P is 2 pi r. The derivative dAdr is also 2 pi r. This isn't a coincidence. We call the area an antiderivative of the perimeter, and soon you'll see this fact in a wider context. Functions associated with areas bounded by curves are intrinsically related to the functions describing the curves by going backwards from differentiation. The Greeks also thought carefully about areas associated with another classical curve, the parabola. However, a parabola goes on forever and doesn't close up like a circle. Nevertheless, we can position a parabola in the xy plane and consider the area between the curve and the x-axis over some particular interval. Let's simplify everything as much as possible and just ask for the area under the parabola y equals x squared for x between 0 and 1, shaded here in green. If you use graph paper, as in this diagram, you can get a very good estimate just by adding up tiny subsquares and fragments of subsquares. If you do this, you can probably make an educated guess as to what the answer might be. But we'll try to emulate the Greeks and find out the exact answer without guessing. Remember, in the previous video, we estimated displacement from the velocity curve by using rectangular approximations. We do something similar here. First of all, divide the interval from 0 to 1 on the x-axis into n equal subintervals of width 1 on n, where n is a positive integer. You can think of n as large, though in this particular diagram, n equals 6. Then move up to the curve and build rectangles that sit above the curve. It's enough for us to consider upper rectangles only, though you can perform a similar calculation using lower rectangles if you wish. Then we shade in the areas inside the rectangles, which includes the green area under the curve, and extra areas coloured in beige which sit above the curve but still inside the rectangles. Note that all the rectangles have a width of 1 on n units. Adding up the areas of these upper rectangles, we get 1 on n times 1 on n squared for the first rectangle, since the height is the value x squared when x equals 1 on n, plus 1 on n times 2 on n squared for the second rectangle, plus 1 on n times 3 on n squared for the third rectangle, and so on all the way up to 1 on n times n on n squared for the final rectangle. Notice how we get 1 on n cubed times 1 squared plus 2 squared plus 3 squared all the way up to n squared. Denote the green area under the curve by A. Then A is approximated by this expression for the areas of the rectangles. As n gets larger and larger, the rectangles get thinner and thinner, and the extra beige area becomes vanishingly small, so that A becomes the limit of this expression as n goes to infinity. We have a chance of evaluating this limit if we can understand or control the sum of all of those squares inside the brackets. A very succinct way of writing a sum like that is to use sigma notation, using the Greek letter capital sigma as an abbreviation for repeated addition. Here we're adding up I squared as I ranges from 1 up to n. If you're not sure about sigma notation, I suggest you pause the video and read about it in the accompanying notes. We're going to use it a lot in the rest of the video. I should also warn you that what follows is quite advanced material and we move very quickly. Don't worry if you don't follow every step, and pause the video frequently if you want to check each of the manipulations slowly and carefully. Now we do something that looks totally bizarre and unexpected, known as the telescoping sum method. Though we want to sum squares, we look at n cubed and open it up like a telescope by successively adding together a cube take away the cube of 1 less, climbing all the way down to 1 cubed take away 0 cubed. Now this looks absurdly complicated, but we're just playing around with 0. You might remember how we used expansions of 0 in the trick of completing the square, and also improving the product rule for differentiation. Here we're using the same trick repeated many times to produce this huge telescope. You can see how terms cancel out, producing zeros all the way to the end, where we get to 0 cubed, which is also 0. So this huge, long telescope really is just n cubed, expressed in a complicated way, for the purpose of discovering something quite remarkable and surprising. Now we use sigma notation to express all of this very concisely. Again, if you're not used to sigma notation, please pause the video and read about it in the accompanying notes. Here we can rewrite n cubed as a sum of I cubed minus I minus 1 cubed as I ranges from 1 to n. Let's play with this expression that uses sigma notation. What follows is quite intricate, and you should pause the video to check the steps if I go too fast. There are also more detailed explanations in the notes. We first expand the difference of the two cubes and see that it simplifies to 3i squared minus 3i plus 1 because of the cancellation of I cubed with minus I cubed. But the sigma notation means a gigantic sum, so we can split this into 3 separate pieces. The first piece becoming 3 times the sum of I squared, the second piece becoming minus 3 times the sum of I, and the third piece the sum of 1 n times, which is just n. So now we get this even more complicated way of expressing n cubed. Where is all of this leading? There's another surprise often referred to as the trick of Gauss. There's a story about Gauss when he was a child. The teacher asked the class to add up all the numbers from 1 to 100, and almost immediately the pupil Gauss answered 5,050, astonishing everyone. How could a child add up 100 numbers so quickly in his head? Well, let's think more generally about adding up all the numbers from 1 to a very large number n and call the total sum s. Gauss's trick is to write the same sum s but backwards, and then add it to itself. Notice how the numbers line up, and you get n copies of n plus 1 on the left and twice s on the right. So that 2 times s is n times n plus 1. So dividing by 2, the sum s becomes this nice formula, n times n plus 1 over 2. So that's how Gauss did it. He multiplied 100 by 101 and divided by 2, which is 5,050. What's the relevance of this? You can see in our complicated expression for n cubed, we have the sum of I as I ranges from 1 to n, which is just our sum S that we evaluated using the trick of Gauss. So let's sub that expression in and see what happens. We get yet another complicated expression for n cubed. But before throwing up our hands in despair, notice that we've made remarkable progress. The thing we're really interested in finding related to our area problem for the parabola is the sum of squares, and you can see it trying to hide inside this equation. But that's no problem for us because we just rearrange the furniture using algebraic manipulation and isolate the sum of the squares. And then just carefully simplify the expression, which involves powers of n. You can pause the video perhaps and check each step if you like. The upshot is that we get this very elegant formula for the sum of squares. Now we can complete our calculation of the area under the parabola. Remember, we called the area A and saw before that A is a limit, as n goes to infinity, of 1 over n cubed times the sum of the squares, 1 squared up to n squared. So now, using our expression for the sum of squares, A becomes a limit of 1 over n cubed times this expression. We can cancel one of the n's and just use our tricks for evaluating such limits, dividing through the top and the bottom by n squared. And seeing that the answer quickly simplifies to 1/3. Thus, finally, we get the answer, in fact discovered by the Greeks thousands of years ago, that the area under the parabola between 0 and 1 is 1/3. Exactly. No approximations. You can see that this was a really difficult calculation and much more difficult than finding the area of a circle. Later in this module, we'll learn a method that exploits the antiderivative of x squared, and the answer of 1/3 will drop out in a couple of steps. However, I wanted you to see this extended, bare-handed calculation as it involves so many different ideas and techniques that you can apply in all sorts of other mathematical settings. In today's video, we discussed two examples of finding areas bounded by curves. Firstly, to use the perimeter to find a formula for the area of a circle, and secondly, to calculate the area under the parabola y equals x squared in the xy plane over the interval from 0 to 1, which turns out to be exactly 1/3. It's remarkable that by using fairly abstract ideas involving approximations and taking limits, we get exact answers in both cases. In the second example, we used sigma notation, which is an abbreviation for adding lots of things together, telescoping sums, which involves elaborate ways of playing around with 0, the Gauss trick of adding successive numbers together, and lots of algebraic manipulation and our techniques of evaluating limits. Please read the notes, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. In today's video, we formalised the method that we've been using in earlier videos, where we estimated areas using rectangular approximations. This leads to the method of Riemann sums, which involves partitioning the interval of interest into tiny subintervals, over which rectangles are formed, reaching up to the curve. As the partitions get finer and finer, as the distances along the x-axis between successive points tend to 0, the Riemann sums approach a limit, which we think of as the area under the curve. This area is called the definite integral, denoted by a stylized S called an integration symbol, which you can think of as some kind of continuous sum. The symbolism is all due to Leibniz, the great visionary from the 17th century. That wasn't until the 19th century that the mathematics had evolved sufficiently to be regarded as having secure and rigorous foundations. We describe the method of Riemann sums, attributed to the famous 19th century mathematician Bernhard Riemann, though in fact the method and proofs were the culmination of combined efforts of mathematical evolution by many mathematicians spanning the 17th, 18th and 19th centuries. We consider a curve y equals f of x, drawn here for x between a and b, where a is less than b. We find the area, denoted by capital A, between the curve and the x-axis over this interval by forming approximations and then taking some kind of limit. The method proceeds in 4 steps. In the first step, we break the interval up into smaller pieces called subintervals. by choosing numbers, say t1, t2 up to tn-1, in between a and b, where n is some positive integer, which you can think of as being large, and it's convenient to call a t0 and b tn. We call the sequence of numbers a partition of the interval from a to b. In the second step, we use the partition to form rectangles that reach up to the curve, and then put all of the areas together with the aim of approximating the area under the curve. In this drawing, the rectangles all sit beneath the curve, but in fact one has complete freedom to create rectangles that use any points at all within the subintervals. If we focus on the ith subinterval for a typical I between 1 and n, we can choose any xi between ti-1 and ti, move up to the curve, and form a rectangle of height f of xi, which has an area that we can calculate easily. Its width we call delta xi, which is just the difference ti minus ti-1. And the area becomes the height f of xi multiplied by this width delta xi. The third step is to add up all of these areas. Our area, capital A, under the curve will be approximately the area of the first rectangle when I equals 1, that is f of x1 times delta x1, plus the area of the second rectangle when I equals 2, that is f of x2 times delta x2, all the way up to the area of the last rectangle when I equals n, that is f of xn times delta xn. This huge sum can be written concisely using sigma notation, where the Greek letter capital sigma, S for sum, is an abbreviation for adding up all of these areas, with typical expression f of xi times delta xi as I ranges from 1 up to n. This expression, which will have many terms if n is large, is called a Riemann sum. Now we can stop at this step if we wish to get a very good approximation to the area A if we've chosen n large enough, and we'll come back in a moment to illustrate this with an example. But there's an important fourth step, which is to see what happens to the Riemann sum in the limit as n gets arbitrarily large. If all of the conditions are right, such as the curve being continuous, and we've followed the previous steps carefully, then the approximation to the area A turns into equality. We reach the actual area A by taking the limit of the Riemann sums. We have a special notation for this using a stylized S called an integral symbol, with a few features I'll mention in a moment. The overall expression is called a definite integral. There's also something called an indefinite integral, which we'll come to in a later video. Notice how the differential dx appears, replacing the delta xi. F of x replaces f of xi. The jagged sigma symbol is replaced by the nice smooth integral symbol, and we have Leibniz to thank for that, and the limit notation has disappeared. The I, ranging from 1 to n, is replaced with a and b, the endpoints of our interval, with a as a subscript and b as a superscript. To aid your intuition, it can be helpful to think of the expression f of x times dx as the area of an infinitely thin rectangle of width dx and height f of x. Here's the curve again with x ranging between a and b. You can imagine forming this infinitely thin rectangle from x up to the curve almost like a single line segment, with height f of x and width the infinitesimal differential dx. So that when we form the definite integral, it's as though we're taking a continuous sum of all these infinitesimal areas f of x times dx as x ranges from a to b. That's certainly how Leibniz thought of it. The Riemann sum is a discrete quantity involving finitely many terms, representing an approximation, which you can think of when we take the limit as becoming a continuous process that finds the actual exact area under the curve, the definite integral, also called the Riemann integral. It's a very important theorem, proved carefully in the 19th century, that if y equals f of x is a continuous function for x between a and b, then the limit of the Riemann sums exists as n goes to infinity, provided the width of the subintervals in the partition of the interval, denoted by delta xi for each I, tends towards 0. To guarantee existence of this limit, we have to make sure the partition gets finer and finer so that the width of the rectangles goes towards 0 as n gets arbitrarily large. This result is very subtle and difficult to prove. The value of the limit is independent of the choices you make in the first step when forming the partition of the interval, and you don't even need the widths of the subintervals to be the same size. And also in the second step, when you have complete freedom to choose your xi from anywhere within the ith subinterval. There are doubly, infinitely many different choices as you perform these steps, and incredibly they all produce the same limit as n gets arbitrarily large. Here are the main features of the definite integral. We have the differential dx at the right, the terminals a and b reminding you of the endpoints of the interval, and the rule for the function f of x sandwiched in the middle referred to as the integrand. Let's use a Riemann sum to estimate the area under the curve representing the unit circle as x ranges from 0 to 1. The equation of the circle is x squared plus y squared equals 1. So rearranging this, y is the positive square root of 1 minus x squared. The area is the definite integral using root 1 minus x squared as the integrand and 0 and 1 as the terminals. But this represents the area of 1/4 of the unit circle, which you can see is just pi on 4. So in fact, we're going to use the Riemann sums to approximate pi on 4. In this illustration, we'll use 10 subintervals, all of width 0.1. We're going to produce two approximations using rectangles that sit beneath the curve to get a lower bound for the true area, and rectangles that sit above the curve to get an upper bound. We first create what is called a lower sum by moving up to the curve, making sure all the rectangles sit beneath the curve. And then take their areas, coloured green, which we add up to form what we call capital L for lower sum. Each of the rectangles has a common width of 0.1 units, which comes out as a common factor, and the heights of the y values, the square root of 1 minus x squared, for the discrete inputs x equal to 0.1, 0.2, 0.3, all the way up to 1. You can check that this evaluates to approximately 0.72613, and this becomes our lower estimate for the area pi on 4. We can repeat this process, but now forming what we call an upper sum by moving up to the curve and using rectangles that sit above the curve, and obtain their areas by topping up the green areas already in the diagram with these extra blue areas. We can then add up all the areas to get what we call U for upper sum, noting that again the interval widths are all 0.1 coming out as a common factor. And now the heights of the rectangles are the y values as x goes from 0, 0.1, 0.2 all the way up to 0.9, which you can evaluate to get approximately 0.82613. If you're astute, you'll notice from the diagram that in this case the upper sum is just the lower sum shifted to the right 0.1 units, plus the area of the very first rectangle, which is 0.1. Then we can get U by adding 0.1 to L. In any case, we have a lower bound L and an upper bound U for the area of 1/4 of this circle. The true area is somewhere in between, so we take their average, which turns out to be about 0.776. You can compare this with the true value of pi on 4 and see that they almost agree to 2 decimal places, and our approximation is an underestimate. This is to be expected as the curve is concave down, and taking averages in this way corresponds to approximating the curve using trapezoids, as explained in an earlier video, and trapezoids sit just slightly below the curve when it's concave down. If we used more subdivisions of the interval, then we'd expect to get even more accurate estimates of pi on 4. We have some further technical definitions involving definite integrals. The preceding discussion assumed throughout that we were finding areas over an interval AB where A is less than B. What if the terminals A and B are the same? It's as though we're integrating over a degenerate, infinitely thin interval with zero area, so it makes sense to define the definite integral from A to be 0. There's also a rule that says that we can swap the positions of the terminals. But then we have to multiply the definite integral by -1. This makes perfectly good sense. Consider again the interval from a to b, where a, as usual, is less than b. If we decide to change direction, like putting a car into reverse, and move instead from b backwards towards a, then we'd be reversing the direction that we're travelling along that same interval, which has the effect of creating negative bases and hence negative areas of rectangles. If you look carefully inside the expression for the Riemann sum, the term delta xi, the difference in the x values, will become negative instead of positive as you move from right to left instead of from left to right. And the signed area of the rectangle inside the sum gets multiplied by the negative base delta xi. Now, in all of the diagrams we've used so far, the curve y equals f of x has been sitting above the x-axis, so all the y values used to build the rectangles in the Riemann sum have been positive. If the curve goes below the x-axis, then the y values become negative. Used as heights of rectangles in the Riemann sum formula, they will contribute a negative sign to the areas. Thus, areas under curves, as we go from a to b, where a is less than b, are negative. For example, consider the curve y equals cos x for x moving from 0 to pi. For x from 0 to pi on 2, the curve is above the x-axis and the area is positive, coloured green. But for x from pi on 2 to pi, the curve is below the x-axis and the area is negative, coloured pink. By symmetry, the magnitudes of the areas, ignoring the signs, are the same, so the indefinite integral from 0 all the way to pi must evaluate to 0, as the positive and negative areas exactly cancel out. We can actually split the integral into two pieces. The integral from 0 to pi on 2, giving the green area, plus the integral from pi on 2 to pi, adding on the pink area, giving a combined total of 0. This is an example of the general fact that definite integrals may be broken up into pieces. If we want to integrate over a long interval, say from a to c, with b somewhere in the middle, we can split the definite integral into two pieces, the integral from a to b and then from b to c, and combine them by addition. This makes good sense, as we're creating one larger area by adding together the smaller areas in succession. There are other important properties. The definite integral is additive, describing another way of splitting an integral into pieces, which means the integral of a sum is the sum of the integrals. This means that you can split the integrand up into pieces, integrate them separately, and then combine the answers using addition. As usual, constants come out the front. Both of these properties follow from corresponding properties about limits of sums and limits of constant multiples, and the fact that definite integrals are themselves limits of Riemann sums. Let's apply these principles to an example. Recall from last time that the area under the parabola y equals x squared as x goes from 0 to 1 is 1/3, which says that the definite integral evaluates to exactly 1/3. Even easier is the area under the constant function y equals 1 as x goes from 0 to 1, which of course is 1 square unit, which gives us another definite integral. So we have these two definite integrals and can use them to find the integral of, say, 12x squared minus 5 over the same interval. First, split the integrand into two pieces, which we integrate separately, then bring constants out the front, and evaluate using the known values above. The answer turns out to be -1. By following these rules, we can predict that the net signed area turns out to be negative. And you can see the effect by drawing the portion of the parabola for this interval. It doesn't matter that my scales are different for the x and y axes. Notice that the pink area under the x-axis does indeed appear to exceed the green area above the x-axis in magnitude. In today's video, we discussed in detail the method of Riemann sums, which uses rectangles to approximate areas under curves. There are 4 steps. One first partitions the interval, forming n subintervals. Then one builds rectangles that reach up to the curve. Then one adds together the areas to form the Riemann sum. And finally, one takes the limits of these expressions as n gets arbitrarily large. It's a major theorem that if everything is well behaved and lengths of subintervals tend to 0, then the limit exists. This limit of the Riemann sums is called the definite integral, also called the Riemann integral, and represents the exact area under the curve. We express this symbolically using an integral sign, which is like a stylized S for sum. Important features of this notation include the integrand, which is the value of the function, multiplied by the differential, and the use of terminals, which are just the endpoints of the interval over which we're working. We use the Riemann sum to approximate the area under 1/4 of the unit circle by taking the average of lower and upper bounds. We also mentioned important properties of the definite integral, that areas are multiplied by -1 if one swaps the terminals, that areas beneath the x-axis have a negative sign, that we can split an integral into pieces by integrating along subintervals and joining the areas together using addition, that we can split the integrand into pieces, again under addition, and finally that we can bring constants out the front. Please read the notes, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. In today's video, we introduce and apply the fundamental theorem of calculus, which provides an elegant formula that uses antiderivatives to find exact values for definite integrals, that is, areas under curves. We discuss common antiderivatives and how they are represented using indefinite integrals, which use the same symbolism as definite integrals, except that terminals are missing. The definite integral is a number representing the area under a curve over some given interval. It's represented symbolically by putting together an integration symbol, an integrand f of x representing the rule of the function, a differential dx telling us what input variable is being used throughout, and terminals a and b that are endpoints of the interval. In principle, we can find the value of the definite integral by taking a certain limit of an expression known as a Riemann sum, discussed and illustrated last time. This looks like a very involved and complicated way to find areas under curves. Under certain circumstances, it seems that a miracle occurs and all of this complexity can be avoided. The fundamental theorem of calculus states that the definite integral can be evaluated as the difference of two expressions, capital F of b minus capital F of a, where capital F of x is any antiderivative of little f of x. The terminology needs explaining, which we do in a moment. This theorem holds whenever the function little f, whose rule appears in the integrand of the integral, is continuous over the interval from a to b. That is, you can imagine drawing the curve without lifting your pen off the paper. Before illustrating applications of this theorem, we need first to spend time clarifying and exploring carefully the notion of antiderivative. To say capital F of x is an antiderivative of little f of x means that the derivative with respect to x is little f of x. In previous videos, you're used to taking the derivative in all sorts of settings, but here little f of x is not being differentiated. Instead, it appears as a derivative itself. To say it's a derivative of capital F of x is entirely equivalent to saying that capital F of x is an antiderivative of little f of x. These two statements convey the same information. There is a subtlety, however. Notice how little f of x is the derivative, whilst capital F of x is an antiderivative. It turns out that antiderivatives are not unique. In fact, all antiderivatives of f of x differ by addition of a constant. I'll explain why later in the video. You'll see constants appearing a lot in integration formulae, represented typically by a capital C called a constant of integration, but more about that later. The whole point of the fundamental theorem is to find areas under curves as simply as possible, and the technique relies on finding antiderivatives of functions. If we're able to do this, then we get exact answers, no need for approximations. There's a twist to all of this. The process of differentiation is relatively straightforward once you've learnt the basic rules, like the chain, product and quotient rules, which turn differentiation essentially into a mechanical procedure. Going the other way, however, forming antiderivatives is far from mechanical and requires great skill and ingenuity. Let's start to build a table with some common useful functions, their derivatives and antiderivatives. For example, here are some simple decreasing powers of x. You're familiar with their derivatives. The derivative of x is 1, so that x becomes an antiderivative of 1. Antiderivatives can differ by a constant, so let's add capital C to cover all possibilities. This is the C mentioned before, the constant of integration. The derivative of x squared is 2x, so the derivative of half of x squared will be just x, so that x squared on 2 becomes an antiderivative of x. Again, we add a constant c to cover all possible antiderivatives. The derivative of x cubed is 3x squared, so the derivative of 1/3 of x cubed becomes an antiderivative of x squared, and we add c. These are special cases of the pattern. In general, the derivative of x to the n is n x to the n minus 1, and an antiderivative of x to the n is the result of adding 1 to the exponent, which becomes n plus 1, and placing n plus 1 in the denominator. And don't forget to add c. Now there's an important exception. We can only divide by n plus 1 if it's non-zero, so we have to stipulate that n is not equal to minus 1. Let's focus then on some negative powers of x, including the problematic case 1 on x equal to x to the minus 1. Again, derivatives are straightforward. And the antiderivatives of x to the minus 2 and x to the minus 3 are taken care of by the pattern we observed earlier for antidifferentiating x to the n. What about an antiderivative of x to the minus 1? It's a non-trivial fact that the derivative of ln of x is 1 over x, so ln of x is an antiderivative. And as usual, we add c. But we're not yet out of the woods. This only makes sense if x is positive. You can't take the log of a negative number. Yet of course x to the minus 1 makes sense for negative numbers. There's a device for covering the negative case which I'll mention later. Let's consider the two circular functions. The derivatives you know, but be careful to include the minus sign when differentiating cos x. Since the derivative of sin x is cos x, then sin x is an antiderivative of cos x, and don't forget the plus c. Now the derivative of cos x is minus sin x, so to get an antiderivative of sin x, we have to get rid of the minus sign, which we do by adding a minus sign to cos x. And sounding like a broken record, don't forget the plus c. Let's also add rows for the natural exponential and logarithm functions, whose derivatives we know well. Antidifferentiating e to the x is immediate. Now for a really tough one. An antiderivative of ln of x is x ln of x minus x. You'd have to be very clever to guess that. There is a systematic way to find this antiderivative using a technique called integration by parts, which you'll learn about if you take courses in calculus that follow on from this course. But it's very easy to check that it actually works. If you differentiate the expression, splitting it up and using the product rule on the first piece, you will see in a few steps that the answer really does simplify to ln of x, confirming that we really have found an antiderivative. We'll spend time discussing antiderivatives, but we haven't used the fundamental theorem yet to find any areas under curves. The theorem tells us that the area is capital F of b minus capital F of a. Because this expression is so useful, it gets its own square bracket notation. Write f of x between the brackets with a as a subscript and b as a superscript as an abbreviation for f of b minus f of a. When people see this, they just often say, evaluate capital F between a and b, which means, technically speaking, to form f of b minus f of a. The theorem now has this compact form, and we say, the area under the curve little f of x for x between a and b is capital F of x evaluated between a and b, where capital F of x is any antiderivative of little f of x. Let's try it out on an example. Let's find the area under the parabola y equals x squared for x between 0 and 1. We already know the answer is 1/3 from an earlier video, so this is a good test case for this new method. The area is an antiderivative of x squared evaluated between 0 and 1. But we know an antiderivative, namely x cubed on 3. So we just evaluate this by subbing in 1 for x and 0 for x and taking the difference, which quickly becomes 1/3, as expected. Notice how effortless this becomes. No complicated telescoping sums, Gauss trick, or any of the other paraphernalia we used in an earlier video. Let's look at another example from an earlier video and evaluate it by direct methods. The area under the curve y equals 12x squared minus 5, again for x between 0 and 1. The area is just an antiderivative of 12x squared minus 5 evaluated at 0 and 1. How do we know to put 4x cubed minus 5x inside the square brackets? Just as we can differentiate piece by piece and bring constants out the front, we can perform similar manipulations to find antiderivatives. We discussed before that an antiderivative of x squared is x cubed on 3, so an antiderivative of 12x squared should be 12 times this, which is 4x cubed. An antiderivative of 1 is x, so an antiderivative of minus 5 should be minus 5 times x. Adding these two antiderivatives together gives 4x cubed minus 5x. And then subbing in 1 for x and 0 for x, and taking the difference, the answer quickly simplifies to negative 1, which happily coincides with the answer we found in an earlier video. Let's find the area under the branch of the hyperbola y equals 1 on x in the first quadrant for x between 1 and 2. The area is given by this definite integral. It's a common and harmless abuse of notation to put the integrand and the differential together as a single fraction, making everything more compact. By the fundamental theorem, all we have to do is evaluate some antiderivative of 1 on x between 1 and 2. But ln of x is an antiderivative, so evaluating between 1 and 2 gives log of 2 minus log of 1, which becomes just log of 2. Hence the area we're looking for is the natural logarithm of 2. Notice that there's nothing special about 2 in this calculation. We can replace 2 by any positive real number k, and the area turns out to be ln of k. This diagram implicitly assumes k is bigger than 1. Suppose instead that k is less than 1. The definite integral is still ln of k, as before, but now integrating from 1 to k, in fact moves from right to left instead of left to right, so that the green area drawn here, calculated in the backward direction, becomes negative. This matches nicely the fact that ln of k is negative. If we really want to regard the green area as positive, we have to integrate forwards from k to 1, and we can swap terminals by multiplying by minus 1 to get negative ln of k, which is indeed positive, and all is well. Let's find the area under the sine curve between pi on 2 and pi. An antiderivative is negative cos x, and evaluating it between pi on 2 and pi quickly produces the answer 1. Amazing! Who would have expected the area to be such a nice number? If we integrate from pi on 2 all the way to 2 pi, then the curve slips below the x-axis, and you expect by the symmetry to add 2 lots of the green area, which is coloured pink in the diagram, but counted negatively, so the total answer should be negative 1. Let's check. We evaluate the same antiderivative, but now between pi on 2 and 2 pi, and quickly see that the answer simplifies to negative 1, as expected. Here's the fundamental theorem again. We have a natural notation to describe the antiderivative. We write capital F of x using the same expression as the definite integral, but without the terminals. This is called an indefinite integral. The indefinite integral describes an antiderivative of the integrand little f of x, so is a function of x. By contrast, the definite integral is an area under the curve, so is a real number. We mentioned earlier the fact that antiderivatives of f of x differ by a constant. This assumes all functions are continuous on a particular interval of interest. I'll briefly explain the reason. Suppose that capital F of x and capital G of x are both antiderivatives of little f of x, so that their derivatives are both equal to f of x. We want to show that their rules are the same, but differ by a constant. The trick is to differentiate the difference capital F of x minus capital G of x, which is the difference of the derivatives, which is f of x minus f of x, which is 0. If the derivative is 0, then the tangent lines to the curve with rule capital F of x minus capital G of x must be horizontal everywhere on the interval, which means the curve must be itself just a horizontal line, so f of x minus g of x equals some constant c, so that f of x equals g of x plus c. Indeed, we've shown the two antiderivatives differ by a constant. This explains the origin of the constant of integration c that you will see all of the time in so-called integration formula, which are just equations linking functions to their antiderivatives and use the indefinite integral notation. For example, this one just says that the general antiderivative of x is x squared on 2 plus c. This one says that the general antiderivative of x squared is x cubed on 3 plus c. These are special cases of the formula that says the general antiderivative of x to the n is x to the n plus 1 over n plus 1 plus c, provided n does not equal minus 1. It's common to use the same capital C for the constant of integration. The exceptional case to integrate x to the minus 1, also written as the integral of dx on x, is ln of x plus c, provided x is greater than 0. You'll also see the same thing with magnitude signs, which is a clever device for covering the case also when x is negative. Why this works is explained carefully in the notes. We also have the integral of e to the x is e to the x plus c, and two integration formulae for the circular functions. Since the derivative of tan x is sec squared x, we get that the integral of sec squared x is tan x plus c. There are many more formulae which you'll see if you open the covers of almost any calculus textbook. There are also some general principles for manipulating indefinite integrals which are made explicit in the accompanying notes. In today's video, we introduced and applied the fundamental theorem of calculus, which provides a simple and elegant formula using antiderivatives to find exact values for definite integrals. We found antiderivatives for a number of common functions and then used some of them to try out this new method to calculate areas under a variety of curves. We also expressed antiderivatives using indefinite integrals, which use the same symbolism as definite integrals except that terminals are missing, and then listed a number of common integration formulae. These all employ a constant of integration, typically denoted by adding capital C, which arises because of the fact that all antiderivatives of a given function differ by a constant. Please read the notes, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. In the previous video, we introduced and applied the fundamental theorem of calculus, which provides an elegant formula under certain conditions for finding exact values for definite integrals, that is, areas under curves. In today's video, we explained the connection between areas and derivatives, which is the main idea that leads to a proof of this remarkable theorem. We also apply the main idea to use the derivative to relate areas of circles to perimeters and volumes of spheres to surface areas. Recall that the definite integral is the area under the curve y equals f of x as x goes from a, the left-hand endpoint of the interval, to b, the right-hand endpoint. Assuming the curve is continuous, then the area is described succinctly by the fundamental theorem of calculus as capital F of b minus capital F of a, where capital F of x is any antiderivative of little f of x, by which we mean that its derivative is little f of x. The main purpose of today's video is to explain why this works. Before starting, it should be remarked that this is one of the most important theorems in mathematics. Though the ancient Greeks employed thought experiments with approximations and limits, the basic ingredients of calculus, it took a couple of thousand years before mathematicians were able to recognize and articulate the main ideas that lead to the statement and proof of the theorem. So you shouldn't expect the ideas to be straightforward. We have to be radical in our thinking, flexible and prepared to experiment and abruptly change our point of view. The first step is to change the name of the input variable that is used to form the curve with respect to which we're taking the area. Let's use t instead of x because we want to reserve x for something else in a moment. Wherever we see an x, we replace it with a t. So the horizontal axis is labelled by t, the curve is a function of t, and the integrand and differential use t. We're still finding the same area under the same curve, just using a different name for the input variable. What's so radical about that? We do something completely unexpected. We still allow x to move from A to B, but now use x instead of b as the right-hand endpoint of an interval, with respect to which we take areas under the curve. We create what we call an area function, capital A of x, using the same curve, but now representing the area under the curve from A up to x, wherever x happens to be in the interval. The value of A of x clearly is able to vary as x varies. Being an area under the curve, the value A of x is still represented by a definite integral, but now x appears as the upper terminal, instead of having a role in the specification of the integrand and differential. On the face of it, this looks like a ridiculous and unnecessary complication, as we're only interested in the area under the curve from A to B. But you've already seen many examples in early videos when we've made things more complicated in order to get past a barrier or obstruction, to solve a problem or make things simpler later. The phenomenon you're about to witness is one of the most spectacular examples of problem solving in the history of mathematics. Calculus is a study of how things change, and especially about instantaneous rates of change. Let's think about the way the area function changes. First of all, make note of what happens at the two extremes when x equals a and x equals b, the endpoints of the interval. When x equals little a, both terminals in the definite integral are the same, and remember this gives an area of 0. In the diagram below, when x equals a, the green area vanishes. However, if x equals b, then a of b becomes our original definite integral, and the green area under the curve goes all the way from a to b. What about the instantaneous rate of change of the area function? This is the derivative, defined as the limit, as h goes to 0, of a of x plus h minus a of x over h. We relate the ingredients of this limit to the diagram representing the area function. We assume throughout the following discussion that h is small and positive, and that the curve y equals f of t is increasing, as in this diagram. These assumptions greatly simplify the argument, but nevertheless suffice to illustrate all of the important key ideas. Because h is positive, x plus h is slightly to the right of x. We move up to the curve and note f of x and f of x plus h on the y-axis. There's a small piece of the curve over the interval from x to x plus h, which we enclose with lower and upper rectangles. The height of the lower rectangle is f of x, and the height of the upper rectangle is f of x plus h. The width of both rectangles is h. We colour in the area of the lower rectangle blue, and the area under the curve between the lower and upper rectangles beige. The value of a of x plus h is the area all the way from a to x plus h, whilst the value of a of x is the area from a to x, so that when you take a of x away from a of x plus h, you just get the area under the curve between x and x plus h, which is just the blue area plus the beige area. We colour in pink the area in the upper rectangle that's not under the curve. So if we add this to the blue and beige areas, then we get an upper bound for a of x plus h minus a of x. On the other hand, if we only consider the blue area, then we also get a lower bound. But the blue area is just the area of the lower rectangle, which is h times f of x. And the blue, beige and pink areas combine to give the area of the upper rectangle, which is h times f of x plus h. So we get this nice cascade of inequalities, with a of x plus h minus a of x sandwiched in the middle. Let's divide through by the positive number h, retaining the same inequalities throughout, so that the h's cancel on the left and right, and we conclude that f of x is less than or equal to a of x plus h minus a of x over h, which is less than or equal to f of x plus h. So let's see what happens as h goes to 0. F of x just stays the same, and f of x plus h becomes f of x, because we're assuming throughout that the function f is continuous. The expression in the middle goes to the derivative a dashed of x. But this must become f of x by the squeeze law, since both the expressions on the left and right have f of x as the same limit. There's nowhere else to move but for all three limits to coincide with f of x. Reflect on what we've just done. We defined an area function by allowing the upper terminal of the definite integral, which we now call x, to vary from a to b, and discover that its derivative is simply the value of f at x. How remarkable! We've learned so many rules for manipulating derivatives, and we're used to analysing and creating complicated functions, and the area function looks like it probably is some very weird and exotic function. But when we differentiate it with respect to x, we just reproduce the value of f at x. This beautiful, simple and elegant relationship between areas and curves evaded detection for thousands of years. What's this got to do with the fundamental theorem of calculus? Well, it tells us that the area function is an antiderivative of the function that gives rise to the original curve. The fundamental theorem gives us a formula in terms of capital F of x, which is an antiderivative of little f of x. But remember, antiderivatives of a given function differ by a constant, so capital F of x must equal a of x plus c for some constant c. To find c, we can sub in x equals a, so f of a becomes capital A of little a plus c, which is the definite integral with a as both upper and lower terminals, plus c, which is 0 plus c, which of course is just c. So the constant is f of a. So f of x becomes a of x plus f of a. In particular, f of b becomes a of b plus f of a. And rearranging gives a of b equal to f of b minus f of a. But a of b is the original area under the curve over the entire interval from a to b, which shows that our original definite integral is indeed given by the formula provided by the fundamental theorem of calculus. Finally completing the proof. Now, there were certain simplifications in the way we set up this proof and the accompanying diagrams, so it's really only a sketch, but all of the main ideas behind the fundamental theorem have been captured by what we've done. In today's video, we introduce and illustrate an important and useful method for anti-differentiation, known as integration by substitution. This method is closely related to the chain rule, one of the differentiation rules that we discussed in the previous module. This method provides us with a tool for reducing complexity of a given integral by making an intelligent or judicious choice of substitution of variables, followed by algebraic manipulation of the integrand and differential. The word integration has several meanings, usually clear from context. It may refer to the process of finding an indefinite integral, which is an antiderivative of the integrand, producing a function. It can also refer to the process of finding a definite integral, which is the area under a given curve over a given interval, producing a real number. The expression integration by substitution typically refers to a rule or method for antidifferentiation, closely related to the chain rule for differentiation. As you'll see, it makes free rein of differentials and takes full advantage of the utility of Leibniz notation. There's also a version of this method involving definite integrals, and special care needs to be taken with keeping track of the correct terminals. Before formalising the method, let's look at the following example and follow our instincts for manipulating expressions, in particular those involving differentials. Our aim is to antidifferentiate 4x times x squared plus 1. A direct method is to expand the integrand and then antidifferentiate each piece, noting that 4x cubed is the derivative of x to the fourth and 4x is the derivative of 2x squared, and putting the pieces together with a constant of integration. A second method is indirect and avoids the initial expansion. The complicated part of the integrand appears to be x squared plus 1, so let's see what happens if we put u equal to this. The derivative of u with respect to x is 2x, and we get the equation of differentials du equals 2x dx. The aim is to express everything, if possible, in terms of u, in order to simplify the integral. So we move a factor of 2x in the integrand to sit next to the differential dx. And notice that the expression becomes the integral of 2u du, replacing x squared plus 1 by u, and 2x dx by du. The problem simplifies to anti-differentiating 2u with respect to u, which is just u squared plus a constant, say c dash, to make a comparison in a moment with an earlier solution that used plain c. Expressing everything in terms of x gives a final solution x squared plus 1 all squared plus c dash. So let's compare our two solutions. On the face of it, they appear to be different. In fact, the differences in the way things are expressed create an illusion. If we expand out the second solution, we reproduce the first solution by gathering together the constants and putting c equal to 1 plus c dash. When one anti-differentiates using different pathways, it's quite common to end up with expressions that look superficially different, but which in fact represent the same function if you carefully examine the constants that appear. Let's look at an example involving the circular functions. As you know, an antiderivative of cos x is sin x. What about an antiderivative of cos 2x? We can guess that it should look something like sin 2x. If we differentiate sin 2x with respect to x using the chain rule and a substitution of u equals 2x, we quickly get 2 cos 2x, which is 2 times more than the integrand cos 2x above, so we compensate by dividing sin 2x by 2, yielding finally the antiderivative sin 2x over 2 plus c. This is called the guess and check method, which usually works well when you have to handle constant multiples of variables. For a more thorough systematic approach, we make a substitution up front by putting u equal to 2x, so that du dx equals 2, so that du equals 2 dx, which we can rearrange as dx equals a half du. The aim is to convert everything involving x to something simpler involving u, so cos 2x becomes cos u, and we can replace dx by a half du. We can bring the constant a half out the front of a simpler integral involving u, so that we get half of sin u plus a constant we can call c dash, which becomes sin 2x on 2 plus c, where c is a half c dash, giving the same answer that we obtained using the guess and check method. With practice, you usually skip the 2 steps involving the constant c dash, which I included just so you can see exactly how it all fits together. Let's develop a general framework for examples like these, called a substitution rule for integration. Recall the chain rule for differentiation, which says dy dx equals dy du times du dx, where we think of the differentials to u cancelling in the numerator and denominator as though these expressions were ordinary fractions. Suppose that y happens to be an antiderivative with respect to a variable u of some function with rule f of u, that is, dy du equals f of u, which can be expressed as an indefinite integral. The integral of f of u with respect to u is y plus c for some constant c, since the general antiderivative is formed by adding constants to any particular antiderivative. Now we can get the variable x into the game by using the chain rule, so that dy dx equals dy du times du dx, which equals f of u times du dx, which tells us that y is also an antiderivative of the expression f of u du dx, whatever it might be, but with respect to the variable x. And this can be expressed also as an indefinite integral, namely the integral of f of u du dx, all bracketed together as the integrand with respect to x, which becomes again y plus c. And there's no harm in using the same general c as before. So y plus c appears in 2 places, linking the 2 indefinite integrals together. Thus we get equality of these 2 integrals, known as the integration by substitution formula. Brackets are usually deleted, which makes the formula very easy to remember because you can think of the differentials as cancelling, treating the derivative as an ordinary fraction, just as we do in remembering the chain rule. The formula can also be written using function notation for the derivative. If u equals g of x, the rule for some function g with input x, then we can rewrite the formula using g dashed of x for du dx and f of g of x for f of u. though you often see the expressions written down in the opposite order, the reason being that one tries, if possible, to recognise some complicated integral as the left-hand side, which dissolves by the formula into the much simpler right-hand side. There's also a version using definite integrals, where we add terminals, say a and b for the variable x on the left-hand side, and g of a and g of b for the corresponding variable u on the right-hand side. The use of the terminals is quite delicate and takes some care, and one needs to accurately match the terminals to the variable that appears in the differential used to form the definite integral. It's common to make errors in manipulating terminals, or to overlook the need to change them as one switches between variables. Consider the following example, which is to find the area under the curve y equals cos pi x on 2 for x going from -1 to 1. We'll approach the solution in two different ways. In the first solution, we start off by working with an indefinite integral and only later introduce the terminals. We remove the terminals and try to find the integral of cos pi x on 2 with respect to x. In fact, we quickly get 2 on pi times sine of pi x on 2 plus c, using a guess and check method by an appropriate adjustment of the constant out the front. The derivative of sine pi x on 2 one can quickly see is pi on 2 times cos pi x on 2. So the adjustment required to get the antiderivative above is to multiply by 2 over pi. Because the antiderivative is a function of x, we just put the terminals back in to get the original definite integral and evaluate it in the usual way using the fundamental theorem of calculus. We substitute 1 for x, minus 1 for x, and take the difference. And see that it quickly evaluates to 4 over pi. Alternatively, we can solve this using definite integrals all the way through. We use the substitution u for pi x on 2, so that du dx is pi on 2, and u is pi on 2 times dx, which we can rearrange to get dx equal to 2 on pi times du. We'll express everything in terms of u, including the terminals. So x equals 1, the original upper terminal, converts to u equal to pi on 2, and x equal to minus 1, the original lower terminal, converts to u equal to negative pi on 2. We now rewrite the original definite integral by replacing pi x on 2 in the integrand by u, the differential dx by 2 on pi times du, the upper terminal by pi on 2, and the lower terminal by negative pi on 2. The constant 2 on pi can come out the front, and then we evaluate in the usual way by the fundamental theorem of calculus, using sin u as an antiderivative of cos u with respect to u, and replacing u by pi on 2, u by negative pi on 2, and taking the difference, which quickly simplifies to 4 on pi, agreeing with the answer we found by the first solution. Using either method, we find the green shaded area under the curve turns out to be 4 on pi. The remaining examples in this video increase substantially in terms of difficulty, and you should pause the video a lot to check the details and your understanding. You may benefit greatly also from consulting the notes that accompany this video, and make sure that you feel really comfortable with the easier substitution examples. What we illustrate next is a tricky antidifferentiation using a mixture of the circular functions in the integrand. It's not obvious at all what substitution to make that could possibly simplify the calculation. With experience, you realise that of the two powers that appear, the even power cos squared x turns out to be the most problematic. You'll see in a moment that the odd power sine cubed x can be used to our advantage. So we try making a substitution of u equals cos x. So du dx equals minus sine x, and du equals minus sine x dx. We now rewrite the integrand to try to exploit this formula for the differential du. We peel off a copy of sine x from the sine cubed x, leaving a factor of sine squared x. which fortuitously can be rewritten as 1 minus cos squared x, exploiting the circular identity. And then we rearrange the integrand to get minus sine x next to the differential dx, and balance everything up with an extra minus sign out the front. Now comes the magical effect of the substitution. We replace cos x, wherever it appears in the integrand, by u, and minus sine x dx gets replaced by du. Our original integral is thus transformed into minus the integral of 1 minus u squared times u squared du. We can expand the integrand, bring the minus sign back inside to get a simple polynomial in u, which is then straightforward to anti-differentiate, piece by piece. And it remains finally to express everything in terms of x, and the original problem is solved. The next example is a difficult integration of a rational function where the integrand is a fraction with a linear polynomial in the numerator and a quadratic in the denominator. Denominators usually create problems, so let's try to rewrite the quadratic in a simpler form. By the trick of completing the square, we can rewrite it as x plus 1 squared plus 1. It will simplify considerably if we make a substitution of u equal to x plus 1, so that du dx equals 1 and du equals dx. The numerator can also be expressed in terms of u by a trick of adding and subtracting 1 to x inside brackets, and rearranging the expression to get 4u plus 3. We're working steadily towards expressing everything in terms of u. The integrand becomes 4u plus 3 divided by u squared plus 1, and the differential dx is simply replaced by du. This is substantial progress, and we can simplify things further by splitting up the integrand in two pieces and integrating them separately. The first piece we'll come back to in a moment, but the second piece, with the constant 3 out the front of the integral of du over u squared plus 1, becomes 3 times inverse tan of u plus c. The reason from an earlier video is that the derivative of inverse tan of x becomes the rule 1 over x squared plus 1, describing the curve known as the Witch of Maria Agnesi, expressed as an indefinite integral involving x, which we're applying here with u instead of x. Notice also that the constant of integration is multiplied by 3, which becomes another constant, which we can just rename as c again. We can go a step further and rewrite inverse tan of u as inverse tan of x plus 1. We still have to figure out the first piece. Again, the denominator is the problem, so make a new substitution, say v equal to u squared plus 1, so dv du equals 2u, so that dv equals 2u du. To set things up, we bring the constant 2 out the front, and then replace the denominator by v, and the new numerator, including the differential, by dv. This produces the much simpler expression 2 times the integral of dv on v. But remember, the integral of dx on x is ln of x plus c when x is positive, which we can apply here, and notice that the constant of integration is multiplied by 2, which we've just renamed by c again. So we splice this into our earlier answer. There are actually 2 constants of integration, both of which we call c, which get added together to get another constant, which again we call c. This kind of abuse of notation, calling everything c all of the time, is universally used and relatively harmless, but you should be aware of what you're actually doing when you manipulate the constants. We in fact want an antiderivative in terms of the original variable x, so convert v into u squared plus 1, and the remaining u that appears into x plus 1, and we've solved the original problem. We'll finish with a very difficult problem, which is to anti-differentiate the fraction root x over 1 plus root x. There are a few different substitutions we could try, but we'll go the whole hog and put u equal to the entire denominator, which can be rewritten as 1 plus x to the half. Then du dx becomes a half x to the minus a half, which is 1 over 2 root x, so that du equals dx over 2 root x, which we can rearrange so that dx equals 2 root x du. Hence, the original integral can be transformed by replacing 1 plus root x by u and dx by 2 root x du. and then bring the constant 2 out the front, and simplifying the numerator to x, which then becomes u minus 1 squared. We can now expand the numerator and split the integrand into pieces. An antiderivative of u minus 2 is just u squared on 2 minus 2u, and an antiderivative of 1 on u is log of the magnitude of u. We've amalgamated all the constants of integration at the right, which I've called c dash, not c, for a reason which will become apparent in a moment. Then we carefully write everything in terms of x only. Now we could just stop here. But notice that we can expand and simplify further in a few steps to obtain x minus 2 root x plus 2 log of 1 plus root x minus 3 plus c dash. Note that 1 plus root x is positive, so we can dispense with the magnitude signs when forming the natural logarithm. The expression minus 3 plus c dash is just a constant, which we now call c, and then we end up with this elegant solution of a very difficult problem. In today's video, we introduced and illustrated the method of integration by substitution, which is closely related to the chain rule, one of the differentiation rules we learnt in the last module. This method enables one to anti-differentiate complicated functions by exploiting combinations of integrands and differentials, which simplify the integral after making appropriate substitutions and changes of variables. Some of the examples could be solved by a guess and check method. Other examples are very difficult and require considerable experience, even to choose the right substitution that's likely to lead to progress, and then require considerable perseverance and technical skill to see the calculation through to a successful conclusion. Please read the notes, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. We now discuss some properties of definite integrals when the integrand is an even or an odd function, and the interval over which we're integrating is symmetric about the origin, that is, the variable ranges between plus and minus some real number. Let's integrate the odd function sin x for x between plus and minus pi on 2. Here's the graph, and the areas under the curve have been coloured green for positive and pink for negative. Clearly the green and pink areas have the same magnitude as the regions exactly coincide under a 180-degree rotation about the origin, hence the overall area must become 0, as the positive and negative areas cancel out. We can check the answer directly using the fundamental theorem of calculus. An antiderivative is cos x, which we evaluate between plus and minus pi on 2. And see that the answer quickly becomes 0, confirming the result. Consider another odd function, say y equals x cubed, and we integrate it between plus and minus 1. Here's a sketch of the curve, and again the positive area is coloured green and the negative area pink. Again, the regions match exactly under 180-degree rotation, so the positive and negative areas cancel out, and the definite integral is 0. Again, we can check the answer using the fundamental theorem, quickly confirming that 0 is the overall area. If we integrate Newton's serpentine curve, mentioned earlier, also between plus and minus 1, then again the positive and negative areas cancel out to give 0. These examples are special cases of a general phenomenon. No matter how complicated an odd function might be, if we integrate between plus and minus a, where a is a positive number, then the positive and negative areas exactly cancel out, regardless of where they appear. Any positive area to the right cancels out with a negative area to the left, obtained by rotating the curve 180 degrees about the origin. Similarly, any negative area to the right cancels out with a positive area to the left. If the function is odd, you always get a net 0 area. What happens if we integrate an even function over a symmetric interval? Consider the even function cos x integrated between plus and minus pi on 2. In this case, the curve sits above the x-axis, so there's no possibility of cancellation. However, the area to the left of the y-axis is an exact mirror image of the area to the right, because the cosine function is even. Taking a mirror image in the y-axis doesn't change the sign of the area, so the entire area is just twice the area on the right. That is 2 times the definite integral from 0 to pi on 2. We can find this using the fundamental theorem of calculus by evaluating the antiderivative sin x between 0 and pi on 2, and we get a total area of 2. Thus the area under the curve splits exactly into 2 areas of size 1, both to the right and to the left of the y-axis. This example is a special case of a general phenomenon. To integrate an even function over the interval between plus and minus a for some real number a, we just integrate from 0 to a and double our answer. This makes perfectly good sense, as any particular region under the curve to the right of 0, whether above or below the x-axis, is matched exactly by a region obtained by reflecting in the y-axis, since the function is even, and this mirroring effect doesn't alter the sign of the area. When the integrand is odd, the area disappears, but when the integrand is even, it suffices just to integrate over the positive interval and double your answer. This fact is quite useful and often creates some economies in evaluating areas when even functions are involved. For example, let's find the area under the Witch of Maria Agnesi over the interval between plus and minus 1 over the square root of 3. Because the function is even, it's enough to integrate from 0 to 1 on root 3 and then multiply by 2. An antiderivative of 1 over x squared plus 1, you might remember, is the inverse tan function, so we evaluate this between 0 and 1 on root 3. Giving pi on 6, which when multiplied by 2 gives the total area to be pi on 3. We'll finish with a very difficult example which uses just about every trick in the book and takes advantage of the knowledge we've built up regarding odd and even functions. This is not a routine example, and it's included more for interest and for those of you that enjoy a challenge. So please don't worry if you don't follow all of the details, and pause the video if I go too fast. We want to find this definite integral. Notice that the interval is between plus and minus pi on 2, which is a clue that we should be exploiting even and odd functions. The integrand, however, is very complicated. If only the strange denominator were not there, then the integrand would become the nice even function cos x, which we looked at before and found the total area to be 2. Maybe we can exploit this if only we could handle the strange denominator. Well, if you separate out the denominator as a function in its own right, ignoring the cos x, you get y equals 1 over 1 plus e to the minus x. It's actually not all that strange. It's an example of a curve we discuss in the next video called a logistic curve. And if you apply your techniques for curve sketching, you can see it looks something like this. Where it crosses the y-axis, at y equals a half, is an inflection, and the curve is sandwiched in between 2 horizontal asymptotes. The curve looks like a stretched out S shape, almost like an integral sign falling over, an example of a sigmoid curve. And it has full 180-degree rotational symmetry about the inflection point. You can spin it around 180 degrees about the y-intercept and the curve will reproduce itself. Now, 180-degree rotational symmetry characterizes the property of being odd, provided the point of rotation is the origin. This gives us an idea. If we can shift the curve down a half of a unit, then the point of rotation, the y-intercept, becomes the origin and we'll have an odd function. This phenomenon is illustrated here just by subtracting a half from the rule for the function in the top diagram. The function in the bottom diagram is odd. You can check the algebra if you wish to confirm that you get a new rule, which is indeed odd. We don't actually need to know any details about the rule for this new function. We only need to know it's odd. Here's our original problem. And we write the integrand as cos x times 1 over 1 plus e to the minus x. And then do a trick you've seen many times before in different contexts. We subtract and add a half to the second factor in the integrand, which doesn't change the overall value. Then we separate the integral into 2 pieces. The first piece has an integrand, cos x times a complicated bit, And the second piece is integrand. It's just cos x over 2. Now, in the first piece, we have two factors. Cos x is an even function. And the second piece is just the rule for that odd function we discussed a little while ago by shifting a sigmoid curve down half a unit. Multiplying the rules for an even function by an odd function in fact gives an odd function. So the entire integrand in the first piece is odd. So the definite integral must be 0 as we're integrating between plus and minus pi on 2. Hence the first piece is 0, and in the second piece we can bring a half out the front of our familiar integral involving just cos x. So that the answer becomes a half of 2, which is 1. Thus the final answer to our original problem is the very pleasant number 1. In today's video we discussed even functions whose graphs have reflectional symmetry in the y-axis and odd functions whose graphs have 180-degree rotational symmetry about the origin. The terminology arises from functions built using even and odd powers of the input variable x and leads to surprising connections between functions and generalizations of polynomials. We saw that if one builds definite integrals over an interval that is symmetric about the origin, then the area under an odd function evaluates automatically to 0, and the area under an even function is twice the area over the positive interval. Please read the notes, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. In today's video, we discussed the logistic function used to model population dynamics, where an inhibition factor is included in the expression describing the rate of growth. The logistic model includes a ceiling on the size of the population. The resulting curve is increasing, has a sigmoid shape, and sits between two horizontal asymptotes. There's a point of inflection halfway between, about which the curve has 180-degree rotational symmetry. We begin with a simpler exponential growth model. Suppose we have a population of size x of t, which is a function of time t, and want to understand its behaviour. This model assumes that the derivative of x is some multiple k of x, where k is a positive constant. One can imagine, without any limit of resources, that the more there is of the colony, the faster it should grow, so that the growth rate should be proportional to the size of the population. This is an example of a differential equation. Note that though x appears on the right-hand side, x is being used as a dependent variable. The independent variable is t, not x, and anti-differentiating the right-hand side with respect to x will not make any progress. It needs some careful preparation to unravel this equation. We first multiply both sides by the differential to t, and dividing through by x gives dx on x equals k dt. We now apply integral symbols to both sides to get equality of antiderivatives of the respective integrands. The differential on the left-hand side involves x, whilst the differential on the right-hand side involves t. An antiderivative of 1 on x with respect to x is ln of x, and an antiderivative of a constant k with respect to t is just kt. We amalgamate constants of integration together with a single plus c on the right. We can raise Euler's number e to the power of each side. On the left we get x back again, and on the right we get e to the kt plus c, which we can expand. Thus x equals a times e to the kt for some constant a by putting a equal to e to the c. Notice that we've reproduced the familiar exponential growth function, whose graph is the exponential curve. Note that x labels the vertical axis and t the horizontal axis. Exponential growth is unlimited. The x values get arbitrarily large as t increases. Of course, this isn't a realistic model when resources are limited. We now modify the previous model to take into account constraints placed on populations by the environment and limited resources. We adjust the right-hand side of the equation dx dt equals kx by introducing a factor 1 minus x on m for some new constant, capital M. Think of m for the largest or maximal sustainable population. The factor kx remains untouched and contributes towards the growth of the population. The factor 1 minus x on m is carefully designed to model inhibition. If x is small, then this factor is close to 1, and the left-hand side is almost exactly kx, as in the original exponential model. However, if x is large, getting close to m, the factor 1 minus x on m gets close to 0, causing the overall growth rate dx dt to slow down to almost nothing. This modification is called the logistic growth model, widely used in population dynamics. We get what's called the logistic equation, whose solutions are called logistic functions. Let's now try to unravel the logistic equation. We first multiply through both sides by the differential dt. Keep the constant k on the right-hand side next to dt, but move the factors x and 1 minus x on m to the other side by division. We separate the variables by putting x's to the left and t's to the right, including their differentials. We assume implicitly throughout that the population x always lies between 0 and m. We add integral signs to both sides to create functions by anti-differentiation. On the right-hand side, a general antiderivative of the constant k with respect to t is kt plus c. The left-hand side, however, is a mystery. Here's the left-hand side again, rewritten to express the integrand as a rational function. To motivate the next step, we first play with some ordinary fractions involving numbers. For example, 1/6 is 1 divided by 2 times 3, which is a half minus a third, which we can write as 1 over 2 plus negative 1 over 3. Similarly, 1/33 equals 1 over 3 times 11. And you can check quickly this becomes 2 lots of 1/3 plus negative 7 lots of 1/11. Both 1/6 and 1/33 decompose into combinations involving the simpler fractions a half, a third and 1/11. It's like recognising that water is H2O or common salt is sodium chloride. Here's a tougher fraction. 1/99 equals 1 over 9 times 11. How can we decompose that? Let's postulate that it becomes a lots of a ninth plus b lots of 11th. We put the right-hand side together as a single fraction, where the numerator becomes 11a plus 9b. We want this to equal 1. And it helps to find multiples of 11 and 9 that differ by 1. Say 44, which is 4 times 11, and 45, which is 5 times 9. By using negative 44 and positive 45, we get a total of 1. Thus, we should take a to be negative 4 and b to be 5, and then 1/99 decomposes as minus 4 lots of a ninth plus 5 lots of 1/11. Let's try something similar with the integrand above, which is a fraction involving polynomials in x rather than just numbers. The numerator is 1. The denominator is complicated with factors x and 1 minus x on m. Let's postulate a decomposition using a lots of 1 on x and b lots of 1 over 1 minus x on m. Rewrite the right-hand side with a common denominator, obtaining a numerator that has to become 1 to agree with the numerator on the left-hand side. If we take a equals 1, then we get 1 minus x on m, and just need to choose b to make the minus x on m go away. And b equal to 1 on m does the trick. Thus the rational function decomposes as this sum, and the right-hand side can be written more simply as 1 on x plus 1 over m minus x. What we've done in an ad hoc way is a special case of the method of partial fractions, a topic you'll meet in more advanced courses in calculus. To perform this integration, it suffices to integrate 1 on x and 1 on m minus x separately and add the answers together. The population x lies between 0 and m, so that both x and m minus x are positive. An antiderivative of 1 on x is ln of x, and of 1 over m minus x is negative ln of m minus x. For the second one, you can use a guess and check method or integration by substitution. We combine the constants of integration together with a plus c dash at the right. The difference of logarithms is the logarithm of the quotient, and we rewrite the expression inside the logarithm to isolate x in preparation for the next step. Our aim, remember, is to unravel the logistic equation, and we produced this difficult integral, which we've just managed to solve. We can put everything together and amalgamate the constants on the right, using again just a single plus c. We want explicit information about x, and it's buried in the expression on the left-hand side. We first raise Euler's number e to the power of each side of the equation, so the ln is stripped away from the left-hand side, and the right-hand side becomes e to the kt plus c, which can be expanded. We reciprocate everything and rewrite the right-hand side. We add 1 to both sides, and now rewrite the right-hand side as 1 plus capital K e to the negative little kt, where capital K is the positive constant e to the negative c. We rearrange this to obtain an explicit formula for x, finally solving the logistic equation, and its solution is known as the logistic function. In writing down the logistic equation, there were two positive constants involved, little k and capital M. In developing the general solution, the logistic function, we introduced a new positive constant, capital K. This function has several important features. Firstly, the population x always lies between 0 and m, where m represents a limiting upper bound or maximum. Indeed, the limit of x of t, as t gets arbitrarily large and positive, evaluates to m, because the expression e to the negative kt, which is 1 over e to the kt, goes to 0. You can think of m as the largest sustainable population in an environment with only limited resources. On the other hand, the limit of x of t as t gets arbitrarily large and negative will be 0, because now the expression e to the negative kt will become arbitrarily large and positive, and it appears in the denominator. The variable t represents time, so the first limit represents limiting behaviour in the future. The second limit represents limiting behaviour going backwards in time to the distant past. In the original differential equation, we can rewrite the right-hand side as k on m times x times m minus x, which is a quadratic in x. Let's graph this quadratic regarding dx dt as a function of x. You can see that it must be an upside-down parabola, which passes through the x-axis when x equals 0 and when x equals m, and has an apex when x is exactly halfway between, that is, when x equals m on 2. At this apex, the derivative dx dt is maximised. This tells us that the growth rate is maximised when x happens to be halfway between 0 and m. We can now sketch the graph of x as a function of t. From features 2 and 3, we can see that x equals m and the t-axis form two horizontal asymptotes, and the curve has to fit in between. From feature 4, the growth rate is maximised when x has value m on 2, and the corresponding point on the curve will be a point of inflection. Moving down to the t-axis will reveal the time at which the growth rate is maximised. You can see a direct connection with the usual exponential function. If you look at the rule for x of t when the denominator is large, the plus 1 becomes negligible. By removing the plus 1, you get a simplified expression which becomes a constant times e to the kt, which is the usual exponential function. This approximation effect occurs towards the left of the graph at time t before the curve gets near the point of inflection. The model indicates that the population is growing approximately exponentially until factors kick in to halt the growth. The population is growing as fast as possible at the moment it reaches m on 2, and after that slows down and continues to slow down as it gets closer and closer to the maximum carrying capacity of m. Let's look at an example. Suppose a yeast colony starts off with a population of 100 cells. Suppose that it's growing most rapidly 10 hours later, at which time 500 cells are observed. Assuming a logistic model, let's find A, an upper bound for the colony size, and B, how long it takes for the colony to reach 90% of this maximum. Let t be the number of hours and x be the size of the colony, which is a function of t. Since we're assuming logistic growth, then x must take this particular form for some positive constants m, capital K and little k. The population is growing most rapidly at t equals 10 hours, at which time 500 cells are present. But the moment of most rapid growth occurs when x is m on 2, which is 500. Hence the maximum m equals 1000, answering part A. We can revise our formula and then think about tackling part B. We want time t at which x reaches 90% of 1000, which is 900. So we just have to unravel the formula for t. This is a straightforward algebraic manipulation. You can pause the video if you like and check this derivation. We have an answer for t, but we haven't finished because it involves capital K and little k. We know that the initial population was 100 cells, so that 100 equals x evaluated at 0, which is 1000 on 1 plus capital K. And we find that capital K equals 9. It remains to find little k. We know that the population was 500 when t equals 10. So I can feed that information into the formula, also using the fact that capital K equals 9. In a couple of steps, we get that 9e to the negative 10k equals 1. And you can check that k equals ln of 9 over 10. We have all of the ingredients to evaluate t. We seem to have a lucky cancellation, and the whole expression quickly evaluates to 20. The model predicts that it takes 20 hours for the colony to grow to 90% of the maximum. Is this just a coincidence that we produce such a simple whole number? It's always good practice to draw a diagram and check that your answer makes sense. Here t labels the horizontal axis and x the vertical axis. The initial yeast colony had size 100, which becomes the vertical intercept. After 10 hours, the population reached 500, so we now have 2 points on the curve. Because the rate of growth was greatest when the population reached 500, we can double that to get 1000, representing the limiting maximum predicted by the model. And this gives us a horizontal asymptote. We thus get a smooth sigmoid curve, having an inflection with coordinates 10, 500. We can mark off the value 900 on the x-axis, which is 90% of the maximum, move across to the curve and down to the t-axis to get the answer to part B of our problem, which we worked out before to be t equal to 20. Now the answer becomes transparent. The intercept on the x-axis and the point with coordinates 20, 900 exactly match up by a 180-degree rotation about the inflection point. If we'd thought of this, then we could have solved the original problem without using any formulae at all. Here's an application to sociology. Suppose that a rumour has been spread that calculus is fun in a small town with a population of 1,000 people. Initially 100 people know about it. After 10 days, 500 people know about it. How many days does it take for 900 people to know about it? We know the answer immediately. It must be 20 days, assuming that the spread of the rumour is modelled by the logistic equation. We know this answer because the data exactly matches the problem that we solved earlier regarding the yeast culture. Even though the physical manifestations are completely different, the underlying mathematics is the same. Is it reasonable for sociologists to employ the logistic model? Let's have a look. Here's the logistic differential equation where x represents the number of people that know about the rumour after t days. We can rewrite the right-hand side as k times m times x on m times 1 minus x on m. You can think of the product k times m as a single constant out the front. The factor x on m represents the proportion of the population that knows about the rumour. The second factor represents the remaining proportion of the population that is not yet aware of the rumour. This now makes sense. Initially, only a few people know about the rumour and it spreads like wildfire with approximately exponential growth. But after a while, a lot of people get to know about the rumour. When exactly half of the population knows about it, then the growth rate reaches a maximum. But after that starts to decline, it gets increasingly difficult to find someone that doesn't know about the rumour, and the growth rate dwindles to a trickle. In today's video, we modified the usual exponential growth model to form the logistic equation used to model population dynamics, by incorporating an inhibition factor as well as a growth factor in the equation. A solution is called a logistic function. We derived a general formula and described its most important features, which include a limiting ceiling on the size of the population, which is approached as the time variable gets arbitrarily large, and a sigmoid shape with 180-degree rotational symmetry about its point of inflection. We applied the logistic model to predict behaviour of a growing yeast population and also to predict the spread of rumours. Please read the notes, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon. This is the final video for this module on integral calculus, and indeed for the entire course. There's no new material and there are no exercises tied to this video, so afterwards you can move directly to the main quiz for this final module. Nevertheless, I think it's beneficial to have a video that creates unity by bringing ideas together. You'll notice many themes from the entire course permeate the narrative. Even just to let the story wash over you should be beneficial. If you have time to pause the video and check details here and there, you should find this video helpful in terms of general revision and developing your fluency with the techniques. Today I want to do something very special and come full circle to the discovery of the integral calculus in the 17th century by Isaac Newton, motivated by his remarkable estimate of the escape velocity of a rocket. This must have seemed like ridiculous science fiction at a time when space travel would have been unthinkable and absurd. In fact, Newton was thinking in terms of cannonballs, not rockets. There are apocryphal stories of him sitting under a tree, gazing serendipitously at the moon, stirred into action by an apple falling on his head. Who knows exactly what happened? In any case, we're the great beneficiaries of Newton's incredibly inventive imagination and vision and the rapid evolution of mathematics in the intervening centuries, supported by the great minds and genius of people such as Leibniz, Euler, Gauss, Agnesi, Riemann and many others. What follows is an extended example that takes us back to the birth of the integral calculus in the 17th century. Recall the witch of Maria Agnesi in its simplest form with rule y equals 1 over x squared plus 1, with global maximum 1 where it crosses the y-axis. What happens if we replace 1 in the denominator with a half? The curve gets stretched in the vertical direction and the y-intercept moves up to 2. What happens if we replace a half with a third? The curve stretches some more and the y-intercept moves up to 3. We can replace a third by a quarter and the y-intercept moves up to 4. We quickly see that if the fraction added to x squared in the denominator is 1 on k, then the y-intercept becomes k. What happens then if k heads off towards infinity? Well, the y-intercept of the witch must also head off towards infinity. But infinity isn't a number, so the curve can't cross the y-axis anymore. There must be some kind of explosion. And when the dust settles, the denominator becomes just x squared, so we get the curve y equals 1 on x squared, which can be rewritten as x to the minus 2. And it's good revision to check the shape of the curve against the sign diagrams for the first and second derivatives. The first derivative is negative 2x to the minus 3, that is negative 2 over x cubed, with sign diagram indicating that the curve is increasing from the left and decreasing to the right with undefined derivative at x equals 0. The second derivative is 6x to the minus 4, that is 6 over x to the fourth, with sign diagram indicating that the curve is concave up, both from the left and to the right, with undefined second derivative at x equals 0. So finally we do get a traditional witch's hat, with a sharp point somewhere off in the infinite distance. The simple rule y equals 1 on x squared is especially important in mathematics and science, and in particular features in the inverse square law used to model gravitation. Suppose we have two celestial bodies, such as planets or stars, separated by a distance of x units. I've drawn them as perfect spheres, but they can be irregular, it doesn't matter. In any case, they have centres of mass somewhere, and the distance x is measured between them. The body on the left has mass capital M, and the body to the right has mass little m. Denote the force of gravitational attraction by F, which is a function of x. it makes sense that F should be proportional to both of the masses. The greater the mass, the greater the gravitational attraction. It also makes sense that F should be inversely proportional to the square of the distance. Remember, the surface area of a sphere is 4 pi times the square of the radius. So you can imagine the gravitational force radiating uniformly outwards from a spherical body, distributed evenly over 4 pi times the square of the distance from the centre. The gravitational force on any unit of area is therefore proportional to the inverse to the total surface area of an expanding sphere, which in turn is proportional to the inverse of the square of the distance to the centre of the sphere. The overall constant of proportionality is denoted by capital G, also known as the universal gravitational constant. This was all known to Newton in the 17th century. There's some controversy about who stated this fact first, but certainly Newton was the first person to explore the mathematical consequences. Armed with this information about gravitational forces, let's consider a rocket moving away from the Earth. Denote the radius of the Earth by capital R, and the distance from the centre of the Earth to the position of the rocket, wherever it happens to be, by capital D. We can ask how much energy was expended in getting the rocket from the surface of the Earth to its present position. The total energy expended can be described by the following definite integral, where the distance x ranges from r, when the rocket was being launched on the surface of the Earth, to its present position d. The integrand is f of x, the gravitational force of attraction with the Earth, against which the rocket is propelling itself. In physics, if a force acts on an object that moves a certain distance, then the work done or energy expended is the product of the force with the distance. So multiplying the gravitational force f of x by some tiny change in the distance, represented by the differential dx, gives a tiny bit of energy required to move that tiny bit of distance. Adding up all these bits of energy, which we think of as being done continuously, is captured by the definite integral. Just think of the curly s integral symbol as summing up all of the energies captured by the products f of x times dx as x varies from r to d. But f of x is given by the formula g times capital M times little m over x squared, where little m is the mass of the rocket and capital M is the mass of the Earth. We have all of the tools to evaluate this integral. The constants come out the front. We can rewrite the integrand as x to the minus 2 and apply the fundamental theorem of calculus by evaluating the antiderivative minus x to the minus 1 between r and d, which becomes, in a few steps, the expression g capital M times little m times 1 over r minus 1 over d. Thus we find an expression for the amount of energy expended getting the rocket to its present position. We can ask what happens to this expression for the energy required as the rocket travels further out into space towards the distant stars, as d approaches infinity and the Earth vanishes to a single point. As d goes to infinity, 1 over d goes to 0. Thus, to reach the stars, in principle, the energy required becomes g capital M times little m times 1 over r. We can rewrite this as the fraction g capital M times little m over r. At the time, Newton was in fact thinking about cannonballs rather than rockets, making use of a continuous supply of fuel. You might recall in a very early video, we considered the trajectory of a cannonball shot directly upwards from the Earth's surface, and the graph of its displacement function turned out to be approximately a parabola. This all works out fine, assuming we're close to the Earth's surface, where the gravitational force may be regarded as constant. Up to this point, that was basically Newton's experience of cannonballs also, but he wanted to think about moving far away from the Earth, where the gravitational force can vary. For Newton, the question was, how much energy should you transfer to a cannonball at the moment it's fired that it manages to escape the Earth's gravitational field? The question then becomes, what should be the initial velocity given to a cannonball such that it has enough energy to escape? The energy required is given by our formula, but now little m denotes the mass of the cannonball rather than the mass of a rocket. We just need to link the velocity v that we're seeking with the formula for the energy required. There's one more fact from physics. The energy of the cannonball is a half mv squared. So we have a half mv squared equals g times capital M times little m over r. So, to find the velocity, we just have to unravel this equation. Observe that the mass little m cancels from both sides, so the velocity will in fact be independent of the mass of the cannonball. Rearranging and taking the positive square root yields a formula v equals the square root of 2 times g times m over r. But we want an actual number for the escape velocity. Getting back to the surface of the Earth, we have the universal formula for the force F, which we can rewrite as little m times capital G times capital M over r squared, expressed as mass times acceleration. And Newton had observed that near the surface of the Earth, the acceleration is about 9.8 meters per second squared. So we have at least gm over r squared approximately equal to 9.8. The last part of the puzzle is having an estimate of the radius r of the Earth. But happily this was provided by the Greek scholar and mathematician Eratosthenes in about 200 BC using clever measurements and some geometry, and was known to Newton and is about 6.37 times 10 to the 6th meters in scientific notation. Putting this all together gives v approximately equal to the square root of 2 times the acceleration 9.8 times the radius of the Earth, which comes to about 11,000 meters per second. Thus, to escape the Earth, a projectile has to be given an initial velocity of about 11 kilometers per second, and the mathematics also shows this to be independent of the mass of the projectile. This is the final video in this course, an introduction to calculus, and I wanted you to get a glimpse of how it all began and what motivated Isaac Newton, who, in parallel with Gottfried Leibniz, invented calculus in the 17th century. We've spoken at length in earlier videos about Leibniz notation, and it appears implicitly in the exposition above, leading to Newton's estimate of the escape velocity. Newton didn't have access to Leibniz notation, nor did he have access to the smooth and elegant framework for formulating the mathematics, which evolved subsequently over the 18th and 19th centuries, and which we, in modern times, too easily take for granted. This makes Newton's achievements and profound insights all the more remarkable. The first two modules of this course introduced ideas and techniques from pre-calculus, preparing for the third and fourth modules which introduced the differential calculus, which is really all about the study of slopes of tangent lines to curves. This fifth and final module introduced and discussed integral calculus, which is really all about the study of areas under curves. Remarkably, slopes of tangent lines and areas under curves turn out to be intrinsically linked, leading to the fundamental theorem of calculus. We began this final module by illustrating how one can use areas under velocity curves to estimate displacement, using averages of lower and upper rectangular approximations, and replicated thought experiments, originally due to the ancient Greeks, involving limits of approximations to discover the formula for the area of a circle and the area under a parabola. We then formalised the method of Riemann sums, using rectangular approximations to areas under curves over a given interval, and the definite integral, which is defined to be the limit of the Riemann sums, as the widths of subintervals in partitions of the interval go to 0. The definite integral captures precisely areas under a curve and has a symbolic description using an integral symbol, like a stylized S, which we can think of as a continuous sum, an integrand representing the rule of the function, a differential indicating the variable with respect to which we're finding the area, and terminals which tell us the endpoints of the relevant interval. We can calculate the definite integral exactly under certain conditions using the fundamental theorem of calculus. This provides a simple and elegant formula involving an antiderivative of the integrand, that is, a function whose derivative is the integrand. Antiderivatives are captured symbolically using indefinite integrals, the result of removing terminals from the definite integral, and provide convenient descriptions of integration formulae. These typically involve a constant of integration, due to the fact that all antiderivatives of a given function differ by a constant. We introduced and illustrated the method of integration by substitution, closely related to the chain rule for differentiation. We discussed odd and even functions related to rotational and reflectional symmetry, and noted in particular that the area under the curve of an odd function evaluates automatically to 0 over a symmetric interval. we discussed logistic functions, which are solutions of the logistic equation, which modifies the usual exponential growth model by introducing an inhibition factor, which provides a maximal limiting size to the population. The graph of any logistic function is a sigmoid curve with 180-degree rotational symmetry about its point of inflection. The purpose of this last video was to provide you with some context and insight concerning interacting ideas and motivation that led to the development of calculus from the 17th century. The mathematical treatment was only the briefest sketch and included important ideas from physics. You'll see a more thorough and rigorous treatment if you undertake further courses in advanced calculus. There are some notes accompanying this video which you can read out of interest and to support your mathematical development, but there are no new techniques required and no specific exercises. Thank you very much for watching, and especially for your sustained interest and participation over many weeks. I wish you well in your studies and look forward very much to seeing you again soon, exploring new horizons perhaps in future courses in mathematics.